before writing the program in any programming language, it is always better that we write an informal description of the solution, which is also called as algorithm. So big O is nothing but if you found out that algorithms are of two types. One is iterative algorithm and other is in computer science. A search algorithm is an algorithm that retrieves information stored within some data structure. Middle element and target element is not equal, but middle element is given in a sequence of numbers. You are supposed to put them either in ascending order or descending order. Instead of being greedy about profits, what I'll try to do is, now why is it called dynamic programming means, before actually calling a function, in order to solve any problem in computer science, generally we write programs. Before writing the program in any programming language, it is always better that we write an informal description of the solution, which is also called as algorithm. Okay, so see, now we have some problem to solve in computer science, and generally we solve the problems by writing programs, right? So if you have to directly write a program in some programming language like C, before writing the program you should write a blueprint, right? Or a, what can we say, in an informal language. In English like language, we want to describe what we want to write so that it will be easier for us to communicate before implementation. Okay, so that is called algorithm. So before going for any problem, solving problem, we have to write a program, and for writing a program we need algorithm. In general, if there is a problem P1, then there might be many solutions, right? So each one, let me call each solution as an algorithm. So there may be many algorithms, A1, A2, A3, A4, so on. There will be many solutions. Now, before implementing any algorithm as a program, we have to find out which among these algorithms are good in terms of time and memory. So we want to analyze every algorithm in terms of, one is time. Time means which one could execute faster, and second is memory. Memory means which one will take less memory, less time and less memory. So the course design and analysis of algorithms, design and analysis of algorithms will talk about how to design various algorithms, like for a given problem, how many algorithms are there and how to analyze them. So what will be the time taken by each one and what will be the memory required by each one. After designing and analyzing, we shall take the best algorithm. Let us say if this time taken by this one is something and time taken by all of this one is taking the least time and least memory, then we shall implement it as a program in C. So that is what is the main purpose of design and analysis of algorithms, right? So before going into taking an algorithm and analyzing it, we should get familiar with the terminology used in algorithms. So some of the notations which are used in algorithms are these. One is they are called asymptotic notations. Okay, so first one is big O. Big O represented like this, okay, by capital O. So big O is nothing but if you found out that, let us say you have found out that the algorithm, as the input size is increasing, if the time is increasing like this, okay, so this is the time complexity or the rate of growth of time, and this is the time growth, this is the n, which means if I keep on giving larger inputs to the problem, if the time increasing is like this, let us call it f of n, where f is a function of n and n is the size of the input. Assume that the time is going to increase like this as the input is increasing like this. Then what is the worst case or upper bound for this function? So we'll find out another function in such a way that that function is greater than the given f of n. Let's call it c into g of n, after some limit n equal to n naught. Okay, so for a given function, how do you find out f of n? I'll tell you later. Given an algorithm, you should be able to find out what is its time complexity or what is its f of n in terms of input n. Now, if you, after finding out this, if you can bound that function by some other function c into g of n in such a way that after some input n naught, the value of c into g of n is always greater than f of n, which means if f of n is less than or equal to c into g of n after some n greater than or equal to n naught, after all the values of input greater than or equal to n naught, where c comma n are real numbers and c is greater than 1, sorry, c is greater than 0 and n naught is greater than or equal to 1. For these conditions, if you satisfy this equation, then we can say that f of n is big O of g of n, which is nothing but f of n is smaller than g of n. That is what we could say. Okay, so I'll give you some few examples and find out if f of n, if these conditions can be met. So see this, let us say f of n equal to 3n plus 2 and g of n equal to n. So can we say that f of n is big O of g of n? If we have to say this, we have to find the two constants c and n naught. So if this has to be followed, then what should follow? F of n should be less than or equal to c into g of n for some c greater than 0 and for some n naught greater than or equal to 1, for some n greater than or equal to 1. Now what is f of n? 3n plus 2 should be less than or equal to c into n. Okay, now when can 3n plus 2 be less than or equal to cn? So you can substitute any value for c. So the best option is, by looking at this, I found out that c when it is equal to 4, that is better. Anything above 3 is also good, right? If I substitute c equal to 4, what I get is 3n plus n is less than or equal to 4n. Yes, we found a c. And what about n? So if you substitute, if you bring this 3n this side, then n has to be greater than or equal to 2, which means for every n greater than or equal to 2 at c equal to 4, f of n is less than or equal to c into g of n. Therefore 3n plus 2 is equal to is big O of g of n. Now we found out that if f of n equal to 3n plus 2 and g of n equal to n, then we found out that f of n is big O of g of n, which means this 3n plus 2 can be written by a constant multiplied by n, and therefore 3n plus 2 will be less than that. So if n is bounding this function, definitely n square will bound, which means if g of n for this one it is satisfying, then for any value greater than n, which means g of n equal to n square or n cube or n power n or 2 power n, for anything, all these functions, definitely all these functions are going to bound 3n plus 2. But we have to keep in mind that always big O is upper bound, definitely. Any of these answers is right, but always go for the least upper bound or the tightest bound. Here the tightest bound is n, right? So any of the answer is fine, but then go for n. Okay. Next one is big omega. So we generally write it as big omega of n. Let us say the actual time complexity or the function which is determining the time for an algorithm is increasing like this. So you have something increasing like this, and now you want to give a lower bound for this. Let us say this is f of n, which is n is nothing but the number of inputs. As the inputs are increasing, as the size of the input is increasing, the function is like this for some algorithm. And now if I give a lower bound for this, let us say this is c into g of n in such a way that c into g of n is less than f of n after some value of n, which is n naught, which means f of n is greater than or equal to c into g of n after some value of n. N is greater than or equal to n naught, where c is a constant which is greater than 0 and n naught is some input which has to be greater than or equal to 1. Why n naught is always greater than or equal to 1 is it is input. Input has to be at least 1. Okay. Now let's take an example and I'll explain you how it is going to work. Let us say f of n equal to 3n plus 2 and g of n equal to n. So can this f of n be bounded by g of n, which means can this f of n has lower bound as g of n? Just check this. So if that condition has to happen, if f of n has to be big omega of g of n, okay, then f of n should be greater than or equal to c into g of n. So what is it? F of n is 3n plus 2 has to be greater than or equal to n. Obviously 3n plus 2 is greater than or equal to c into g of n, even if c equal to 1, right? So even for c equal to 1 this is true, and moreover for what values of n? All values of n. Therefore n naught is greater than or equal to 1. So c equal to 1 and n naught is greater than or equal to 1. We found out the values of c and n for which the condition gets satisfied. Therefore we can say that 3n plus 2 is omega of n. Okay. Now is this 3n plus 2 is omega of n means 3n plus 2 will be lower bounded by n. So can we check if 3n plus 2 and n square, let us say f of n equal to 3n plus 2 and g of n equal to n square. Can 3n plus 2 be lower bounded by n square? Just check this. If it has to be 3n plus 2 has to be omega of n square, which means if we don't know, right? So if 3n plus 2 has to be omega of n square, we are not sure, that is why I am writing with a question mark. Then what should happen is 3n plus 2 has to be greater than or equal to c into n square for some n naught, for some value of n naught, which means after some value of n, given some values of n, this condition should satisfy always after n naught. Then can you find such as c? It turns out that we cannot find such as c for which this condition can be satisfied, which means 3n plus 2 can never be lower bounded by n square, but then it can be upper bounded by n square. Okay. So if you found out that f of n is omega of n, then anything less than n can be answer, which means if f of n is lower bounded by n, then it will be even lower bounded by anything less than n, which means you can go for log n. Log n is less than n, it will be lower bounded by this, or you can go for log n, it will be lower bounded by this. Okay. So what I mean to say is there will be more than one answer for big O and omega always, but then it is better that you take the closest bound or the tightest bound, tightest lower bound here, and in case of big O, tightest upper bound. Okay. We shall see more examples about it. Now let's see theta. Big theta. Okay. So what about big theta is, if I have a function f which is growing with respect to n, if this is the size of the input and if a function f is there which is growing with respect to n, okay, then I should find both the upper bound and lower bound by a function just by varying the c values of constant. So if I can find a function which can even upper bound it and lower bound it, if this is f of n and this is c1 into g of n and this is c2 into g of n, if f of n is bounded by g of c1 into g of n and c2 into g of n, then we can say that f of n is theta of g of n. So these constants C1 and C2 could be different, and moreover, after what value you could take any value after which it is true. So let us say this value is n0, which means after this value of n0, both of them will agree, which means C1 into g of n will be less than f of n, and C2 into g of n will be greater than f of n. Okay, so we say that a function f of n is theta of g of n if f of n is bounded by g of n both in the lower as well as upper, right? So which means C1 into g of n should be less than or equal to f of n should be less than or equal to C2 into g of n, where C1 and C2 are constants greater than 0, and this should be valid for all values of n0 greater than or equal to some. For all values of n greater than or equal to n0, where n0 has to be greater than or equal to 1, any constant. N0 can be any constant, right? So in the previous example, if you see, once we have taken this example, so f of n equal to 3n plus 2 and g of n equal to n, right? And we have seen that f of n is less than or equal to g of n, f of n is less than or equal to c into g of n, where c equal to 4. If I have this 3n plus 2, it is less than or equal to 4 into n, where C2 equal to 4, which means I can find out the upper bound for the function f of n when I substitute in place of C2 4, right? And this is valid for all n0 greater than or equal to 1. This is valid, isn't it? So always 3n plus 2 is less than or equal to 4n, which means g of n can be a upper bound for f of n, as well as let us see if it is lower bound as well. So f of n is greater than or equal to c into g of n for what values? 3n plus 2 is greater than or equal to, let us say this is C2, this is C1, okay? And now if I substitute C1 is equal to 1, which means C1 equal to 1 means I get n. Then for all values of n0 greater than or equal to 1, then I can say that f of n is greater than or equal to C1 into g of n, which means this 3n plus 2 is bounded by g of n both in the upper bound as well as lower bound. For the upper bound, C2 is equal to 4, and for the lower bound, C1 equal to 1, and both the cases are valid for n0 greater than or equal to 0. So sometimes this theta is also called as asymptotically equal, which means if the leading term in the function is going to be n, then you can take n as the g of n because they are asymptotically equal. If I have 3n square plus n plus 1, then it will be theta of n square, isn't it? Always the leading term, the dominating term can be taken here. If I have 3n cube plus n square, this is always theta of n cube, okay? So now we have seen three notations. I'll show you why these three notations are useful: big O and big omega and big theta, okay? So we have seen what is big O and what is omega and what is theta. Then what are the practical significance of all these notations is, given any algorithm, big O is going to say the worst case time or the upper bound, which means if you are giving any time in terms of big O, it is also saying that in any case your time will not exceed this. So if you are giving the time in case of, if you are using omega, it is giving the best case, which means in any case you can never achieve better than this. And theta is giving you the average case, right? So generally this omega gives us the worst case, okay, and big O gives the worst case, and omega gives the best case, and theta gives the average case, right? So if you see, in practice, we are not interested in what is the best time that this algorithm could execute. We are always interested in what is the worst case time that will be taken by this algorithm for any input. That is what we are interested in. So we are not interested in finding out the best cases. We are generally interested in finding out the worst case, right? And when do we use this average cases? When best case and worst case both are same. For some algorithms, the best case and the worst case both will be same, which means there is, for any input, it will take the same time. So in such cases generally we go for theta. Understand this? So in practice we are going to use big O in the worst case time to find out the worst case of an algorithm, and we are going to use omega in order to say that this is the least time possible. You can never go beyond that, which means it is the lower bound, it is the upper bound, and it is the average case. So in order to make this point even clear, I'll take a practical algorithm and I'll show you how it works. Assume that we have an array of numbers like this: 5, 7, 1, 2, 4, 10, 20 and 11, something like this, an array. Now we have to search for an element. So given this input, let us assume that the size of this array is n. Let us say I want to search for an element. Then in best case, and I am going to use linear search. Linear search means I'll compare. Let us say x is given and I want to find out whether this number x is in the array or not. Then I'll take the x and compare with the first element, second element, third element, fourth element. I'm going to do this sequential search, okay, linear search, which means I'm going to not go to any particular element. I'll go to all elements one after the other. So given this algorithm, what is the best case time we could execute this algorithm in? So best case time is nothing but if the element that we want to search is 5, then in best case we could search it in one comparison, isn't it? Which means in just one step we can find it out. Therefore the best case algorithm, best case time, if you want to write, you have to write like this: omega of 1, which means in best case you can find out the element in just one comparison or in one step. Now then, what is the worst case? Worst case is if I have n elements in the array and if I am searching for an element, then in worst case I might have to compare with all the elements. Therefore worst case time is going to be big O of n. Then what is the average case? Average case is worst case, and in general if there are n elements, if you do some amortized analysis is nothing but average analysis. So you can find out that it is nothing but theta is big, theta of n by 2. So which is nothing but theta of n. So that is how all these three notations are varying. So first notation says that this is the worst case, you can never go beyond this, and this notation says that this is the best case, you can never go down beyond this, you can never go up beyond this, and this is generally average case is used whenever worst case and best case are same. So for this example we don't generally use average case theta, right? So we are going to generally, for any practical purposes, we are never interested in best case, we are always interested in big O, and in case best case and worst case both are same, we generally use theta. So keep that in mind. Okay, till now we have seen that either discussing about big O or omega or theta, we have seen that there is a function which is growing like this, which is the actual time taken by the algorithm, and n is the input size. But in practice, even though we are saying that this is the time taken by the algorithm to exist, but when you write it into the program and execute it, this is not the real time, this is just an approximation. It means that if f of n increases for the algorithm, for the program time increases. If f of n decreases for the algorithm, for the program time decreases, which means this is not actually the real time, it is just an approximation. And now let's see how to find out this f of n, which means what is the approximate time taken by an algorithm to finish. That is just an approximation, right? So how to approximate the time taken by an algorithm? So in order to find it out, first of all we should understand that there are two types of algorithms. Okay, so algorithms are of two types. One is iterative algorithm and other is recursive. Okay, so coming to iterative algorithm, the algorithms will look like this. So if I have for I equal to 1 to n, so we are doing something, so max of a comma b, something like this, right? So if you are doing it in a for loop or while loop or do while loop, then it is generally called iterative algorithm. And recursive algorithm is like this: if there is a function a which takes an input of size n, and it is again computing the value in terms of the same function a, something like this. So if a is calling itself, then it is called recursive, and if there is no function calling, and if it is having a for loop or while loop, then it is called iterative function. It is worth noting that any program that could be written using iteration could be written using recursion, and any recursion can be converted to iteration. Therefore both are equivalent in power, so nothing is more powerful than the other. That is one thing you should note. And the second thing is how to analyze these programs. They basically differ. So in order to analyze such an iterative program, we have to count number of times a loop is going to get executed, one thing. And if you have to count the iterative program, I mean if you have to find out the time taken by an iterative program, we use recursive program, we use recursive equations, which means we write a function of f in terms of function of n by 2. It is f of n and it is f of n by 2. So both of them, the analysis wise both are different, the power wise both are same, but analysis wise both are different. In case if the algorithm does not contain either iteration or recursion, then it means that there is no dependency on the running time on the input size, which means whatever is the input size, the running time is going to be a constant value. So if there is no iteration or recursion inside the program, you need not worry about the time at all. It is going to be constant time. So for such programs we write order of 1. Order of 1 represents constant time. Let's now see all the examples of some examples of iterative programs, which will give us some depth about how to analyze this. See the first example. In this example, in this algorithm, we have an integer I and we have a for loop, and for loop is writing one more thing. Whatever code I am writing, it is not corresponding to the syntax of any programming language. You can just consider it as a general English. Okay, so there is an integer I. For I equal to 1 to n, printf Ravi. How many times this name will be printed? So how it will be printed is, for I equal to 1, I equal to 1 to n. Therefore for I equal to 1 to n, which means total n times this line will be printed, right? Therefore I say that the complexity of this algorithm is order of n. Okay, in case if I have something like this, instead of this only n, if I have again int I comma j, I have it, and I have for j equal to 1 to n, printf Ravi, right? Then how does it work? So this one is going to, outer loop is going to run n times, and for every time outer loop runs, inner loop runs n times, which means totally it will get executed n square times. Then in this case the time complexity is going to be order of n square. If we have one more loop, in nested loop, then again it is going to be order of n cube. That can be extended. See this question is important. This has been asked in GATE 1991. So I have just changed the program. They didn't ask this exactly printf Ravi. I just changed it. Now see how many times this while loop is going to get executed. There is I and j, two variables, and then while s is less than or equal to n, which means s is going to start with 1 and it is going to go till the point where s crosses n. So how is I incrementing? I is getting incremented in steps of 1, and how is s getting incremented? Every time you enter the loop, s is going to get incremented exactly by a value of I, which means the increment in I is linear, but the increment in s is actually depends on I. Let's see how these two I and s are getting incremented. Initially I is 1 and s is 1, right? So when it enters one time, how much will I be incremented? By 1. And how much will s be incremented? S equal to s plus I, which means whatever is this, whatever is s, to that you have to add I, which means these two will be added and we are going to make it 3, right? And then this is second time, and again one more time when it enters the loop, I is going to be incremented by 1 and s is going to be incremented by whatever is the value. So s value plus I, which is 6, and again it is going to be incremented by 1 I, but then s is going to be incremented by 6 plus 4, which is 10, so on. So maybe do one more time, 5, 15, one more time, 6, 21, so on, right? Now when is this thing going to stop? When is this entire loop going to stop? This entire loop is going to stop whenever s value reaches a point where the value of s is greater than n. So whenever s reaches a value which is greater than n, okay, so if you cross the value of n, then it is going to stop. So let us say, I don't know how many times it is going to get executed. Let me say k. By the time we reach k iterations, I am saying that this while loop is going to be stopped after k iterations, and after k iterations the value of s has to be greater than n. That is what I say. Therefore, what will be the value of s after k iterations? That is what we have to find out. Now if you see the value of s, how it is increasing is, for I equal to 1, s equal to 1, for I equal to 2, s equal to 3. So if you observe this, it is nothing but sum of the first two natural numbers is s value, which is nothing but 3, and when I equal to 3, s value is sum of the first three natural numbers, and when I equal to 4, s value is sum of the first four natural numbers. When I equal to 5, s value is sum of the first five natural numbers. See, when I equal to 1, it is 1, and when I equal to 2, s value is 1 plus 2, which is 3, and when I equal to 3, s value is 6, 1 plus 2 plus 3. When I equal to 4, s value is 1 plus 2 plus 3 plus 4, 10, right? Which means by the time I reaches k, s value will be sum of first 10 natural numbers, which means s value will be k into k plus 1 by 2. By the time I reaches k, s value will be sum of first k natural numbers, which is k into k plus 1 by 2. Now if this loop has to stop, then k into k plus 1 by 2 has to be greater than n. So from this equation it is clear that this side I will get a function in terms of k square plus k by 2, and this side I get a function of n, which means the number of times I get executed, that is k, is actually order of root n. Okay, therefore this loop will get executed in order of root n times. Okay, read this example first. For I equal to 1, I square less than or equal to n, I plus plus, printf Ravi. How many times this will be printed is, I is going to run from I square till I square is going to be less than or equal to n. So one other way of writing this is, instead of writing I square is less than or equal to n, we could write I is less than or equal to root n. Therefore this loop will run for I equal to 1 to root n, which is nothing but this one will be this statement will be executed exactly root n times. Therefore the total number of times this one is going to get executed is root n. So the time complexity is order of root n, right? And so in this case we should observe one thing is, the best case is root n and the worst case is root n, and even the average case is root n. Therefore it is even better if you write theta of root n. It doesn't make any difference, either you write big O or theta for such examples, it doesn't make any difference. In case if there is any break statement depending on something inside the loop, then we could have best case, worst case and everything. Okay, so look at this one next. This is interesting. We have ij, kn variables, and this outer for loop is running for I equal to 1 to n, which means this outer for loop will run totally n times, and the inner j loop, this one is running from j equal to 1 to I, which means this one will run the number of times this inner for loop will execute depends on the value of I, and the innermost for loop, this one, it is running for k equal to 1 to 100, which means the number of times the innermost for loop executes is independent of I and j. So it is a constant. So whatever happens, every time you get into this j loop, you will execute this 100 times. Okay, So how to analyze this is, just see what happens, what is the value of I, and for each value of I, how many times this one will be printed. That way we can actually unroll the loops. So I'm going to say, initially if I equal to 1, how many times will j loop be executed, and how many times will k loop be executed in total. So j loop will be executed exactly for j equal to 1 to I, which means only one time, and k loop will be executed exactly 100 times for each j value. So j is executing one time, and for every time k will be executed 100 times. Therefore k will be executed 100 times in total. Okay. Now for I equal to 2, how many times j will be executed? J loop will run from j equal to 1 to 2, isn't it? For j equal to 1 to 2 means it is going to be executed 2 times. J is going to be executed 2 times, and this inner loop, this is going to get executed 100 times for each execution of j, which means k loop will execute 100 times for every time j is getting executed. How many times j is getting executed? 2 times. Therefore k is getting executed 2 into 100 times. Therefore this printf is going to be printed 200 times. Now for I equal to 3, let's see what happens for I equal to 3. For I equal to 3, j is going to get executed exactly for j equal to 1 to 3, which means 3 times, and k is getting executed. The number of times k will get executed is, for every value of j it will get executed 3 times, which means j is taking 3 times, and k will execute 100 times for every value of j, which is nothing but 300 times, right? So now coming to I equal to 4, what happens is, for I equal to 4, j will get executed for I equal to 1 to 4, which means 4 times, and k will get executed 100 times for every value of j, which means k will get executed 4 into 100 times. And for I equal to 5, j will take 5 values, which means j will get executed 5 times, because j is from 1 to I, and for every time you get into j, k will get executed 100 times, which means 5 into 100, right? So on. For I equal to n, j will get executed n times. Why? Because j is going to take values from 1 to n, and for every time j gets executed, k will get executed 100 times, and j is getting executed n times, therefore it is n into 100. So if you take the total number of times this printf is going to be printed, it is 100 plus 200 plus 300 plus so on plus n into 100. So total number of times this printf is getting executed is 100 plus 2 into 100 plus 3 into 100 plus so on plus n into 100. So if I take out 100 as common, then what do I get? 1 plus 2 plus 3 plus so on plus n, which is nothing but 100 into n plus 1 by 2. So which is nothing but order of n square, right? See this example. There are variables I, j, k, n, and out of for loop is running for I equal to 1 to n, which means out of for loop will run n times, and for every value of I, inner j loop will execute for j equal to 1 to I square, which means the number of times this j loop will execute depends on the value of I. If I equal to 1, j loop will execute 1. If I equal to 2, j loop will execute 4 times, which means j value is depending on I. So whenever there is dependency like this, you have to unroll it, which means what is unrolling is, for every value of I, you have to check how many times this is going to get executed. In case if there is again a dependency, again you have to unroll it for every value of I, for every value of j, how many times it is going to get executed. Just see the dependency here. The innermost k loop is executing k is from 1 to n by 2, which means k is not actually depending on I or j, and k is a independent loop. Therefore you need not unroll j. So how to solve such a question is, see, I is executing from 1 to n, which means n times, and j is executing for every value of I 1 to I square, and k is executing 1 to n by 2. Then how to solve this is, for I, whenever I equal to 1, then j is going to get executed from j equal to 1 to I square, which means 1 to 1. J is going to execute it only one time, and for every value of j, k is going to execute it n by 2 times, and since j is going to be executed only one time, therefore the innermost k loop is going to execute it n by 2 into 1 times. For I equal to 2, j is going to get executed from 1 to I square, which means I square is nothing but 4. Therefore j is going to get executed 4 times, and for every execution of j, for every time j gets executed, k is going to get executed n by 2 times. Therefore total number of times k is going to execute it is n by 2 into 4. For I equal to 3, j is going to get executed 9 times, and for every time j gets executed, k is going to get executed n by 2. Therefore total number of times k gets executed is n by 2 for every time for each j, and there are 9 such j's. Therefore 9 into n by 2. So on, for I equal to n, j gets executed n square times, and for every execution of j, k will get executed n by 2 times. Therefore n by 2 into n square. Now the total number of times this printf will be printed is, this Ravi will be printed is the total number of times k getting executed. Therefore what is that number? N by 2 into 1 plus n by 2 into 4 plus n by 2 into 9 plus so on plus n by 2 into n square. So if you pull out n by 2 as common, then what do I get? 1 plus 4 plus 9 plus so on plus n square. So it is nothing but n by 2 into n plus 1 into 2n plus 1 by 6. Isn't it? Sum of first n square natural numbers. Sum of squares of first n natural numbers. It is nothing but n into n plus 1 into 2n by 2. So you could either even write it as order of the most significant term, n into n into n into n, which is nothing but n power 4. So always remember, if I have a function as f of n equal to n power k plus n power k minus 1 plus so on, you could write it as order of n power k, which means n power k can be used to bound this function tightly. Okay, so in this case it is going to be order of n power 4. Okay, see how is I going to be, see this example. I is 1 from I is going from 1 to n, and I is incrementing not in steps of 1, it is getting incremented double every time, which means here the increment is not linear, it is going to be multiplied with 2 every time. Then how many times will it get executed is, let's see how I is going to get incremented. I is going to start with 1, and then it is going to get double, which means 2, and then 4, and then so on, so till we reach a value where we hit n. Let us say it is going to take k iterations by the time we reach n, which means I is going to be 1 initially, which is nothing but 2 power 0, and then 2 power 1, and then 2 power 2, so on. Let us say 2 power k. At this point, 2 power k is equal to n, and we stopped. Then how many times does it get executed is, when 2 power k equal to n, it is getting executed k times, right? This printf is going to be printed k times, which means 0 to k minus 1, and when actual value of this is 2 power k, which is equal to n, we are going to stop. Then what is the value of k that we get is, k is going to be log n, which means we are getting executed log n times. Therefore we can even say the total number of times it gets executed, or time complexity, is order of log n. Okay, now so whenever you remember it, whenever I is running from 1 to n, and if I is incremented in terms of 2, then the time complexity is going to be log n base 2. Right, in case instead of 2 if you had 3, then it is going to be log n base 3. In case in terms of in place of 3 if you had 6, then I is going to be then the time complexity is going to be log n base 6. So whatever it is, in terms of this value, this number, you have to write log n base that number. In case if it is going to get executed, incremented in terms of 10, then the for loop is going to executed log n base 10 times. Okay, so that depends on what is the steps of increment here. Now depending on that question, let's answer the second question here. Depending on the first question, see this, for there are three variables I, j, k. For I equal to n by 2 to n, which means this I is going to run for n by 2 times. From n by 2 to n means this one is going to run for n by 2 times, and this one is going to run for j equal to 1 to n by 2, which means again this is going to run for n by 2 times. And now this one for k equal to 1 to n, k is getting incremented in steps of 2. We have already seen that if there is any such loop, then that gets executed log n base 2 times, right? So there is no dependency. Every loop is running independently. Therefore, you need not unroll the loops. You could directly take it and multiply like this. So the total time that they get executed is, that printf get printed is n by 2 into log n base 2. Therefore, what is this total time? Order of n square log n base 2. This is the total time. Okay. See this example. For I equal to n by 2 and I less than or equal to n, I plus plus, which means this outermost for loop is going to get executed n by 2 times exactly, from n by 2 to n, right? And this one for I equal to one more thing, it might be n by 2 plus 1 or minus 1. There is a small difference, but however it is going to be order of n by 2, this one. Okay, it has to be strictly I less than n, then only it is going to be n by 2 times, but now understand that it is going to be n by 2. So this one, for I equal to 1, I less than or equal to n, it is going to be incremented in steps of 2, which means it is going to double. It is not incrementing linearly. So we have already seen that for such a loop it is going to be log n base 2. What if it is I is less than or equal to n by 2? Then it will be log n by 2 base 2, right? Then this one is for k equal to 1, k less than or equal to 1, k equal to k into 2, which means k is again keeping on doubling until we reach n. Therefore, even for this it is log n base 2, right? So how many times will this printf be printed is n by 2 into log n. So that is nothing but n by 2 into log n base 2 whole square, right? So what is it? It is order of n into log n base 2 whole square. That is how we write it. So order means we just remove the constants and we let the most significant term remain. What is the most significant term here? N into log n base 2, right? And next one is, look at this example. Assuming that n is greater than or equal to 2, which means n is going to start from 2, what will be the number of times this program will get, this inner loop will get executed is, initially when n equal to 2, we enter the while loop once, and by the time we come out of the while loop, n will be 1. Now n is not greater than 1, therefore it will stop. Therefore only one time. If n equal to 2 power 1, this while loop is getting executed only once. If n equal to 2 power 2, which means 4, then we enter the while loop once. By the time we come out of the while loop, it will be 2, and again it will get executed once, and by the time we come out of the while loop, it will be 1, and we will not go into it anymore, which means if n equal to 2 power 2, while loop will get executed 2 times. If n equal to 2 power 3, which means 8, we will enter the while loop once, and by the time we come out of the while loop, the value of n will be 2 power 2, and now again we enter the while loop once. By the time we come out of this while loop, the value will be 2 power 1, and again we enter it once. By the time we come out of it, the value will be 1. We are going to stop it. Therefore, when the n value is 2 power 3, we are going to get it executed exactly 3 times. So assuming that n is a power of 2 and n equal to 2 power k, we can say that it is going to get executed k times, where k is log n base 2, isn't it? If we assume that n is a power of 2, which means n equal to 2 power k, then we can say that this loop is going to get executed k times. Therefore k is log n base 2. Therefore the number of times this one will get executed is log n base 2. If n is not a power of 2, let us say n is 20, then we enter it, and then by the time we come out of the while loop, the value of n will be 10, right? And then we enter one more time. By the time we come out of it, value of n will be 5. We enter it one more time. By the time we come out of it, value of it will be 2. We enter it one more time. By the time we come out of it, value of this will be 1, which means if n equal to 20, we get it executed 4 times, which is nothing but log 20 base 2, right? It is floor. Why? Log 20 base 2 is 4 point something, and it is getting executed exactly 4 times, therefore this. So the time you can say is order of log n base 2. It is enough, but even if you can put the floor, then it is fine, not an issue, right? So what you should understand here is when we are trying to start from a value and when we are trying to reach 1, not in steps of 1 but by dividing with 2, then it is going to be log n base 2. What if this is instead of 2, if it is 5? If it is 5, then the answer will be log n base 5. If it is 10, then the answer will be log n base 10. Okay, so this is an important model. See this example. For I equal to 1, I less than n, I plus plus, which means this loop is going to get executed n times, and internally for j equal to 1, j less than n, which means j is going to go from 1 to n, but the steps of incrementing j depends on I, which means there is a dependence between outer loop and inner loop. Whenever there is dependence, you always try to unroll it. Unroll means for the value of I, for each value of I, how many times the internal loop will get executed. Okay, so initially when I equal to 1, what happens is j is going to get executed from 1 to n, and the steps of increment is 1. Therefore total number of times j is getting executed is n times. Therefore total number of times printf will be printed is name will be printed is, for I equal to 1, it is n times. For I equal to 2, again j is going to get incremented from 1 to n, fine, but then the increment is in steps of 2, which means we'll reach n faster in this case. Why? Because j equal to 1, then 3, then 5, so on. Here j equal to 1, 2, 3, 4, so on, but here j equal to 1, 3, 5, 7, so on, which means j will get incremented very fast, and the number of times this j loop will get incremented is executed is nearly n by 2 times, because we are not going to enter this and print Ravi for every value of j. We are going to print it only for the alternative values of j, which means it will be near n by 2 times. Now for I equal to 3, again j will get executed from 1 to n, but then the increment of j will be in steps of 3, which means 1, 4, 7, so on. Therefore it will even reach faster. J will reach n very fast, and the number of times we enter the loop is n by 3 times, so on. So whenever I equal to k, then j has to run from 1 to n, but then increment will be in steps of k. Therefore number of times Ravi will be printed is n by k times. And now when I equal to n, then j will run from 1 to n just in one step, which means in first time the loop will be 1, first time j value will be 1, and second time j value will be n plus 1, which means it will only get executed one time, right? So if you see this, which means n by n times, if you see this, the total number of times this printf will be printed is n into 1 plus 1 by 2 plus 1 by 3 plus so on plus 1 by n. So this is nothing but log n definition. So log n is nothing but 1 plus 1 by 2 plus 1 by 3 plus so on plus 1 by n. Therefore it is equal to order of n log n. So that is the execution time of this. So let's analyze this program. n equal to 2 power 2 power k, which means n is given as a fixed constant and n's value depends on k. Okay, and for I equal to 1, I less than or equal to n, I plus plus. So I is running from 1 to n and it is incrementing in steps of 1. Why? Because it is in I plus plus, right? Therefore, how many times will the outer for loop will get executed? N times. There is no change in it. Now coming to the internal loop, for j equal to 2, j less than or equal to 1, j equal to j square. So j is running from 2 to n, but not in steps of 1 or steps of doubling. It is actually getting squared every time, j equal to j square. So in order to analyze this, j value is depending on n. So n is 2 power k. So in order to analyze this, let's keep substituting the values of k. For k equal to 1, let's see what happens. For k equal to 1, what is the value of n? Value of n is 2 power 2, which is 4, right? Then how many times will this loop be entered is, initially j equal to 2 and j is less than 4. Yes, j is less than 4, therefore it will be entered. And then j equal to, next time is j square, which means j equal to 4, then j is less than or equal to n. Yes, true. Why? Because j is less than or equal to 4 is less than or equal to 4, which means second time it will get entered and printf will get printed. So when k equal to 1, then the total number of times we are printing this Ravi is 2 times, isn't it? And how many times will it get totally printed? N times, because n times we are going to hit this, isn't it? Therefore it is 2 into n times. In case if k equal to 2, then what happens is n value will be 2 power 2, which is nothing but 2 power 4, which is 16. N value will be 16. Then initially j value will be 2. Then the for loop will be entered once, because 2 is less than or equal to 16. Then j value will be squared, which means 4. 4 is less than or equal to 16 one time, it will again enter it, and again 4 will be squared, which means 16. Then again we are going to enter one more time, and then k will be 16 into 16, which will be greater than 16, therefore it will not enter. Therefore the number of times printf will be printed for a value of k equal to 2 is 3 times, isn't it? 3 times it will be printed, and outer for loop will run always n times, therefore it is going to be printed totally n into k time, n into these many times when k equal to 2. When k equal to 3, let's see how many times this enter, we enter j loop and print Ravi. So n equal to 2 power 3, which is nothing but 2 power 8, right? So j will be initially 2, we'll enter the while loop once, then j will be 2 square, we'll enter the while loop once, then j will be 2 power 4, we'll enter the while loop once, then j will be 2 power 8, 2 power 8 is less than or equal to 2 power 8, we enter once, next time it will be 2 power 16, which will be greater than this, therefore we will not enter it. So how many times are we going to enter this j loop and print Ravi is 1, 2, 3, 4, which means if k equal to 3, we are going to enter 4 times. And what about this one? This one will already get executing n times, therefore total it is n into 4 times. See, outer for loop there is no change, n times, always n times, but then inner loop that depends on the value of k. How is it depending? If k equal to 1, it is getting executed 2 times. If k equal to 2, it is getting executed 3 times. If k equal to 3, it is getting executed 4 times. Therefore if k value is k itself, then how many times it will get executed is, outer for loop will get executed n times, and then inner j loop will get executed k plus 1 times. Therefore this is the total number of times this this printf will be printed. Then I want the answer. If I want the answer in terms of k, only n's, not in terms of k. If you want the answer in terms of k, then you can substitute in place of n 2 power k. If I want the answer in terms of n, then what you should do is convert it. So n equal to 2 power k. Apply log on both sides. That implies log n equal to 2 power k, log n base 2, right? That implies log n equal to k. therefore k equal to log n. So k here we get it as log n, so that equal to n into log n plus 1. So what is the leading term here? Leading term is n into log n. So total expression is n into log n plus n. So in which the leading term is n into log n. Therefore you can say that the time complexity is n into log n. Okay. So this is the time complexity of this algorithm. So we have seen that there is the other kind of program which is called recursive programs. So recursive model is, if I have a function a and if the size of the input is n, in order to solve this problem I'll call a function, again the same function with something like n by 2 or again n by 2, something like this written, which means a function calling itself is called recursion, and whenever such a function is given, the way in which you have to analyze the time complexity is very much different from the way we used for iterative functions. The reason is there is nothing to count here. That is why we write something called as recursive functions and then we try to analyze them. So how do we write it is, in order to solve a of n, let us assume that time taken is t of n. Okay. Now how is that time split up is, first of all we are trying to do some comparison here, something if condition. Let us assume that for if condition time taken is some constant, and then we are going to find out on t of n, this a on n by 2 and again a on n by 2, and then we are summing up. So there is some constant time involved for this if condition and for this addition, therefore some constant time plus we are calling a of n by 2 two times, which means 2 times. If for t of a of n time taken is t of n, then for a of n by 2 time taken will be t of n by 2. Okay. So this is how we should write the recursive functions, and then we should try solving these recursive functions. So one way how we could solve the recursive function is, I'll take an example and I'll show you. There are various ways, I'll take some examples and I'll show you this. See, one way of solving this function is, assume that the function is like this: a of n, if n is greater than 1, then return a of n minus 1, something like this. Which means if you assume that time taken for t of a of n is t of n, then that time is actually some constant time for this comparison, and after that constant time taken to solve the problem on n minus 1 inputs, which means you can write it like this: the recursive equation will be t of n equal to some constant time, let us say 1. We could represent the constant time using 1 or c, it doesn't matter. Okay. And then after this the time will be taken to solve this. If time taken to solve this is t of n, then the time taken to solve a of n minus 1 will be t of n minus 1, isn't it? Now how to solve it is, one way is called back substitution. So we have one method which is called back substitution. I'll show you that. So this method can be applied for all the any model of the problems, but the problem with this method is it is somewhat slow. Let me solve it. So t of n equal to 1 plus t of n minus 1, right? Then what will be t of n minus 1? If I substitute in place of n minus 1, then I get 1 plus t of n minus 2. Why? In place of n minus 1 I am substituting n minus 1. And now what will be t of n minus 2? In order to find out t of n minus 2, in place of n you substitute n minus 2. Then I get t of n minus 2 equal to 1 plus t of n minus 3, right? Let me call it equation 1, equation 2 and equation 3. Now you substitute equation number 2 in equation number 1. Then what do we get? T of n equal to 1 plus, I am substituting equation number 2 in equation number 1, which means in place of t of n minus 1 I am going to put this entire thing, equal to 1 plus t of n minus 2, that equal to 2 plus t of n minus 2, right? and now in place of n minus 2 I am going to substitute this entire thing, t of n minus 2, I am going to substitute this. Then what do we get? 2 plus 1 plus t of n minus 3, right? That equal to 3 plus t of n minus 3. So we can go on like this, and finally you are going to get k plus t of n minus k. Okay, so this is what you are going to get finally. So if k, then we are going to get k plus t, t of n minus k. Then where do you want to stop it? When are you going to stop it? So see the algorithm when it is going to stop. So this equation t of n equal to 1 plus t of n by 2, t of n equal to 1 plus t of n minus 1 is valid only when n is greater than 1, isn't it? So this is valid when n is greater than 1. Then what happens if n becomes 1? N is going to start from a very large number and it is going to gradually decrease. According to this algorithm, it is going to gradually decrease, and at some point it is going to reach 1. Therefore, whenever it reaches 1, we are simply going to stop, which means we will just do the comparison, this one, and whenever it is 1, we are going to stop, right? So this is called anchor condition or base condition or stopping condition, which is going to stop the recursion. Now this one will stop. If you want to eliminate it, then you should get t of 1 here. If I have to get t of 1 here, then n minus k has to become 1, which means n minus k has to become 1. Then for what value of n minus k will become 1? Then for a value of n equal to, or for what value of k, this n minus k will become 1. For k equal to n minus 1, this value will become 1, which means in place of k I am going to write n minus 1. So on, in place of k I am going to write n minus 1 plus t of n minus 1. Then what do we get? N minus 1 plus t of 1, that equal to t of 1, we already know that it is 1. Therefore it is n minus 1 plus 1, that equal to n. Therefore t of n equal to n. You can even write it as order of n. This is the answer. This is called back substitution. So just recollect what we have seen. Now if there is an algorithm which depends on the input size of n, then I am writing it in terms of input size of n minus 1. Then I am using a method. After writing this recursive equation, how did I write recursive equation? Let us assume that time taken to solve an instance or a problem of input n is t of n. Then how is that time split up? It is actually the time taken to compare, which means some constant time, and then to return, which is some constant time, plus time taken to solve n minus 1, t of n minus 1, right? And you should even find out the base condition. Why? Because that is where the function is going to stop. Base condition is when n equal to, let us say 1. When n equal to 1, it is going to return 1, right? Then what did I do? I kept on back substituting. In place of t of n minus 1, I substituted this. In place of t of n minus 2, I substituted this. So we could go on like this, and finally I got the answer to be n. So which is also order of n. Okay, we shall see one more example. Let's see one more example for back substitution. Let us say some algorithm is given, and after converting it to recursive equation, later when we see the algorithms, I'll even show you how to convert it to recursive equation. But for now, just consider that already recursive equation is given, and the recursive equation is like this. Time taken to solve a problem of n instances is, just assume that some n plus t of n minus 1, which means time taken to solve a problem on n instances is n time taken plus time taken to solve remaining n minus 1 elements. The algorithm is run on n minus 1 elements. Let us say this is when n is greater than 1, and that equal to 1 or some constant time. C or constant, it doesn't make any difference. And n when n is equal to 1. Okay. So how to solve it is again the same method. So if I have to substitute this, I should know what is the value of t of n minus 1. In order to find out t of n minus 1, in place of n you substitute n minus 1. So what do I get? In place of n, if I substitute n minus 1 in place of n, then I am going to get, in place of n minus 1 plus in place of n minus 1, which means it is n minus 2. Okay. Now t of n minus 2. Why? Because I got n minus 2. So if I want to find out t of n minus 2, in place of n you substitute n minus 2. Then what do we get? N minus 2 plus t of, in place of n you substitute n minus 2. Then we get t of n minus 3. Right? So let me call this equation 1, this equation 2, and this is equation 3. So keep on substituting the equations with higher numbers in equations with lower numbers. Right? So let us say I want to substitute equation number 2 in equation number 1. Then what do we get? If I substitute 2 in 1, which means already 1 is t of n equal to n plus t of, let me write it here, t of n equal to n plus t of n minus 1. Okay. Now that equal to, in place of n minus 1 I am going to substitute this one, n plus, in place of t of n minus 1, this one, right, n minus 1 plus t of n minus 2. That equal to, in place of n minus 2 I am going to substitute this one, n plus n minus 1 plus, in case of n minus 2, which means this one, n minus 2 plus t of n minus 3. That equal to n plus n minus 1 plus n minus 2 plus so on plus n minus k plus t of n minus k plus 1. How did I write this? Just see. So I am just following the sequence, right? So if it is n minus 3, n minus 2 here, then it is followed by n minus 3. Similarly, if it is n minus k, then it will be followed by n minus k minus 1. So I am just writing it in a sequence. Now when is it going to stop is, we have to eliminate this t completely. I have to write t of n only in terms of n. I don't want to write it in terms of t. How can I eliminate this t? By using the base condition. What is the base condition? T of n equal to 1 when n equal to 1. Which means if this entire term could be made 1, then this entire t could be eliminated. So what I am going to do is n minus k plus 1, this entire term has to be 1. If this entire term has to be 1, then what should be the value of k? That is what I wanted. Then n minus k minus 1 equal to 1. That implies k equal to n minus 2. So for a value of k equal to n minus 2, I'll get here as t of 1 and I could stop it. Therefore I am going to substitute k equal to n minus 2 here. Then what happens? N plus n minus 1 plus n minus 2 plus so on plus, in terms of this k I am going to substitute n minus 2. N minus 2 plus, in terms of k I am going to substitute n minus 2. T of n minus 2 plus 1. Then this entire thing is going to become 1 and this entire thing is going to become 2. So what do we get here? N plus n minus 1 plus n minus 2 plus so on plus 2 plus 1. So 1 plus 2 plus 3 plus so on plus n. Then what is it? N into n plus 1 by 2. Sum of first n natural numbers, right? So this can even be written as, always remember, whenever I have a polynomial of function of like this, n plus k to the power m, then what is the most significant term in this? N power m. So don't worry about the constants. Then we could always write it is order of n power m. Then what is the most significant term in this? It is n square. Therefore I could always write order of n square. So the time complexity for this problem is turned out to be order of n square. How did we get this? By back substitution. Okay, we shall see other method. Now we shall see the next method called recursion tree method. Using this method also we could solve some of the recursive equations, not all, some of them could be solved. So like this, if the problem is like this, the method is this, recursion tree method. Recursion tree method. See, I am going to tell you all the methods available, but then in exam we are going to use a theorem called Master's theorem. But anyways, it is worth knowing that there are all these methods. You might come across some interview questions in this. So assume that the time complexity is T of n equal to 2t of n by 2 plus c, which means in order to solve a problem with n inputs, the time taken will be some constant time plus 2 times, again the problem is going to be reduced to a problem of inputs n by 2, that to 2 times, right? So, or you could think of it like this: if I do a c amount of work, I could produce 2 problems with smaller sets of inputs, and each input size is reduced to n by 2. Okay, and always there should be a anchor condition. So let us say this condition is valid when n is greater than 1, and when n equal to 1, when we touch 1, then it is constant amount of work. Then how could we solve this question is, so t of n, if I do constant amount of work, I can break the problem into 2 smaller problems, each of size n by 2 and n by 2, right? And at this level, if I do constant amount of work at this point, if I do constant amount of work again, I'll be able to break the problem into 2 instances, each of size t of n by 4 and t of n by 4, right? And similarly the same way here. If I do some constant amount of work c, I could break the problem into 2 instances, t of n by 4 and t of n by 4, right? And again at this level, if I do some constant amount of work, we could break the problem into 2 instances, t of n by 8, t of n by 8. The same thing happens here. If I do constant amount of work here c, I could break the problem into 2 instances, t of n by 8 and t of n by 8, right? Same thing will happen here. If I do a constant work, I will be breaking it into t of n by 8 and t of n by 8, and again if I do a constant work like this. Okay, now just observe at every level how much work is done and how long are we going to go. So we are definitely going to stop it whenever we reach t of 1, right? T of 1, t of 1, t of 1. Whenever we reach this t of 1, we are going to stop, right? Now how much work is done at this level? C work. How much work is done, total work, amount of work done in this level? 2 into c. How much total work is done at this level? C plus C plus C plus C, which is 4 into C. Now how much amount of work is done at this level? 8 into C, right? So at the last level, how much work is done? C. When it is t of n by 8, the work done is 8c, isn't it? At the last level, what is it? How can you write it in n by something? If I had to write t of n in n by something, how can I write it? T of 1 is nothing but t of n by n, right? So when it is t of n by 8, the total work done is 8c. When it is t of n by 4, the total work done is 4c. When it is t of n by n, the total work done at this level will be nc, right? So if I add up the total work done, what do we get is c plus 2c plus 4c plus so on plus n into c. So pull out c as common, then what do I get? 1 plus 2 plus 4 plus so on plus n. Now assume that n equal to 2 power k. So it is not going to hurt our result, or it is not going to change anything. Just by assuming that n is a power of 2, we could actually do the answer in a easier way. Simply, it is just a simplification. There is no harm in doing this, in this assumption. Therefore, assuming that n is a power of 2 power k, then I'll get this as a GP, isn't it? GP 1, 2, 4, 8, so on 2 power k, where common difference is 2 and the number of terms are k plus 1. This is 2 power 0, 2 power 1, 2 power 2, so on 2 power k. Therefore, total number of terms is k plus 1 and the common difference is c. Then what is the formula for this? A into, what is A? Initial one, A into R is common difference, 2 power k. K means total number of terms. Here it is k plus 1 minus 1 divided by R minus 1. That equal to C into 2 to the power k plus 1 minus 1. So we have already seen that 2 power k is n. Then what is 2 power k plus 1? 2n. Therefore it is c into 2n minus 1. So that is the time complexity. So time complexity is c into 2n minus 2, which you can also write it as order of n. So that is the time complexity taken by this we got from this equation. Okay, so we shall see one more example using this recursion tree. See this one more example. T of n equal to 2 into t of n by 2 plus n, which means if you do a work of n, work which is proportional to n, if t of n, then the work has to be n. Then we are going to divide the problem into two sub problems, and each problem is of size n by 2. Okay, and this equation is valid when n is greater than 1, and when n equal to 1, the time taken is 1, which means constant amount of time. So let's see the tree method for this. So t of n is, if I do n work, then the problem is going to be divided into two sub problems, each of size n by 2 and n by 2, right? And now what about t of n by 2? T of n by 2 is 2t n by 4 plus n by 2. That is important. See, t of n by 2 is 2t n by 4 plus n by 2. So we are not going to do n work at every node. We are going to do work which is actually equal to this number, which means if it is t of n by 2, we are not going to do n work there. We are going to do only n by 2 work, because we got the equation to be n by 2. Now if I do n by 2 work, then I am going to split the problem into two parts, and first problem is t of n by 4 and t of n by 4, and again this is also same, n by 2 t of n by 4 and t of n by 4, right? And now if I am going to do this one, again n by 4 work has to be done, and n by 4 work has to be done, and n by 4 work has to be done, n by 4 work, so on. We are some way going to reach t of 1, right? So somehow we are going to reach the t of 1 at the last level, right? So at every level, let's see the total amount of work done. So what is the total amount of work done here? N. What is the total amount of work done here? N by 2 plus n by 2, which is n. Here also n by 4 into 4, which is n. So here we will get the number of leaves, n leaves, and every leaf is going to have a work of 1, because t of 1 is 1 and we have n such leaves. Therefore the total work done is n. Now what is the total amount of work is? We have to add all these n's, right? So now the question is, how many such n's are there, or how many levels are there? Let's see how many levels are there. We know that at every level work done is n, then the total work done is n into total number of levels. Now we have to count the total number of levels. Let's see the way in which this the tree is shrinking or tree is growing. Initially it is n. I can write n by 2 power 0, and then it is n by 2 power 1. This is first level, and at second level it is n by 2 power 1, and then it is n by 2 power 2, and then it is n by 2 power 3, so on. We are reaching 1, right? So let us say the last level is n by 2 power k. If we assume that n equal to 2 power k, this is where we are reaching 1. Therefore, how many levels are there? 0, 1, 2, 3, so on k, which means we have k plus 1 levels. If we assume that n is a power of 2, which means n equal to 2 power k, then we had totally 0, 1, 2, 3, so on k, which is nothing but k plus 1 levels. If we have this k plus 1 levels, totally k plus 1 levels, right? So if you are having this k plus 1 levels, then what is k in terms of n? So we already know that k equal to log n. Apply log on both sides, then we get k equal to log n. Now in case of k, if you substitute log n, then the total number of levels is log n plus 1 is the total number of levels, and at every level we have seen that work done is n. Therefore the total work done is n into log n plus 1, out of which the leading term is n into log n. Therefore, the time complexity is n log n. So for this problem, the time complexity is n log n. Now let's see about searching algorithms. So in computer science, a search algorithm is an algorithm that retrieves information stored within some data structure. Now we are going to store the data in some data structure. You can think of either an array or a linked list or a tree, any data structure. Now we want to search for some element, so that is called searching. And data structures can include linked lists or arrays or search trees or hash tables or various other storage methods. Now what we want to do is we want to find, given an element, whether this element is present in this data structure or not. Now why are they useful is there are various applications that you can think of. So one is even in SQL select command. So if you don't know about SQL select command, it is nothing but in a database we are searching for an element. Okay. So let's see what are the various types of search methods we have. Even in search engines also we do search, isn't it? So there are various applications for it. Now in this in this video we shall see only two search methods. One is linear search and the other is binary search. Now the linear search and binary search. First let's discuss about the linear search and then the binary search. So what is the linear search is? The name itself says that we are going in a linear fashion, which means one after the other. So linear search or sequential search is a search for finding a target value within a list, and how it works is we go on checking the elements one by one. See this? It sequentially checks each element of the list for the target value until a match is found or until all the elements have been searched. It works on both sorted and unsorted data. So one thing you should remember is if you go with linear search or sequential search, you can apply it both on the sorted as well as unsorted data. But coming to binary search, you can apply it only on the sorted data. Now let's see how it works. It is a problem statement. Now we are giving the algorithm here. Given a list L of n elements with values or records like this, L0, L1, L2, so on Ln minus 1, and target value t, the following subroutine uses the linear search to find the index of the target element t in L. So what it means is if you have a list of elements, each element is having an index 0 to n minus 1, then given an element t, we have to search in this entire list whether t is present or not. In case if t is present, we are going to return the index of the element where it is present in, right? So let's see the algorithm. Initially we start with the 0th element, that is why set I to 0, and then if Li is equal to t, which means if that particular element Li is equal to the target element, this search can terminate there itself and it can return that I. Otherwise increase I by 1, otherwise we go to the next element, and if I is less than n, then go to the second step, which means we take every element and we keep on checking with t. Wherever we get t, we stop there, otherwise we go to the next element and again we check it, right? So this is what is the algorithm. Let's see a program. This is the implementation of the given algorithm, and here we are going to search for an element in an array. Okay, see this implementation of linear search algorithm in arrays. So the algorithm, the name of this program itself, it is written in C. Okay, the name of the program itself is linear search, and the input is, it is given an array. So see this, the first parameter for this function is array, which means we are sending the address of the array in which the elements are present in, and that address will be captured in ARR. And then we are sending the size of the array, and we are also sending to this program through this function what is the element we have to search for. So target is going to contain it. Let's take an example. Now let us say this is the example we are taking. So this is the array. So ARR is going to point to the beginning of this address, beginning address of this array. Now it has 7, 5, 9, 2, 10, and then size is 5. So what does it mean? The size of this array is 5, and it is also sent to this function, and the target is 2, which means in this array we want to search for the element 2. Okay, so in this array we want to search for the element 2, that is what we are searching for. Now how does this work? For int index equal to 0, which means we are starting from the 0th one, okay, 0th element, and index is less than size. Yes, it is less than size. Now we keep on searching, right? So we see whether this element 7, which is array of index, is equal to target or not. So whether this element 7 is equal to 2 or not. In this case it is not equal. Then what do? Again we go to the next element by doing I++, this index plus plus, and again I check if index is less than size or not. Yes, it is less than size. And now I just check if this particular element is equal to target or not. Here it is not equal, so again I go to the next element, index plus plus, and again I do the same thing. I check whether this element is equal to target or not. So in this case it is not equal. Again I go to the next element, and now again I check if this element is equal to target or not. Yes, this element in this case is equal to target. Then I am going to return index. So what should we return? Here we should return the index as 3. So 3 is returned. Got it? Now let's see the time complexity for this method. Now if you observe it, in best case we'll be able to find out the required element in the one search. So when is it possible? When this particular element is present at the beginning, right? If the element we are searching for is the first element of the array, then we can stop immediately. Then in that case the number of iterations is 1, right? Otherwise, worst case, we will not be able to find the element in the array at all. So we go on searching with the entire array and we don't find it. In that case the number of iterations is going to be n plus 1. Why? N times we search all the elements and n plus 1 time we come out of the iteration, okay, that loop. Therefore in average case, if you see this, if you add these two divided by 2, it is order of n. So average case or the worst case time in this case is order of n. Worst case is order of n, and the average case is also order of n in this case. Now if you want to analyze the time complexity in some other method using the recurrence equations, you can do that. If you are going to search for an element in a list of size n, then you can do some constant time operations like one comparison, and in one comparison you can decide or you can eliminate one number from the entire list, right? See this. Now if n is the total size of the problem, in just one comparison you can decrease the size of the problem by 1. Why? In case if it is not the target element, then we can say that the target element might be in the remaining elements, right? How many elements might be there? N minus 1. So this is how the problem size will keep on decreasing. After every comparison the problem size will decrease by 1. That is why T of n equal to T of n minus 1 plus 1. Now if you solve this recurrence equation, then we are going to get it as order of n. You can solve it, okay? Now let's see how to implement the linear search on a linked list. Now let us say to this function we are passing the head of the linked list, right? Which means the address of the first node of the linked list we are passing to this function as the first argument. Therefore head will point to the first element in the linked list, and target means what is the value you want to search for. So both are passed to this method. Let's see an example here. Now let us say this is the linked list on which we want to search. Now assume that target is passed as 2, which means in this linked list I want to search for 2, and inside this head we are passing the starting address, the address of the first node in the linked list. That is what we are passing to the head. That is why head is pointing to the first element in the linked list. Now we shall first check if head is null or not, okay? If head is null, if head is not null, then only we enter this loop. If head is null, we don't enter this loop, we don't enter this block, if block, we just return. See this. If head is null, then we just don't enter this for loop, if block, we just come out and we just return here. Otherwise if head is not equal to null, we enter the if block. Now once we enter the if block, then we have the while loop. Now let's see what while loop is doing. So here we have entered it because head is not equal to null. Now we are entering the while loop. In the while loop we are testing while head is not equal to null, which means as long as head is not equal to null, we just keep on comparing the data. So head of data equal to target or not, which means this data is equal to this target or not. So it is not equal, therefore again we go to the next element. In order to go to the next element, we are using head equal to head of next, which means whatever earlier head was pointing, now I am just going to the next element, right? Head of next means this element. Now head is made to point to this element. Got it? Okay. And again we shall see, we check whether this is null or not. In case if it is not null, then we try to find what is the value present in it and we compare. So 5 is compared with 2. Head of data is compared with this. So it is not. Now again we go to the next one, right? Again we do the same thing, right? So 9 is compared with 2. Now it is not equal, right? Now again we go to the next element. Again we check if it is null or not. It is not null. Now we compare the data. Yes, in this case head of data, which means this data is equal to this target, and so we have to return this head. So what is returned? The address of the node which is containing the required target is returned, right? Therefore head will be returned here. Okay, now that is what is returned. So this is about all the search. So we have seen the linear search, one in case of array and other in case of linked list. Both of them are going to give the same worst case time, which is order of n. Okay, fine. Now that we have seen the linear search, we found out that the time complexity for linear search is order of n. And in case if the data is present in array and if array is sorted, we can do much better than the linear search. So that is why we are going to see binary search. So binary search is efficient when the data is stored in array, first thing, and second thing, the data has to be sorted. Okay, remember these two. If the data is stored in either linked list or if the data is unsorted in the array, it will not be applied. It is applied only in the case where data is stored in the array and it is sorted. So it is also called as half interval search or logarithmic search. So why is it half interval search? Is at every step we try to decrease the size of the search by half. Search space is nothing but initially the entire array. At after every comparison, we try to decrease the size by half. That is why it is also called half interval search. Now why is it called logarithmic search? Is because the time complexity is going to be a logarithmic time. So that is why it is logarithmic search. Now let's see the algorithm. Okay, so how it works is binary search works on the sorted arrays. It begins by comparing the middle element of the array with the target element. So we don't start from the beginning. We look at the middle element and we see if it is the target that we need. And if it is not the case, if the target element is less than the our middle element, if the target element matches the middle element, then we are done. Otherwise, if the target element is less than the middle element, then what does it mean? The number that we are searching for will be present in the left half, right? So that is where we are going to continue the search in the left half. Otherwise, we keep searching in the right half, right? So let's see the algorithm for it. Now the algorithm is here. So let us say we have we have an array, and this array, the elements, there are n elements and the indices are from 0 to n minus 1. So first you put the left L, you set the L to 0 and R to n minus 1. It is nothing but we are having two pointers. One is pointing to the leftmost element and other is pointing to the rightmost element. Why? As of now, the element could be anywhere in the array. That is why the probable search space is the entire array. Okay. Now we try to find out the middle element. Middle element is nothing but L plus R by 2. Okay. Then we compare the required element with the middle element. So we compare the target element with the middle element. If the middle element happens to be the target that we are searching for, then we simply return that middle element. Okay. Otherwise, we see if the middle element is less or greater. If the target element is greater than the middle element, it means that target element might be present at the right half, right? So in order to search only in the right half, the left pointer will be moved to the middle element plus 1. Otherwise, if target element is less than middle element, then we have to search in the left half. That is where the right pointer will be moved to the middle element minus 1. So with an example, I'll explain you with the program. It will be easy. Now this is the program which we have written. So this is the implementation of the iterative version. You can also write a recursive version. You write it on your own. We are writing it in the iterative version. Now let's take an example and see what happens here. Now for this binary search, the input is given as an array, and to this function the pointer, which means the address of the first element of the array, is passed as the is one of the argument. Therefore we are able to get the starting address of the array, and then we are having the second one is the index, which means from where do you want to start the search from. So it is, let us assume that we want to search the entire array. That is why left index is given as 0 and the right index is given as 9. In case if you want to search only in some part of the array, then you can set the left index and right index appropriately. For example, if you want to search only between 2 and 6, you can do that, right? And then finally we have the target element that we want to search for. Okay, so let us say this is the array which is given and we want to search for the element 23. Then what we should do? So first thing is we try to find out whether left index is less than right index or not, which means these two should always be like this. Left index should always be less than right index, which means left index should be to the left side and right index should be the right side. There should not be any overlapping, right? Crossover. Now we are trying to find out the middle element. So in order to find out the middle element, you could do it two ways. Left index plus right index by 2 you can do. Otherwise left index plus, I'm just trying to find out the entire size of the array by doing right index minus left index and then dividing it by 2. You can follow any logic. Okay, so now we found out the middle element. Here the middle element happened to be the fourth one. Now I am testing if the element which is present in the middle is equal to the target element or not. 16 is not equal to target element, right? Then what should I do? I should check whether this element is greater than this element, right? Now see this, the required element is greater than the middle element, therefore definitely we should continue this search on the right side. So that is why this condition happened to be true, and therefore I am moving the left index from here to here. Why? Now that we know that the required element is greater than 16, there is no chance that the required element will be present anywhere to the left of 16. That is why we should search only in the right half of 16. That is why I am moving the left index to here, right? And the right index is going to be here. Now in this space I want to continue my search, right? And now I have to find out the middle element again. Okay, now next one is find out the middle element. So left is here, right is here, the middle element happened to be this. Now again I check with the target element, right? Now I found out that it is not equal. Middle element and target element is not equal, but middle element is less, the target element is less than the middle element. Therefore I have to continue my search to the left side of this. Already this is all over, discarded, and now only to the left of it I have to search. That is where left index will be present here and the right index has to be moved from here to here. That is what we did. Okay, now again I have to find out the middle element. Now if I find out the middle element between these two, if I do that L plus R by 2, right, or this condition is written in such a way that the base is, the floor is going to be returned. It is a integer division, right? 5 plus 6 by 2 is not going to give you 5.5, it is going to give you 5. That is integer division we used, right? So that is the reason we are again going to search this middle element with this. Okay, now we finally found out that the middle element is equal to the target element, and now we can return its index. So what will be returned? The index of it, 5, will be returned. Got it? So this is how the binary search method works. Okay, now let's see the time complexity of this method. Now you can use the recursive relation method in order to find out the time complexity. So how to understand this is, by doing one comparison you are able to reduce the size of the problem space to half. What I mean by saying this is, just by compute the middle element and then compare your target element with the middle element. Now you need not search the entire space, you have to search either the left half or the right half, right? That is why the number of elements to be searched initially was n, but after comparing with the middle element in constant amount of time, you have to search either in the left half or in the right half. That is why problem size is reduced by half. Initially problem size is n, now the problem size is reduced by half. Got it? That is the meaning of it. Now if you try to analyze it either by Master's method or by back substitution method, you are going to get that the time complexity for this method is going to be order of log n base 2. Okay, fine. Let me explain you the sorting algorithms. Sorting means given any sequence of numbers, so I'm just stating the problem, you must already be knowing about it, but just for the sake of completion. So given any sequence of numbers, you are supposed to put them either in ascending order or descending order. We have various sorting algorithms like iterative versions and then recursive version, and this insertion sort I am showing you here is iterative version. Okay. So this is the sorting. The sorting problem is like this. If I have a number like this, if I have some list like this, right, then what does this sorting algorithm mean is, after the completion of this algorithm, you are supposed to have the numbers in this sequence: 1, 2, 3, 5, 6, 7, 8, 9, and maybe 0. Okay, so this is what we are supposed to see, which means given any random array, random list, then we are supposed to get a output which is either in ascending or descending order, that is sorting. So one simple way is, maybe you can try out one simple possibility. You can find out all the permutations of this, all the permutations, and then in those permutations you can find out what is the permutation which is in ascending order. That is one simple method, right? So but then in order to find out the total permutations of a number containing n numbers, of array containing n numbers, it takes order of n factorial time, which is nothing but, it is in the order of n power n, so which is exponential time. I don't want such exponential time. See, I have already told you that order of 2 power n or order of n power n, these are very costly algorithms and we want to avoid them. So let's see something better here. I'll explain that insertion sort code with this example. Let's see this example first and then I'll explain you what that program is doing. So insertion sort is named in such a way because it is actually similar to playing the cards. So you must be, you must have played the cards, right? Let us say all your cards, the deck of cards, are on the table and all the cards are facing downwards on the table. Then what you do, you take the first card from the top of the table and put it in your left hand side, right? And then you take the second card from the top of the table and you compare it with your card here. If it is lesser, you put it in the left side. If it is greater, you put it in the right side, isn't it? And now let us say in my hand I have 2 cards. Then I'll take the third card and then I compare them from the rightmost to leftmost, which means I'll see the position where the third card has to be inserted, either at the end or in the middle or in the beginning, right? That depends on comparing with one by one. Then I'll insert it. Then in my hand, in my left hand, all the cards are already sorted, right? And I'll take the next card. By the time I pick up the fourth card, the 3 cards in my left hand are already sorted. Now I'll take the fourth card and I'll see the placement. How? By comparing it with cards one by one. That is the same method this insertion sort is going to use. I'll show you this. See this? Now pick up the first card and put it in your left hand side. So this card is already picked up. Okay. Then you pick up the next card. Okay. Next card, which means next card is not here. You have picked it up. 6. Right. And now you compare it with this. Okay. Now is this number greater? Yes. Therefore it has to be moved here and this has to be moved here. Therefore you are going to move 9 here and you are going to place 6 here, right? So after this, 2 cards are in my left hand side and they are sorted, right? Now these 2 cards are in my left hand side. Every number is nothing but a card here. So in my left hand side I have sorted 6 and 9, they are sorted, right? And now I'll see the next one. Now I'm seeing the next one, 5, right? Then I'll compare 5 with 9. Then I'll check what happens. See this, which means I'm picking up 5 and I'm holding it in my right hand side, which means 5 is not here. Now I have picked it up, right? And now I'll compare this card with this card. So what did I find out? That this is greater. So whenever it is greater, I'm going to move it. So 9 will be moved here, making the room for 5. So can I put 5 here? Before putting 5 here, you have to see whether 6 is greater than that. Since 6 is greater, you move 6 here and you place 5 here, right? Let me put all of them in array. they are all in array. Okay, and let us assume that array is starting from 1, 1 2 3 4 5 6 7 8 9. Okay, fine. Now 3 elements are in their right positions, which means the 3 cards in my left hand side are already sorted. Then I'll pick up the 4th card. I picked it up and I'm examining it. Where should I insert it? Then I'll compare this card with this number. Then what I find out, this number has to be moved and made room for 0, right? Which means I'm just moving the cards in my left hand. Then what about this? Again these two are compared. Then what did you find out? This number has to be moved. And again these two are compared. What did you find out? This number has to be moved, right? And finally this number will be placed here, right? Therefore after this all the 4 cards are in their right positions. So observe this, at any time whenever I am examining the 5th card, by that time the first 4 cards are already sorted, right? And whenever I am examining the 6th card, the first 5 cards will be sorted, right? See this. Next one is I'll pick up 8, picked it up, and now I am examining where I should be placing it. I'll compare it with 9. 9 is greater, therefore move it and make room for 8. Therefore I am moving it here, and then I'll check 6 with 8. 6 is lesser, therefore 8 has to be placed here. I'm going to place it here, right? And now next one that has to be picked up is 2. So I'm going to pick up 2, and now I'll check this space. 9 is greater, therefore 9 has to be moved and space has to be made. 8 is greater, therefore 8 has to be moved and place is made. And 6 is greater, therefore 6 has to be moved and place is made. And 5 is greater, 5 has to be moved and space is made, right? And now I'm going to finally put 2 there, right? And by this time all the 6 cards are in their correct positions. Now I'm going to take the 7th card. I picked it up. 7th card happened to be 7. Now 7 and 9 are compared. Then you understood that 9 has to be moved because 9 is greater. 9 will be moved and 7 will be placed. And then 8 and 7 will be compared. 8 is greater, 8 will be moved. 6 and 7 will be compared. 6 is smaller, therefore 7 will be placed here. By this time all these 7 cards are in their right position, right? And similarly next one picked up is 1. Now when you pick up 1, then 9 will be moved here, and 8 will be moved here, 7 will be moved here, 6 will be moved here, 5 will be moved here, 2 will be moved here. Now 1 is greater than 0, therefore 1 will be placed there, right? And finally I'll pick up 3. So when I pick up 3, 9 will be moved here, 8 will be moved here, 7 will be moved here, 6 is moved, 5 is moved. Now 2 is less than 3, therefore 3 will be placed here. So that is how I got all the numbers here, right? 0, 1, 2, 3, 5, 6, 7, 8, 9, right? So that is how the algorithm works. Now how did we trace out the algorithm? We are going to take the cards one by one and examine the cards with the already sorted list, right? Which means the left side. So when we pick up, let us say when I pick up 5, I am going to examine all the remaining cards from 5 to 0, right? Which means from 5 to 1 I am going to examine them from 4 to 1, and if the number is greater I am going to move it. If the number is smaller I am going to fix it there, right? So let's see how this example is working. How this program works. Let me take an example and show you the same example. Let us say, what is the example? 9, 6. Let us say 1, 3. This is the, and let us assume that I have examined till these 4. Once this examination is over, then what will be on top of what will be on the list? It is 0, 5, 6, 9, right? So by the time I reach this number in the algorithm, this entire list would have been sorted, and that number will be 0, 5, 6, 9. 0, 5, 6, 9, right? Then let us say I am examining this, so it is better, it is easier for me to explain like that. Okay, so let me show you the algorithm. Okay, instead of this I will take the original one only. 9, 6, 5, 0. So let me start from the beginning. So look at the algorithm. For j equal to 2 to a dot length, which means you are going to start your j from here. This is 1, this is 2, and till the end. You are going to start it from this point. Why not from this point is, the reason is simple. I need not do anything about the first element. Why? Because first card is already sorted card. If I take the first card, I did not do anything, right? From the second card onwards, I have to compare and I have to move, right? And now key equal to a of j. Key equal to a of j is nothing but picking it up and placing it in somewhere. Key equal to 6. That is what is done. So key is a temporary variable which is used to hold the card or the number for some time. The reason is you might overwrite that number. If you don't do this step, you might, when you move this 9 here, or when you move this, shift this 9 here, you are going to overwrite on that. That is why you are going to pick it up and hold it. And now I equal to j minus 1, which means I is going to start from the left side, whatever is left to j, and from there it is going to start, while I is greater than 0, which means I should not go beyond the number 1, the first element, if a of I is greater than k, which means if this element is greater than this, then a of I plus 1 equal to a of I, which means move it here. This has been moved. That is the meaning of it, right? And then I equal to I minus 1, which means you go next, right? Then what happens? I becomes 0, right? So whenever I becomes 0, what is that you are supposed to do? You are going to stop. Why? The reason is this is going to break. Then a of I plus 1 equal to key 6. That is how it is done, right? Then after this, I started j with 2, right? In this array, let me give the indices and show you. So indices are like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Now this, I started j from here, and now j has been incremented to this point. Now j is this, okay? Then what should I do? J equal to 3. Now key equal to a of j. Therefore inside the key I have to take this. A of j is 5. I picked up, right? Okay. It doesn't mean that the number vanishes from here. Number will be present here, but there is a chance that it might get overwritten. That is why I am storing it in a temporary location. Then I equal to j minus 1, which means I am going to start I from this location. Then while I is greater than 0, yes, I is greater than 0, a of I is greater than key. Is a of I greater than key? Yes, which means there has to be a moving. A of I plus 1 equal to a of I. So you move it here. A of I plus 1 is nothing but a of 3 equal to a of 2. Therefore I moved it. 9 is present here and 9 is present here. What happened is 5 is overwritten. That is why I saved 5 here, right? And now after this, I equal to I minus 1, which means this I will point to the first element. Okay. Then what happens about this? I is greater than 0. Yes, I is greater than 0. And a of I is greater than key. Yes, a of I is greater than key, which means this also has to be moved. Therefore a of I plus 1 equal to a of I, which means 6 will be moved. Then what happens next? I equal to I minus 1, which means I will point to 0. Then while I is greater than 0, is I greater than 0? No. Therefore while loop will break. So once the while loop breaks, you are going to come out and you are going to write a of I plus 1, which means a of 1 equal to 5. That's it. Okay. Now for the next iteration, j will become 4. J is automatically going to increment, right? Now j will become 4. Now see this, key equal to a of j, which means inside the key you are going to write 0, right? And I is going to start with j minus 1. Now you compare this one and this one. It is greater. Therefore a of I plus 1 equal to a of I, which means this will be overwritten with 9. And I will be decremented. I will point to the next element, right? And again 6 will be compared with 0. So therefore what did you find? 6 is greater than 0, therefore 6 will be shifted, and now I will be decremented. Now what happens? 5 is compared with 0, 5 is greater, therefore 5 will be shifted, right? And again I will be decremented. I is here. Now I is not greater than 0, therefore while loop will break. Then a of I plus 1, which means this point equal to key. A of I plus 1 equal to key. So that is how this algorithm works. So how is it working? Now j is moving from 2 to n slowly, right? And whenever j is going to j is going to be at some point, then I is going to compare with all the elements, right? And the comparison is going to stop whenever we find the correct location, right? So now in worst case, let us see how many comparisons and how many movements are required here. In worst case, if j equal to 2, which means if I am examining the second element, then what happens? I might have to examine it with the first element. Therefore, how many comparisons are required? For j equal to 2, number of comparisons required are 1 and the number of movements required are 1 in worst case, right? Therefore, 2. If j equal to 3, then how many comparisons and how many movements are required is, if I am standing at this point, I am talking about the worst case, okay? So what is the worst case input is? Input is reverse sorted order, that is the worst case input. If j equal to 3, then I have to compare with these two elements, therefore number of comparisons required are 2, and moreover I might have to move these two elements forward, number of movements required are 2, which means I might have to do 4 operations, 2 comparisons and 2 movements, right? And when j equal to 4, I might have to compare with these three comparisons, and then I might have to move these 3 elements one forward, which means 3 movements, which means 6, right? When j equal to 5, I might have to do 4 comparisons and 4 movements, which means 8, right? Therefore you can understand, you can observe one pattern in this. So the pattern is, when j equal to n, then I might have to do n minus 1 comparisons and n minus 1 movements, right? Therefore that is going to be 2 into n minus 1, right? So this is nothing but 2 into 4, this is nothing but 2 into 3, nothing but 2 into 2, this is nothing but 2 into 1. Therefore what is the total time complexity taken in the worst cases? For j equal to 2, the total number of comparisons and movements required are 2 into 1. For j equal to 3, the total number of comparisons and movements required are 2 into 2. So on. For j equal to n, the total number of comparisons and movements required are 2 into n minus 1 in worst case, right? Therefore, if I pull out 2 as common, the total time required is, in terms of operations, 1 plus 2 plus so on plus n minus 1. That is nothing but sum of first n minus 1 natural numbers. So what is it? 2 into n minus 1 into n by 2, right? So that is nothing but order of n square. So in worst case, the time complexity required in order to solve this question is order of n square. Then what is the best case? The best case time complexity comes, see, this worst case time complexity comes when the input is reverse sorted, which means every element I have to insert into the sorted list happens to be the first element. That is nothing but reverse sorted order. I'll just show you that input. When does this thing happens is when the entire input is in reverse sorted order. 9, 8, 7, 6, 5, 4, 3, 2, 1, right? So if I pick this element up, I have to move, compare with this and move this, isn't it? So for this one comparison, 1 movement are required. Then I'll get 8, 9. Now if I pick this element up, I have to compare with this, move this, compare with this, move this, right? Then I get 7, 8, 9. If I pick this element up, then I have to compare with this, move this, compare with this, move this. All of them have to be moved, and then this has to be inserted in the beginning, isn't it? If I pick this element up, all of them have to be moved, and then this has to be inserted in the beginning, right? And again the same thing, all of them have to be moved and then inserted to the beginning. That is why if I have to insert the second element, the number of movements are actually 1 comparison and 1 movement. That is why I got order of n square. Then what is the best case input? The best case input for this algorithm is already sorted list, which means if I have the list as 1, 2, 3, 4, 5, 6, 7, 8, 9 like this, then if I pick up this element, with just one comparison I will find out that it is its actual position, which means for j equal to 2, number of comparisons required are 1 and number of movements nothing, right? And for j equal to 3, I'll pick it up and I'll find out that the element is lesser than this, therefore it is the right position, which means one comparison. With just one comparison I'll find out that they are in the right position, isn't it? Then what happens, for all the n-1 elements I need n-1 comparisons and 0 movements, right? Therefore the best case complexity is order of this omega of n. So always we write the best case complexity as omega of n, which means you cannot execute this algorithm with any time lesser than this, and this is the worst case time required to execute the algorithm. That is how we can analyze this. What about the space complexity? Apart from a, which is given in the input, we need only one more variable. I think we need 3 variables. One is key to temporarily save that card, that number, and other is I, and other is j. So whatever is the size of the input, I always need only 3 variables. Therefore the total space complexity is order of 1 or constant time, right? So whenever we don't need any extra space, or whenever we need only constant time, constant space to sort any given list, such a sorting algorithm is also called as in place. In place means we are not taking any extra space to sort the algorithm. Whatever array is given, we are doing it within that place. That is why it is also called as in place algorithm. So insertion sort is called in place algorithm, and the worst case time complexity is order of n square, and the best case time complexity is omega of n. So the best case input is already sorted list, and the worst case input is reverse sorted list, and average case it will be nearly order of n square. Okay, so insertion sort, we have seen that the time complexity depends on 2 things. One is number of comparisons involved, and the other is number of movements involved, right? So one is number of comparisons and other is number of movements. Movements means you are shifting the elements in order to make the room. Now how can I decrease the number of comparisons, or how can I decrease the number of movements? So if you observe one thing, in insertion sort, always whenever we are examining an element j, the entire list before it is going to be sorted, right? And in order to find out the position of j in this sorted list, actually I am doing a linear search. That is why it is taking order of n time, isn't it? But what if I apply binary search on this? If I apply binary search on this, then the total number of comparisons required to find out the actual position for this jth element might fall down to order of log n. So binary search takes order of log n time. I'll talk about binary search later, but just understand that instead of linear search, which means instead of going one element like that, if I apply binary search, because this list is already sorted, by the time I reach this point, my algorithm is guaranteeing that all the elements before it are already sorted. So if I apply the binary search on this, maybe I can reduce the number of comparisons to order of n, order of log n, right? So is this going to increase, improve the time complexity? I don't think that it is going to improve the time complexity. The reason is, even the number of comparisons are smaller, you have to move the records. After finding out the position, you have to move all the records, and for movement it is going to be order of n. So even if I use binary search instead of linear search, the number of comparisons could be reduced to order of log n, true, but the number of movements, which means in order to, after finding out the location of the element, I have to move the elements, right? The number of movements is going to take order of n time. Therefore finally it is going to take order of n itself, isn't it, in order to search an element inside the list, right, and place it. So for every searching and placing, it is going to take order of n time, and I have to do it nearly n-1 times, right? therefore it is going to be order of n square. Then what is the other one? Let us say I want to decrease the number of movements. If I don't want to move, if I don't want to do any movements, then obviously we need linked list. Since this is an array, I have to move the elements and put it in the exact location, right? So if I don't want to do, then I can go with a linked list. So which linked list is better? Double linked list. If I use a double linked list, then movements can be reduced, which means number of movements need not be anything. I need not move anything. Directly I can insert an element in constant time, fine. But then I will not be able to apply binary search on it. So using this, I might have to apply linear search, right? So either I use a double linked list, right? What is double linked list is? It will be like this. All the elements are not present inside the, right? Now let us say the elements are sorted 9, 5, 1, 2, and now I have to next element is 4. If I have to insert this 4, I could directly insert it here without moving all of them. How? Just by just by taking this element and then pointing it to this and then pointing it to this. That's it. So in constant time I can insert the elements, but then in order to find its location, in order to find out that it actually belongs here, I have to compare with all these n-1 elements, right? Therefore, even though I use double linked list, the number of movements could be reduced, but the search time is going to be order of n. Therefore, anyway, for searching its location and placing it there, the time taken is going to be order of n. So the time complexity of insertion sort cannot be improved either by using binary search, the reason is movements are going to be more, or by using double linked list. The reason is I cannot apply binary search on double linked list, I have to apply linear search. So whatever it is, in order to find out the correct location of the element, the time taken is going to be order of n, and there are n-1 such elements. Therefore the total time complexity is going to be order of n square only, and the space complexity is order of 1. The reason is only constant amount of space is required, and the algorithm is also called as in-place algorithm. I mean, this algorithm belongs to the class of algorithms called in-space algorithm. So you don't need extra space. Within the same space you could actually sort it. Okay, fine. Next we shall see merge sort. Now we shall look at merge sort. It is also a sorting algorithm, and merge sort is better compared to the insertion sort, and it is even sometimes better compared to the quick sort. So merge sort is supposed to be good in terms of the time complexity. So before going to discuss about merge sort, the heart of the merge sort is a procedure called merging. So let me talk about merging. Entire merge sort depends on a procedure called merging. Let me talk about merging first, and then I'll talk about merge sort. Okay, so just to explain you what merging is, if input is given in an array such that some part of the array is let us say the array is containing like this 1, 5, 7, 8, and the other array and the other part of the array is containing 2, 4, 6, 9. Okay, so now in this array let us say indexes are like this 1, 2, 3, 4, 5, 6, 7, 8. Okay, in this array 1 to 4 are sorted and 5 to 8 are sorted. Okay, listen to this. Now 1 to 4 are sorted and 5 to 8 are sorted. Now what I want to do is I want to sort these two lists. Actually this array is containing two lists. One part is from 1 to 4 and other part is from 5 to 8, right? Now we contain two lists. Now these two lists are already sorted. Now the result has to be again a sorted list which contains all the elements. So how does this algorithm work is, whenever any array is given A in such a way that from P to Q it is sorted, and from Q plus 1 to R it is sorted. That is how P to Q and then Q plus 1 to R. If these two lists are sorted, now I want to merge them into a single list which is sorted. So how does this algorithm work is, first I'll create a new list called L. which will have exactly the number of elements from P to Q. Its size should be exactly P to Q plus 1, which means 1, 2, 3, 4 plus 1, 5, right? That is what is we are doing. So now 5 elements will be there in this cell, and again I will create one more list called R. And in this also, how many elements are there from Q to R plus 1, which means here there are 4 elements, therefore 5. 1, 2, 3, 4, 5. So what is the first step? They are giving you a list which contains a sorted list and a sorted list in an array. Now we are creating two separate arrays. One array is containing the first, one array size is exactly the size of the first list plus 1, and the other array size is exactly the size of the second list plus 1, right? And the next step is you copy all of them, all the one list from to L and other list to R. So in order to copy one list to L, I will copy this 1, 5, 7, 8, and the other list is 2, 4, 6, 9. So how much time does it take for you to copy the elements? It is nothing but order of n. If there are totally n elements, then to copy them the time taken is order of n. Fine. Then the next step is at the end of every list you write infinity. So infinity is practically infinity is not possible, but then by saying infinity I mean you put a very large number, okay, whatever is possible by the data structure which is used to hold these numbers. And next thing is, into this list, this one, we are going to copy everything, which means into the list A, into the array A, 1, 2, 3, 4, 5, 6, 7, 8. So all the elements are already present. I am going to overwrite it. So into this element 1, 2, 3, 4, 5, 6, 7, 8, into the same array A, the given array, I am going to write all these elements in the sorted list. So what I do is, I'll take a pointer, let's say 2 pointers, one is called I and other is called J, right? And then I'll take a pointer K here, right? Now I indicates the element that you are examining in the left list, J indicates the element that you are examining in the right list, and K indicates the element that has to be filled in the array, right? The given array. Now I'll compare this left list element I and right list element J. Whichever is lesser, I am going to write it into the array, okay? And I'll increment it. Since this is already written, I am going to increment this, and anyways K is going to be incremented to this. Now K is going to point to second one. Then again I compare these two, right? List, left list and right list, the corresponding elements 2 and 5, which is less, 2 is less, therefore I am going to write 2 here and I am going to increment it. And again these two elements are going to be compared. So which is lesser? 4 is lesser. I am going to write 4 here and again increment it, right? And now 4 has to be incremented, right? Then 5 and 6 are compared. Which is lesser? 5 is lesser. Therefore write 5 here and you increment it, right? And now 7 and 6 are compared. Which is lesser? 6 is lesser. Write 6 here and you increment it. Then 7 and 9 are compared. Which is less? 7 is lesser. Write 7 here and you increment it. Then 8 and 9 are compared. Which is lesser? 8 is lesser. 8, write 8 here and then you increment it. Now infinity and 9 are compared. Which is lesser? 9 is lesser. Write here and stop it. So that is the entire algorithm. So what is the algorithm going to do? This merge procedure. The merge procedure is going to take the entire list and it is going to create two lists. So in one list I am going to copy the first ordered list, first sorted list, and in the second list I am going to compare the second sorted list. And now after copying them, I am going to write everything back into the original list in such a way that the entire list will now be sorted. If you check this, it is sorted, right? So just I'll explain you the code here. First of all, A, P, Q, R. So merge is going to get an array A in which it is going to get 3 pointers. One is P, one is Q, one is R. This P represents from P to Q it is sorted, and from Q plus 1 to R it is sorted. That is what PQR represent, okay? And now you just count how many elements are there in the first list. The number of elements in the first list are these many, Q minus P plus 1. q minus p plus 1, and the second element contains, and the second list contains r minus p. So these are the number of elements in the first list and the second list. And now you create two lists. So I am going to create two arrays, one array by name L and one array by name R, in such a way that these lists are able to accommodate how many ever number of elements are there in the first list plus 1, and how many ever number of elements are there in the second list plus 1, right? So why that plus 1 space is reserved, so that I could put the infinities at the end, right? And now this for loop is used to copy the first list into the left array, and this for loop is used to copy the second list into the right array. Therefore I am going to copy the first list and second list into the arrays, right? And the last element is filled with infinity. The last element is filled with infinity, right? And then I start comparing. So I'll start with I equal to 1, j equal to 1, which means I start with this pointer 1 and this pointer 1. And now for k equal to p to r, which means for k equal to p to r, so p to q and q to r, which means the entire elements. I am just seeing, comparing between left and right, which one is less. Let us say if the left element is less, I am going to write it down, right, and then increment it. If the left element is less, then I am going to copy that left element into the array and increment the left side pointer. If the right element is less, I am going to copy the right element into the array and increment the right pointer. Anyways, you have to increment, yes, k is going to be incremented at every step. Understand this? So I am going to compare these two elements, whichever is lesser I am going to write it and then increment it. K is how we are going to be incremented, and next time I am going to do this, right? So what is the total time complexity for this is, first of all, in order to copy these two lists into these new lists, the time taken is order of n, right? And how many copies and how many comparisons are required is, understand this, if the total number of elements in the array are n, then in order to write one element into the array, I have to do one comparison. Therefore, if there are n elements, then I have to do n comparisons, plus every element after compared, one of it has to be written down. Therefore, there have to be n element comparisons and n copies. So again it is going to be order of n, right? So first thing is, for copying the elements into two different lists, time taken is order of n, and then for copying the elements from the two different lists again back to the given array, it is going to take order of n. Therefore the total time complexity required by this merge sort is order of n, right? That is the heart of the algorithm. So the questions on this might be, given two lists, two sorted lists, one list is of size n and other list is of size m, how much time does it take to merge them into one sorted list, right? So what will be the size of the final list? Size of the final list will be n plus m, right? So n plus 1 elements have to be written from here to here. So for writing one element into this, I need one comparison and one movement. Therefore total number of comparisons and movements required is order of n plus m. And one more thing is, remember that if they are giving you this n elements in one list and m elements in other list, you have to have space, extra space, which is equal to n plus m. Okay, so time complexity is going to be whatever is the size of the input given, which is nothing but order of n, but the space complexity required is whatever is the size of the input given, we are again creating nearly elements of that much size, isn't it? So the space complexity required is order of n and the time complexity required is order of n. The reason is, whatever the elements are given, input is given in this array, I am again writing all the elements into two lists, and these two sizes are nearly equal to n. Therefore, in order to solve this problem, I need exactly, at least order of n size, extra size. So this merge procedure is also called out of place procedure. The reason is, we are copying all the elements out of their places and then solving them, right? So you might get a doubt, why are we adding infinity at the end? I'll just explain you. If you understood this, the time complexity is order of n and space complexity is order of n. Now I'll explain you why should we add the infinity at the end. I'll take some other example and I'll explain you that. Let's say one list is, or the given array is like this. One, two, three, four, or given array contains 10, 20, 30, 40, and then the next elements are 1, 5, 6, 9. Okay, and this is A, and P is the beginning of one sorted list, and Q is the ending of that sorted list, and Q plus 1 is the beginning of next sorted list, and R is the ending of it, right? Now this means that from P to Q I have one list which is sorted, and from Q plus 1 to R I have other list which is sorted. Now what is the size of one list? 4. Therefore you have to create an array which is of size 5. 1, 2, 3, 4, 1, 2, 3, 4, 5, right? And I'm going to copy 10, 20, 30, 40 in this, and in the fifth element I'm going to copy infinity. Now I'll tell you why this infinity is used. And now in the other one, 1, 5, 6, 9, and now infinity is added at the end, right? So now you will start with I here and J here, and let us say this is the array A itself, 1, 2, 3, 4, 5, 6, 7, array A itself. Whichever is lesser I am going to write here, which is lesser? 1, right? And which is less, now 1 will be incremented, and now which is lesser? 5, this will be incremented. Which is lesser? 6, this will be incremented. Which is lesser? 9, this will be incremented, right? Now you are going to see that one entire list has been copied here, and the other list is still there. If this other list has to be copied onto this element and onto this list, that is why I have to have infinity at the end. Finally infinity will be compared with 10. So this having infinity at the end will ensure that if one list is over, then the other list will automatically get copied onto the A, right? Now by comparing infinity with 10, obviously 10 will be copied, and now comparing 20 with infinity, 20 will be copied. Comparing 30 with infinity, 30 will be copied. 40 with infinity, 40 will be copied, right? Now by having infinities at the end without doing any modifications to the code, if one of the list is over, other list will automatically be copied. You need not check if one list is over, then you have to copy the other list and all. This just to simplify the matters. If you don't like having this infinity at the end, maybe you might have to just change the code in such a way that you have to check if one list is over. If that is the case, you have to copy the remaining list completely. That is the only reason why infinity is added. Anyway, the important point is, for merging two lists, if extra space is given, then only the time complexity is going to be order of n. If extra space is not given, then the time complexity might increase, right? If extra space is not given, then you might have to apply some other sorting method. Merging method might not work. Therefore merging method needs, if the input is given in n numbers, then we need an extra space. Then in order to copy all the elements from the given list to the next list, we have to have order of n time, and the space complexity is order of n. Okay, now we shall see how to use this merge method in order to sort the entire array. Okay, that is called merge sorting. We shall see it now. So we have already seen the merge procedure, how to merge two sorted lists into one single list. Now we shall see merge sort. Okay, so what is this merge sort algorithm is? It actually falls in a category called divide and conquer. So divide and conquer means, if I have any problem of size n, divide and conquer says that you divide the problem into two sub problems, okay, or any number of sub problems, and then you solve the sub problems first, and then you combine the solution. Okay, the same thing is what is merge sort is going to do. In merge sort also, in order to sort a list of size n, or in order to sort an array of size n, it is going to divide the array into two halves, and it is going to sort the first half first, and then the second half, and then it is going to merge the solution, okay, into the final answer. So that is how merge sort is going to work. So merge sort, given an array A, which we have to sort elements from P to R, then we are going to find the midpoint, and now we are going to sort the array from the starting element P to the midpoint, and then from that next to that midpoint to the end, which means we are going to find out the midpoint first, we are going to sort it from there to there, and then from the midpoint to the next one, and then we are going to merge it. So instead of talking about the algorithm, explaining the algorithm, I'll better take a example and I'll explain you. I'll take an example of small size. Let us say I have an array of size 6, right? And merge sort is different and merge is different. See this, merge sort is going to call, one is merge sort procedure and merge sort procedure, and the other one is merge procedure, and all this this merge sort and merge both are different. So let's say I have 6 elements like this. 6 elements are okay, these 6 elements, and now I have to sort them, and all these 6 elements are present in an array called A, and they are numbered, and the indices are from 1 to n. Let us say this is 1 2 3 4 5 6. Okay, now this array is present like this. Then how does the merge procedure work is, merge sort work is, so in order to sort from 1 to 6, I have to call merge sort on A. A is already implied, therefore I am not going to write A. I am going to call it from first element to sixth element. Okay, then what is happening is, see, every function call is going to call 3 functions, therefore I am going to write a tree with three children. Okay, and now what are the 3 children? First one is merge sort is going to call, first it is going to find out the middle. So what is the mid value for 1 and 6? 1 plus 6 by 2 is 3.5, and if I take the floor it is going to be 3. Why? The midpoint of 1 plus 6 is 1 plus 6 by 2, it is 3.5, and if I take the floor it is going to be 3. Therefore I am going to apply merge sort from 1 to midpoint, which is 3, and then I am going to apply merge sort from 4 to 6, the remaining elements. And then what is the next one? Once this list is sorted and once this list is sorted, I got 2 sorted lists and I am going to merge them, right? Therefore it is going to be merge of 1 to 3 and then 6, 4 to 6, right? So all the merge sort I am going to write as MS. MS means this merge sort calling, and M means merge procedure calling. And what does this one do? This one will also call 3 sub functions, right? So what are the functions? One is it has to merge 3 functions. What are the 3 functions? One is it has to find out the midpoint. What is the midpoint of 1 and 3? 1 plus 3 by 2, which is nothing but 2. Then merge sort of 1 comma 2, and then merge sort of 3 comma 3. So from 1 to 3, if I sort 1 comma 2, then what is remaining? Only 3, third element, that is why that one. And then finally whatever result we get, we have to merge, right? We have to merge these two, which means I have to merge from 1 to 2 and then 3, isn't it? 1 to 2 is sorted and then 3 to 3 is sorted, that is why I have to merge them. Then what about this? Again find the midpoint, right? So how can I find the midpoint? Merge sort of, what is the midpoint of 1 and 2? 1 plus 2 by 2, which is nothing but 3 by 2, which is 1, right? So merge sort of 1 comma 1, and then merge sort of 2 comma 2, and then you have to merge list from 1 to 1 with 2 to 2. That is why I am calling this. And what about this one? This merge is fine, merge is not going to call anything. Now what about this one? Find out the midpoint. What is the midpoint? 4 plus 6 by 2, which is nothing but 5, which means I have to merge sort of 4 comma 5, and then I have to apply merge sort on 6 comma 6, isn't it? Why? Because it is already over. then the 4 to 5 is sorted and then 6 to 6 is sorted. Therefore you have to simply merge them. I have to merge 4 to 5 with 6, isn't it? I have to merge the list from 4 to 5 and then 6 to 6. So you can see how am I writing these numbers from that algorithm, right? And then what about this? I have to merge, I have to apply merge sort on 4 comma 4, and then I have to apply merge sort on 5 comma 5, and then I have to merge 4 to 4 and 5 to 5, right? So now you just see how I got all this. Every merge sort is going to call 3 sub functions. That is why I am going to have for every merge sort 3 callings, but then merge is not going to call anything else, therefore merge is going to end. And what about this 1 1 2 2 3 3 4 4 5 5 6 6 is whenever p is less than r, then only we are going to do this. But in this case p is equal to r, p equal to 1, q equal to r, right? P and R both are equal. P and R both are equal. Therefore, this is where you are supposed to stop. Only if P is less than R, which means if 1 is less than 2, we go for the calling. If P equal to R, we are not going to call anything else. Therefore, they are going to halt here, right? So, merge procedure is going to halt wherever, whenever it is, called. But then merge sort is going to halt only when P equal to R. That is why merge sort is going to halt at 1 1 2 2 3 3 4 4 5 5 6 6, right? Now let's see what happens. Then what is the order in which all these functions will be called is just traverse it top down, left to right. I am traversing like this, which means they are saying that I have to apply merge sort on 1 to 6 elements, right? So let us say all these 6 elements are these, right? 9 6 5 0 8 2. Let us say these are the elements. Now 1 to 6 elements are these. It is saying that I have to sort all the 1 to 6 elements. In order to sort 1 to 6 elements, it is calling sort 1 to 3, which means you have to sort these 3 first. So it is just saying that by the time I finish this, I'll be able to sort 1 2 3. But then this is the first time you are visiting it, which means the function is just now called. The function is not yet done. Now this function is calling merge sort of 1 comma 2, which means it is saying that in order to sort this, you have to sort these 2. And now this function is saying merge sort of 1 comma 1, which means in order to sort this, you have to sort this first element 9, and it is done. It is done, right? Why? This is the last time I am saying it. Whenever I am saying a note for the last time, you can think that that computation of the function is over. Now the computation of 1 comma 1 is over. It means the list which is containing first element is already sorted. Then we are going to go to the next function, which means it is calling 2 comma 2, this one, this element, right? And by the time I finish it, it means that it has already sorted the list which is containing the element 2 comma 2, which means 6. Therefore, by the time I reach here, there are 2 lists. One list contains the first element and the other list contains the second element, and both of those lists are already sorted. The reason is merge sort is supposed to sort them. So, and moreover, every list which is containing one element is already sorted. So by the time I reach here, I have 2 lists which are sorted. And now I am calling merge. This merge is called to sort the list from 1 to 1 with the list 2 to 2, which means this is supposed to sort, or this is supposed to merge these 2 numbers. If I merge these 2, what do I get? 6 comma 9, right? So by the time I reach here, it means that I am going to merge 6 and 9. I am going to get 6 comma 9. And this is the last time I am going to visit 1 comma 2, merge sort of 1 comma 2, which means by the time I reach here, the array from 1 to 2 is already sorted, which means the array from 1 to 2, which was containing 9 comma 6 elements, is now sorted as 6 comma 9. That is the meaning of it. And now this one is saying merge sort of 3 comma 3, which means you apply sorting on 3 comma 3. So any list containing only one element is already sorted, right? That is why it is not doing any work. By the time I finish this, which means by the time I leave it, it is already sorted. Then by the time I reach this, see this, one list from 1 to 2 is already sorted and other list from 3 to 3 is already sorted, and now this merge is saying that you merge 1 to 2 list with 3 to 3 list, which means you merge 1 to 2 list with 3 to 3 list. That is the meaning of it. This function means you merge 1 to 2, which is already sorted, with 3 to 3. So if I merge these two, what do I get is 6 will be compared with 5, therefore 5, and then remaining list 6 comma 9, right? So by the time I finish merging, this is the list I got. So therefore by the time I reach here, I am visiting the merge sort of 1 comma 3 for the last time. What is the meaning of it? It means that the list containing 1 to 3 elements inside the list from the indices 1 to 3, they are already sorted. Listen to this, see this. Now the list containing 1 to 3 elements, they are already been sorted, isn't it? Initially it was containing 9, 6, 5, but now they contain 5, 6, 9. Therefore by the time I leave this, I got a list which is from 1 to 3, which is already sorted. Now I am hitting this, right? I am just starting here at this point, which means now I'm here, which means I'm about to sort the array from 4 to 6. I didn't sort it yet, I'm just about to sort. So it means that I have to sort the array 4 to 6, right? And this is calling the function 4 to 5, which means in order to sort the elements from 4 to 6, you have to sort the elements from 4 to 5, right? And now this is calling the function merge sort 4 comma 4, which means in order to sort this 4 to 5, we have to sort the 4 comma 4. That is the meaning of it, okay? And now we hit the next element. This element is saying that in order to sort, we have to sort 5 to 5, which means this element. By the time I reach here, I have already seen the list containing 4 to 4 and I sorted it. Why? Because it is only single element, that is why nothing to be done, but it is already sorted. And by the time I reach here, it means that I have already seen the element 5 to 5, which is also sorted. Now I'm seeing the merge procedure. Merge procedure is saying that 4 to 4 is already sorted and 5 to 5 is already sorted. You merge those two, which means these two. 4 to 4 and 5 to 5, they are already sorted, we have to merge. If I merge these two, what do I get? So 0 will be compared against 8 and 0 will be written, and then 8, right? So therefore 4 comma 5, I get a list of 4 comma 5 which is sorted. I am leaving this merge sort of 4 comma 5. At this point I will be sure that the list containing 4 comma 5 is already sorted, right? And now I am seeing merge sort of 6 comma 6, which means we have to sort this element 6 comma 6. Since it is a single element, is already sorted list, right? And now by the time I hit this, it is merging 4 to 5, which means 4 to 5 along with 6 to 6, which means this one. So these two lists have to be merged. That is the meaning of it. How can I merge them? Which one is lesser? 0 is lesser, and then which is lesser? 2, and then which is less? 8, right? So by this merge procedure, I got this 0 to 8 list. Now by the time I reach this, right? So what is it? Merge sort of 4 comma 6. By the time I reach this, I'll be sure that the list containing 4, 5, 6 is already sorted as 0 to 8, isn't it? The list is sorted. And by the time I reach this, the list 1 to 3 is sorted, right? Now we have two lists. This merge is given the task that, see, from 1 to 3 it is already sorted, from 1 to 3 it is already sorted, and from 4 to 6 it is already sorted. Now we have to merge these two, right? Which means this function, it has to merge 1 to 3 with 4 to 6. How will it merge it? Comparing the first two elements, which one is lesser? 0, therefore 0 will be copied, right? And then comparing first two elements, which one is lesser? 2 will be copied, and then 5 and 8 are compared, which one is lesser? 5, therefore 5 will be copied, and then 5 is copied, and then 6 and 8, 6 will be copied, and then 8 and 9, 8 will be copied, and finally 9, right? So this is going to merge it all. Finally, when I visit merge sort of 1 comma 6, at this point I can be sure that the entire array starting from 1 ending at 6 is already been sorted, right? So this is how this merge sort is going to work. So in fact, if you observe it, how it is going to work is, the basics is this: it is going to divide the array until we are going to get the smallest list. The smallest list is nothing but list containing single element, and moreover any list containing one element is already sorted, right? And now we are taking two such lists and we are merging them. So it is nothing but dividing the entire problem into such a small problem that every problem will contain only one element, and one element list is already sorted. We take two such sorted lists and we apply the merge, right? And the merge is the actual procedure which is doing some work here, right? And merge sort procedure is simply used to divide the problem, right? And now this is how we trace out the example and see it. Now I want to find out the space complexity. What is the space required by this? So extra space is required, yes. So no, don't worry about this P, Q and R. They are constant time. Extra time is required for merging. Why? In order to merge two lists, I need to create a different list and then I have to copy into it, right? Therefore, every merge procedure is going to take extra space. But then if you observe it, whenever I am working on one merge procedure, I don't need to work on the other merge procedure simultaneously. Therefore, if I create a global array, one global array which is containing n elements, I can use this rough space whenever required. So just by creating one more array, all the merge procedures can be made to refer to this by creating it globally, right? So the extra space required by the merge is going to be order of n, that is for sure. But then what is the other extra space required is for the function calling for recursion, which means inside the recursion stack, how much extra work or how much extra space do we need? In order to analyze this, first thing is we have to find out what is the total number of function calls made and what is the order in which they are made and what is the total height of the stack we needed, right? So if you see this, how many function calls are made is, I am just writing them. So first function call made is this one, and the second function call made is this one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so totally 16 function calls are required, and these function calls are made in the order I have shown you. So according to the numbers, right? So if there are 16 function calls required, then do we really need a stack which has a depth or height of 16, which means should I push all these activation records of the function calls one upon other so that the stack height becomes 16? It turns out that the height of the stack required by the recursion stack is actually equal to the height of the tree or the number of levels in the tree. See this? In this level, first level, we have only one function call. Therefore, in this stack, in one level, I need only one, this one function call will be pushed onto the stack. Okay, I'll take this stack and I'll show you. See this, what happens is, initially, function number 1 will be called, therefore, its activation record will be pushed here. And then function number 2 will be called, therefore, its activation record is pushed here, 2 is pushed. And then 3 is called, 3 is pushed, 4 is called, 4 is pushed, right? And now at this point 4 is over, therefore 4 will be popped off, right? And now 5 will be called, therefore 5 will be pushed onto the same space into the same cell where 4 was sitting previously, isn't it? And now at this point 5 is over, 5 is popped, and next 6 will be called and 6 will be sitting in the same cell where previously 5 was sitting, isn't it? And now at this point 6 will be popped off, and at this point 3 will be popped off. Why? It is the last time you are visiting a node. See, whenever you visit a node for the last time, remember that it has to be popped. If you are not following this, please go back to the example where I have shown you how to analyze the space complexity required by a recursive function. Okay. Now here, by this time, 3 will be popped off. Why? Because it is visited for the last time, right? And now 7 will be pushed. Now what is the least level, what is the least available level? This one only, right? Which means 7 will be pushed into this, right? And now at this time 7 is popped. Why? It is visited for the last time. And now 8 is pushed, 8 is visited, right? And at this point 8 is popped, right? Just observe here, 3, 7 and 8, they all occupy the same cell, one after the other, isn't it? Why? Because they are in the same level, 3, 7 and 8, and moreover 4, 5 and 6, they all occupy the same cell. The reason is they are at the same level. Therefore all the functions which are in the same level will occupy the same cell. Therefore number of cells required in the stack, that actually depends on the number of levels we have in the tree, right? Fine. Now 8 is over, then we are going to see 2, right? So by the time I reach here, 2 is going to be over, 2 is over, right? Then now you will reach 9. So what is the least available cell here? 9 will be pushed here. Now see this, 2 and 9 are pushed, are occupying the same cell. The reason is because they are in the same level. 9 is over, no, 9 is not yet over. Now 10 will be pushed, next available level is this, and then 11 will be pushed, 11 will be pushed here, right? And at this point 11 is over, 11 is popped off, and then 12 is pushed, and then at this point 12 is over, 12 is popped off, and 13 is pushed, and at this point 13 is over, 13 is popped off, and now at this point 10 is popped off, and at this point 14 is pushed, 14 will be pushed here, and now at this point 14 is over, 14 will be popped, and 15 is pushed, right? And now at this point 15 is over, and at this point 9 is over, isn't it? Now see this, 3, 7, 8, 10, 14, 15, 3, 7, 8, 10, 14, 15. These are all the function calls that are at the level 3. Therefore at this cell 3 we have all those function activation records, right? Activation records are records are nothing but for every function call we push a activation record, that is also called as activation record. Okay. Now at this point 9 is popped off, and then 16 will be pushed, right? And at this point 16 will be popped off, right? And finally 1 will be popped off. See this, at level 1 how many function calls we have? Only one function call. Therefore inside this stack at the cell number 1 we have only one function which is continuously occupying this space, which is 1. And then at level 2 how many function calls were there? 3 function calls were there. And what are they? 2, 9 and 16. 2, 9 and 16. This is level 2, right? And at level 3 how many function calls were there? 3, 7, 8, 10, 14, 15. Therefore 3, 7, 8, 10, 14, 15, right? And then at level 4 how many function calls were there? 4, 5, 6, 11, 12, 13. Therefore the total space required by this is, even though you had these many functions, all of them are occupying a maximum of 4 cells, right? But then this 4 is not a constant, that depends on how many what is the size of the n. So if you analyze this for 4, 6, 10, 20, 30 like that, you will find out that as the size of the given array is increasing, and if the size of the given array is n, then the number of levels required in this stack, this recursion tree, is log n plus 1. These many levels are required, right? And for every level we need a cell in the stack. Therefore assuming that then what is the stack size of the stack? Therefore the size of the stack required to implement this is this much, log n plus 1. This is the size of the stack required. and assuming that the stack is going to occupy a constant amount of size k, the total space complexity required in order to implement this recursion stack is order of k into log n, which is nothing but order of log n. Okay, so this is the space required for this stack in order to implement this program. And what is the space required for the merge procedure? For merge procedure, for merging, the space required is order of n. The reason is we are going to create a global array and all the merge functions are going to refer to that global array for the rough work, right? So for the stack, for the recursion stack, the space required is order of log n, and for the merge procedure, the space required is order of n. Therefore, the total space required, the total space complexity for this merge sort algorithm is order of n plus log n, and the dominating term is n, therefore it is going to be order of n, right? So this is the space complexity that is required by this merge sort. And one thing you should observe is merge sort falls under a category called out of place algorithms. Out of place algorithms means we are not going to sort the given array inside the array itself. We are going to copy the elements onto some other array and then sort them and again bring them back, which means we need extra array in order to sort it. That is why it is called out of place. We are taking the elements out of their place and then sorting them. So this algorithm falls under the category called out of place algorithm. Okay. Now let's analyze the time complexity. So this is how you should analyze the space complexity, and the time, space required is order of n. Now let's see the time complexity. How much time does it take in order to execute this program? So let us assume that given array is of size n. Then merge sort is called in order to solve merge sort is called to sort a array of size n. Then this one is going to be T of n. Let us say T of n represents time taken to sort the elements, n elements. Okay. Now we are going to divide the problem into two halves. How? By finding the midpoint and then the first half and then the second half, right? Then this one will contain half of the elements. Therefore, if the time taken to sort the n elements is T of n, then the time taken to sort n by 2 elements is T of n by 2, and time taken to sort the remaining half is T of n by 2, right? And time taken to merge is, if I have n by 2 elements and n by 2 elements, what is the time taken to merge total elements into one n list is order of n. This one we have already seen. If the total number of elements are n, right, and out of which I don't know how many, what is the size of the first list, and what is the size of the second list, but I am interested in finding the total size of the list. Let us say total size of both the lists put together is n elements. Then the time taken to merge both of them is order of n. Then how can I write this equation? T of n is equal to 2 into T of n by 2 plus order of n, right? Which means in order to solve a problem of size n, we are dividing the problem into two sub-problems of size n by 2 and then sorting them and then solving them, and then we are merging the result, right? So if you see this using the Master's theorem, the answer will be order of n log n. So whatever is the case, even if you give the sorted list or if you give the reverse sorted list, there is no best case and worst case for this. The time taken is going to be same. So both the best case and worst case is going to be n log n, which means if you give a sorted list, it doesn't solve faster, or if you give an unsorted list, it doesn't take longer time. Whatever is the size of the problem, it is always going to take n log n time, right? So that is about the merge sort. So next one is we shall see the quick sort. Like merge sort, if you observe that merge sort, the heart of the merge sort algorithm was merge procedure, right? Similarly, the heart of the quick sort algorithm is partition procedure. So I'll tell you what the partition procedure is, and the name of this sorting is quick sort algorithm. The reason why this name is given is it is not actually faster compared to others for all the inputs, but then if you compare merge sort and quick sort, if the size of the input is small, let us say if the size of the input is only 100, if I have to sort only 100 numbers, or let us say 10 numbers, if the size of the input is very less, then merge sort is going to have more complexity, in the sense more overhead, because merge sort uses lot of function calling. So that is why it is going to be sometime, so somewhat time consuming. But compared to quick sort, for smaller inputs, quick sort runs faster compared to merge sort. That is one thing you should keep in mind. And second thing is, even this merge sort and quick sort, both of them follow divide and conquer only. So I'll show you how it is divide and conquer problem. Let me talk about partition problem first. See, so quick sort works like this. Given an array, right? So quick sort will take an element, any element. So let's assume that it is taking the last element, and now it will take the element and put it in its position in such a way that all the elements to the left of it are less than or equal to this, and all the elements to the right of it are greater than this. Okay, so all the elements to the left of this will be less than or equal to this, and all the elements to the right of them will be greater than. Okay, so that is how it is going to partition. And therefore after doing this this step, one element will be in its correct position. Then we apply the quick sort on the left side list and quick sort on the right side list, right? So how do we do? Again, take the last element and put it in its correct position. Then one element will come into the correct position. Again, quick sort on the left side list and quick sort on the right side list. That is how it will continue. So whatever, we have to first examine the partitioning algorithm. So let's see the partitioning algorithm now. So I'll take an example and I'll explain you how the partition algorithm is working. Let's say the input is okay, this is the input. Assume that that is the input, and now we are supposed to sort it, or no, not sorting, we are going to apply this partitioning method. I'll tell you step by step what is happening there. So first see this, all these elements are there. So initially we'll take this element, 7 element, and then we'll try to place it in its correct position. So by the end of this partitioning method, this 7 is supposed to come into its correct position, and all the elements to the left of 7 should be less than or equal to that, and all the elements to the right of 7 should be greater than that. Okay, now in order to solve that, what we do is we'll start with 2 pointers. One is I and other is J. Okay, now the purpose of J is it will scan the entire list one by one, and whenever J finds any element which is less than 7, which is less than the last element, it will try to save it. See, it will try to move it to the forward. So now how does this algorithm work is, see this, J will keep on scanning the list, and whenever it finds any element which is less than 7, it will try to put it in its in the beginning. So 9 and 7, so 9 is greater, therefore don't do anything, move J. So J will be here. Okay, now 6 and 7, so 7 is greater, so we found an element which is less than 7. Now what we are supposed to do is we have to put all the elements which are less than 7 in the starting of the list. Therefore whenever we find any element which is less than 7, we'll increment I and we swap the I and J. So we increment I and we swap I and J. So if we swap I and J, what do I get? I get 6 here and 9 here, right? So see this, what is happening? J is scanning the list. Whenever J finds any element which is less than 7, which is less than the last element, it is going to put it in the next position pointed by I. Therefore whatever I is pointing, the entire list to the left of I will contain the elements less than or equal to 7, right? So now this is over. Now again J will move. Now J has found an element. This 5 is less than 7. Therefore, whenever it finds an element less than 7, we increment I and we swap the numbers, which means we increment I and we swap ith element with jth element, which means 5 will come here and 9 will come here. So if you observe what is happening, so all the elements which are less than 7 are now going to the starting of the list, and I is containing the boundary which beyond which, left of which all the elements are less than 7. And now again J is going to be incremented. J is pointing this. It found out 0 and 0 is less than 7. What does it mean? We found one more element which is less than 7. Then what are we supposed to do? Increment I and you swap the elements. If I swap the elements, 0 will come here and 9 will come here, isn't it? Then again J is incremented, and now the next value pointed by J is 8. So what do you say? J8 is greater than 7. Don't do anything. Again J is incremented. Next value pointed out by J is 2. So what did you see here? So this 2 is less than 7. Then what is that we are supposed to do? We are supposed to exchange with I plus 1, which means increment I will point to this now, and now you swap I and J. If I swap I and J, what do I get? 2 will go here and 9 will come here, right? So now just observe it. So till this point, wherever I is pointing, from there till the end, all the elements are less than or equal to 7, and from the next element till the J, all the elements are greater than 7, and the next following element, we didn't examine them yet, right? And now J will be incremented. J will point to 4. Then what did we find out? We found out that 4 is less than 7. Therefore again 4 has to be sent to the starting of the list, which means I will be incremented, and now ith element and jth element will be swapped. 4 will be here and 8 will be here, right? Fine. And now J will run from the first element to the element to the left of this chosen element. Now this is where the algorithm is going to halt. Fine. Now by this time we are sure that all the elements which are pointed by I, which are to the left of it, are all less than or equal to 7, and all the elements to the right of I are greater than or equal to 7. Therefore the correct position of 7 will be this one, isn't it? So we are going to exchange I plus 1 with this one. So we are going to exchange I plus 1 is nothing but this 7, and 9 will go here. Got it? So by the end, 7 is in its correct position. So this list is set of all elements which are less than 7, and this list is set of all elements which are greater than 7, and this list is the 7 is in its exact position. So now one element has been sorted. Therefore by the end of one iteration, or by the end of one partitioning algorithm, one element is getting sorted, right? So what is the total time taken? We are running J from first element to n minus 1th element. Therefore the time complexity is order of n. Time taken by the partitioning algorithm is order of n. Let's take one more example and trace it out. I'll take few more examples and I'll just trace it out what is happening. I'll just show you. So maybe I'll explain you the algorithm also. Let me take an example and show you. Let us say the input is 13, 19, 9, 5, 12, 8, 7, 4, 21, 2, 6, 11. Let us say this is the input. Then how does this algorithm work is, this is the complete array. How does this algorithm work is, first we have to choose the element. So here partition is called on an array A with P and R as the boundaries, which means we have to partition the array A from pth index to rth index. Let us say here P is 1, there are 12 elements, right? So let us say we are calling partition algorithm on partition A 1 to 12. Okay, so first thing is we are going to take x as a of, first line is x equal to a of r, which means I am going to take x equal to 11, right? And now I equal to p minus 1, which means I will point to 0. 0 means it is not pointing to anything. Okay, and now for j equal to p to r minus 1, which means j will start from here, p is 1 to r minus 1. R minus 1 means 11, which means j will run from first element to the last but one element. Then how is it going to work? So it is going to take, for every time it is going to compare if a of j is less than or equal to 11, which means whenever the search, whatever j is doing is simply it is searching for an element which is less than or equal to 11. Now whenever it finds an element which is less than or equal to 11, it is simply going to increment I and exchange that element, those two elements. That is what is happening, which means, see this, now j will be compared with 11. Is this element less than or equal to 11? No, therefore incremented. So j will point here. Is this element less than or equal to 11? No, therefore incremented. J will point here. So finally we found an element which is less than or equal to 11. Then what is that we are supposed to do? Increment I, which means I will be incremented, I will be present here, and now we swap a of I and a of j. So 9 will be present here and 13 will be present here, right? So that is what is done in the first round. Now again this j will start moving till the last point. Now j will be incremented, j is here. Check this, is a of j value less than 11? Yes, we found an element less than 11. So what should we do? We should push it to the initial starting of the list. Therefore we increment I, which means I will point here, and then we exchange these two elements. Which elements? 5 and 19. So 5 will be here and 19 will be here, right? And again j will continue. So j will go to the next element. Now what did you see? Next element is greater than 11, so don't do anything. Again next element, again we found an element which is less than 11. So whenever the element is less than or equal to 11, we are supposed to push it to the initial, which means I will be incremented, and now we are going to exchange it with this. So 8 here and 13 here, right? And again j will move. J has again found an element which is less than or equal to 11, so it has to be forwarded, right? It has to be sent to the beginning, which means I will be incremented and now it will be exchanged. So 19 and 7 will be exchanged, 7 and 19. Now you just at this point you can stop and examine all the values which are from I to the beginning. All these values will be less than or equal to 11 anytime, right? And from that next element to I plus 1 to j, all those values will be greater than 11, and remaining elements, they are yet to be examined. We don't know the relationship, right? Now j will be here. We have again found an element less than j, less than 11. Therefore again we are supposed to exchange, increment I, and you exchange 12 and 4. 12 and 4, and again j will be next element. Check this. So 11 and 21 is greater, so don't do anything and increment it. Again I found an element which is less than 11. 2 is less than 11. Therefore what is that we are supposed to do? Since 2 is less than 11, we are again supposed to increment I and then swap it. So one doubt is, why are we not swapping I with j? Why should we increment I plus I to next element and then swap? if I directly swap I with j, already this element is also less than 11 and this element is also less than 11, but if I exchange them, again I will leave an element which is less than 11 in the ending. So I have to take the first element which is greater than 11 and then swap it, so that I will always point to the elements which are less than 11, right? So I increment I, first increment I and then swap it. So 2 and 13 will be swapped, 2 here and 13 here, right? And again j will be incremented, and as we got one more element which is less than 11, then what should we do? Increment I have incremented I and then swap them. So 6 will be here and 19 will be here, right? Now observe this, this j is running from 1 to 11, so j has to run from p to r minus 1. R minus 1 is 11, right? So therefore this entire loop is over, this entire for loop is over, the for loop is over. Now I have to go to the next element, next line, right? So what is next line? Exchange a of I plus 1 with a of r, which means this element has to be exchanged with this element. The reason is simple. From the point where I is pointing to the beginning, all the elements are less than or equal to 11, right? And therefore the correct position of 11 has to be the next element to I. So you have to exchange a of I plus 1 with a of r, which means this 8 has to be exchanged with this 12th position. So these two have to be exchanged. 11 will come here and 12 will go there. Therefore by the end of this partition, one element 11 is in its correct position and all the elements to the left of them are less than or equal to it, and all the elements to the right of 11 are greater than that. Now if you observe this, all the elements to the left of it are actually less than or equal to this, but then they are not sorted. That is one thing you should observe. These are all just less than or equal to, but they are not sorted. These elements are greater, but they are not sorted, right? Therefore partitioning algorithm, if I call it on a list, it is just going to take one element and it is going to place it in its exact position, and that position can be anywhere. And again you have to apply partitioning on the left side and on the right side. That is how the sorting will work. So one thing you should observe here is, whatever is the input, whatever is the pattern in the input, either it is sorted or unsorted or random numbers, it is always going to take order of n time. The reason is j has to run from starting to n minus 1. So j will start from here and will go till the first point. Therefore the total time taken will be order of n minus 1, which is nothing but order of n. So that is how partition is going to work. After partition algorithm, one element is going to come into its exact position, and now we are even returning its position, right? So what is the position that we are returning? 8, which means that the array to the left of 8 has to be sorted and the array to the right of 8 has to be sorted, but the array at 8 is actually sorted, which means now if you send to this algorithm an array A with indices 1, 12, it is saying that from 1 to 7 you have to sort it next, and then from 9 to 12 you have to sort it. The element 8 is already sorted, you need not consider it, right? That is how this algorithm is going to work. Now let's see how partition is going to help us in order to build a complete sorting algorithm. Okay, that is nothing but quicksort. Remember that in merge sort the heart of the algorithm was merge procedure, and in quicksort the heart of the algorithm is partitioning procedure. Okay, let's see this quicksort. As I said, the heart of the quicksort is partition algorithm. So we have already discussed partition algorithm, and I'll show you this, explain you how this quicksort works. So quicksort, when it is called on an array A with p as the left index and r as the right index, see this, quicksort is called on an array A with p as the left index and r as the right index. And what happens is, so given an array A where p is the left index and r is the right index, first thing is it is going to call partition on the same algorithm from p to r, isn't it? Partition is called from p to r. Then what will partition do? It will take the last element. And one more thing is, partition is supposed to take any element, it need not take the last element. Some books have this implementation that they take the last element and put it in its correct position. Some books have the implementation where it will take it from the first element and put it in its right position. So whatever it is, one element will be kept in its right position, correct position, and then the elements to the left of it will be less than that, and elements to the right of it will be greater than that. That is the purpose of it. And implementations, they vary from textbooks to textbook. I am following the Coreman, okay, the Introduction to Algorithms by Coreman, CLRS book. You can follow any book. So see this. Now partition, this one is going to take this element and it is going to put in its right position. Let us say this one, and let us assume that this position is Q, and that Q will be returned by the partition. Therefore partition algorithm is going to return the index Q, right? Then what should we do? Now P2 Q minus 1, they are all less than Q and they have to be again sorted. That is why again we are going to call quicksort on P2 Q minus 1, isn't it? And then Q plus 1 to R, from here to here, they all have to be sorted. That is why again we are calling quicksort on this one, right? Again we call quicksort on this one and quicksort on this one. What will this quicksort do? Again it will call the partition. Again let us say partition will partition it like this. Then quicksort will be called here and quicksort will be called here. Again on this side also quicksort will call partition. Let us say partition will give this one. Then again you have to call quicksort here and quicksort here. In fact it is nothing but divide and conquer, right? The entire big problem is going to be divided into two small problems, and again those problems will be subdivided until we get size 1. So what is the main difference between merge sort and quicksort is, if you have watched my merge sort algorithm, video, in that algorithm I have shown you that merge sort is always going to find the midpoint and it is going to divide it into equal halves. But here quicksort, the way it divides the problem, that depends on what is the output given by the partition, right? Sometimes partition will give you the midpoint and sometimes it will give you some other point. So depending on what is written by partition, the sizes of the subproblems will vary. So I'll take an example and I'll explain you how this quicksort is going to work. Let me take an example of 7 elements. Let us say the 7 elements are this. Given array is 5, 7, 6, 1, 3, 2, 4. Just for the sake of example, let's say these are the numbers, right? Now let me give them indices. So they are all present in an array called A, which is global array, which will be passed to the pointers will be passed to all the functions, right? And the index is 1, 2, 3, 4, 5, 6, 7. 7 elements are there, right? Initially quicksort, so quicksort will be called on the array A that is known from the index 1 to 6, right? So see this, when I call quicksort on array A from the index 1 to 6, first condition, this condition has to be checked. Always P has to be less than R, which means lower bound has to be greater than less than upper bound, 1, 7, right? Yes, 1 is less than 7. Then first step is it is going to call partitioning. Now it will call partition on 1, 7. Depending on what is the result of this partition, the next function calls will depend. If you have watched the merge sort algorithm, there I was directly writing merge sort of 1, 7 and then merge sort of maybe 1, 3 and then 4, 7, because there I know that the partitioning is exactly in the middle. But then here the next function call actually depends on the result of this partition. So let's run the partition on this first. Now see what happens if I call partition on this. So now if you remember that partition algorithm just I have shown you previously, it will take this element and it will try to put it in its correct position. How? By taking I and j, right? So initially I will be to the left of the left bound and j will start from here. J will start from here and it will run till the 6 until it finds out some element less than or equal to 4. So is 5 less than 4? No. Is 7 less than 4? No. 6 less than 4? No. 1? Yes. So it found an element which is less than 4. Therefore j will stop here initially. Then what will happen? I will be incremented and these two will be exchanged. So what do I get? 5 here and 1 here. All the elements which are less than 4 will go to the beginning, right? And again j will be incremented, and we found an element which is less than 4. So I will be incremented whenever we find an element which is less than 4. I will be incremented and exchanged, which means 7 will be here and 3 will be here, right? And again j will be incremented. Now again we found an element which is less than 4. Then what should we do? Increment I and you exchange it. If I exchange these two, what do I get? 6 here and 2 here, right? Now this partition algorithm, you know that for loop of partition will stop here. Now we understood that from I onwards to the left of it, all the elements are less than or equal to this chosen element. This element is also called as pivot. The partition algorithm is going to pick an element and it is going to put it in its right position. That element is also called as pivot or pivot, right? Remember this, pivot is the element around which this partition algorithm is going to partition the array. Okay, so in this case the pivot element is the last one, which is nothing but 4. Now what does partition algorithm do? It has to exchange I plus 1 with this pivot element. 4 will be placed here and 5 will be placed here, right? And then it will return the index of the placement. So what is the index of the placement of the pivot element? 4. Therefore it is going to return the number 4, saying that after partitioning the array, the array has the 4th position, the element is placed in its position, and to the left of it all are less than it, and to the right of it all are greater than it. In the left of it the elements are less than or equal to, which means in case if I have any force, they will be in the left of it. On the right of it all the elements will be greater than it, right? Now accordingly, if I got the pivot element as 4, which means if the returned the number is 4 by partition, then quicksort has to be called accordingly, right? Now if I have to sort from P to R, then now I have to sort from P to Q minus 1. Therefore quicksort here will be called from what is P? 1. 4 is already in its correct position, therefore 1 to 3 I have to sort these 3 and the remaining half, 5 to 7. So 1 to 3 I have to sort and 5 to 7 I have to sort, right? And again now quicksort will be calling, first thing is partition from 1 to 3, and then I don't know. So depending on the output of partition, the next calls of quicksort will depend, right? So let's see what happens here depending on the calls of partition, right? So now I have to, partition is called from 1 to 3, from here to here, right? So in this array 1 to 3, what is the last element? 2. Therefore 2 will be chosen as the pivot element. Now 2 is the pivot element. I will be to the left of the left bound and j will start from here. So what is the responsibility of j? To find an element less than or equal to 2. Yes, it found an element less than or equal to 2. Then I will be incremented. Both I and j will point to the same element and they are to be exchanged. If I exchange, we get the same thing, right? And then j will be incremented. So j will be incremented from P to Q minus 1, right? So whatever it is, the element to this. So j has to stop here, right? And now you understood that I is here, I is pointing to the first element and j is pointing here. Therefore pivot has to be exchanged with the next element which is to the I. So these two will be exchanged. 2 and 3 will be exchanged, and this is the placement of the pivot. Therefore what will this this partition algorithm return here? 2, which means it is saying that in the array 1 to 3 I have got the element placement as 2, right? 2, and now we have to see how to call the quicksort. Now what is remaining? 1 to 3, so 1 to 1 is remaining and 3 to 3 is remaining. 1 to 1 and 3 to 3, and 1 to 2 is already placed in its correct position. So first call to partition has placed 4 in its correct position, second call to partition has placed 2 in its correct position, and therefore remaining array is 1 comma 1 and 3 comma 3. So remaining array is 1 comma 1 and 3 comma 3, right? Now let's see what happens to this one, this function quicksort. So if you see this quicksort 1 comma 1, it will enter it, but then p is not less than or, which means 1 is not less than or, therefore it will not enter into this if loop. So it will not do anything, it will simply return. And even the same thing with this, it will not do anything, it will simply return. The reason is simple. So we have to sort only an array whose size is 1, and moreover every array of size 1 is already sorted, therefore no work to be done. So by this point Q13 is over, which means Q13 is sorted and 4 is already sorted, and what is remaining? 5 to 7. So look at this, Q5 to 7. What will this one do? This one will call partition on 5 to 7, right? Therefore partition is going to work here. So if partition algorithm works here, it will take 5 as pivot and try to find from 5, try to find the element less than 5. It didn't find anything. Therefore j will be 1 less than 5, I will be 1 less than 5, and j will be standing here, right? And then what happens? Finally I has to be incremented. Yes, I is incremented. Sorry, I will be here. I plus 1 and the pivot will be swapped, which means 5 and 7 will be swapped, right? Now what is the position that is returned by the position returned by the partition algorithm is 5. So 5 is being returned by the partition algorithm. Then what should the quicksort do? Quicksort should start from 5 to this partition minus 1. So it has to call two quicksorts, right? It has to call again quicksort on 5 to 5 minus 1. See, that is how it is done. So if I am having quicksort on P to R, then once I get a Q, then it should call from P to Q minus 1. Here what is P? 5. What is Q? 5. So 5 minus 1 is 4. This is meaningless. Sort an element, sort an array which is starting from 5 and ending at 4. How can array start with 5 and end at 4? This is meaningless, right? And what about the other one? The other index is P plus 1, Q plus 1. So what is Q plus 1? 6 to R, which is nothing but 7, which means you have to sort this one by this function, right? Now see this 5 comma 4. Yes, 5 comma 4, it will never enter this if loop. The reason is 5 is not less than 4, P is 5 and R is 4, therefore nothing will be done by this. Now we have to see it. Look at this one, right? The element containing Q containing two elements. Now it will call partition on 6 comma 7. When it calls partition on 6 comma 7, this one will be pivot, 7 will be pivot, and then j will try to find out the element less than it, which is 6. It found out, therefore I will be starting from here. I will be incremented and a of I and a of j will be swapped, which means 6 only. And now 7, so j is going to start here and stop here. The reason is there is only one element other than the pivot element. And now 7, we know that 7 has to be placed in the right of this, right of I, which means 7 has to be placed in its position 7 itself. So the pivot will be remaining here, right? So what is the position returned by this? 7, right? Then what does the quicksort call? Again a quicksort on P, which means 6 comma Q minus 1, which means 6. And then again quicksort will be called on, and again quicksort will be called on 7 comma Q plus 1, which means 8 comma 7, which is meaningless. This one will stop and this one will stop, right? So that is how this entire algorithm is going to work, right? So one thing is I cannot draw the tree directly and then trace it out. So I am actually doing it dynamically. So seeing on what is being written by the partitioning, I am going to do this, right? So one question is, what is the space complexity required by this? So even though you are seeing that there are a lot of function calls here, so if you count all the function calls are nothing but 1, 2. So what is the order in which function calls are made? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, sorry, 9, 10, 11, 12, 13. This is the order in which function calls are made. So does it mean that since I have 13 function calls, does it mean that I need a stack which should hold 13 records? It turns out that we don't need those many, right? So how many stack records that should we need is that should be equal to the number of levels, right? So the number of levels in the tree is equal to the number of stack entries required. So that depends on how many levels we could get the this recursion tree as. So in best case, if I have n elements in the beginning, if the partition algorithm is going to divide it into n by 2 and n by 2, I mean nearly n by 2 and n by 2, obviously one element will be less, and if every time if I am getting a balanced partitioning, which means n by 2 like this, n by 4, n by 4, n by 4, n by 4, in this case the total height of the tree, see, I have already shown you how to analyze a recursive function space complexity when I was dealing with merge sort. You please refer to the merge sort video, how the space complexity actually depends on the height of the tree, right? See, in this one we are not going to use any extra space, only p, q constants are used, only p and q are used, p or q are used, so 3 variables, and the extra space required will be for the stack. So how many records that we need in this stack? So in this example I need, how many levels are there? 1, 2, 3, 4. 4 levels are there, therefore I needed 4 records. So the number of levels actually determine what should be the depth of this stack, right? So what should be the depth of this stack? In case if the input, if the input is divided into equal halves, then the height of the tree will be order of log n, isn't it? In this case, the space complexity required by the recursion stack is, assuming that there are log n levels, then the number of records required in the stack will be log n. Assuming that each stack is going to occupy a constant time, then the time taken will be order of c into log n, which is nothing but order of log n. This is the space complexity required in case if it is balanced. Now let us say that it is unbalanced, which means let us assume that in the worst case what happens is, you will call this quicksort on n elements, and now that is going to divide the algorithm that is going to partition the array in such a way that one element will be there in the first one and n minus 2 elements will be there in the second one, right? And one element will be in its correct position. Then again this one may get divided in such a way that one element will be there in the first half and n minus 3 elements will be there in the next half, right? Let us say n minus 4, so on, right? Then in this case the height of the tree might go as big as order of n, right? So if the balancing is not even, if the balancing is not actually dividing it into even parts, then in that case the height of the tree might grow as big as order of n. So in that case I might get the space complexity as order of c into n, assuming that every stack record is going to take c. In that case space complexity could be order of n. Therefore for quicksort using recursion, the space complexity can grow as big as order of n. But for most of the cases we don't get such a kind of division, okay? So most of the cases we get even if it is not even kind of division, then also we don't go to that worst case. But in worst case the space complexity is going to be order of n. In average case space complexity is going to be order of log n. Now let's see what happens about the time complexity. So coming to time complexity, let us assume that the time taken to sort n elements by this quicksort is T of n, right? then the time taken for this partition algorithm we already know is order of n. Then in best case means if the partition algorithm is going to give us the midpoint as the pivot element, then in that case there will be equal sized partitions, which means A will be partitioned into half elements, first half and then the second half. In that case I have to apply sorting on n by 2 elements, nearly n by 2 elements and n by 2 elements. This is the best case time complexity, right? So in the best case the equation is going to be T of n equal to 2 into T of n by 2 plus order of n, and we already know that by Master's theorem this is theta of n log n. So time complexity, the best case time complexity for quicksort is order of n log n, theta of n log n. Then what is the worst case time complexity? See this, let us say the total time taken is T of n in order to sort n elements using quicksort. Then obviously there is no shortcut here, so for partitioning time taken will be order of n itself, right? Then by the quicksort, after the partitioning we might go as bad as always there will be one element or even zero elements. There will be zero elements on one side and then n minus 1 elements on the other side. What happened to the other element? That element is already in a correct position, which means, see this, you might have given some input like this, let us say 1, 5, 6, 7 and then 10, and when you apply the partition on this, then 10 element is going to be in its same position, right? Therefore we get only one partition, which means we get only one part which contains all the n minus 1 elements. One element will be in its correct size and the other side there will be no elements, right? That is the worst case, which means after partitioning the one element got in its exact position, which is either at the first half or at the beginning or at the ending, and all the other elements n minus 1 elements are remaining to be sorted. In this case what is the equation? T of n equal to T of n minus 1 plus order of n. You can write this order of n as Cn, n minus 1 plus Cn, right? Now if you apply back substitution, what do I get is T of n minus 1 is nothing but T of n minus 2 plus C n minus 1 plus Cn. In place of T of n minus 1 I am substituting this entire thing. Okay, how? Just see this, T of n minus 1 equal to T of n minus 2 plus C into n minus 1, right? Again in place of n minus 2 if we substitute this, what do I get? T of n minus 2 equal to T of n minus 3 plus C into n minus 2 plus C into n minus 1 plus Cn, right? So on, I'll get n minus 1 into C of n minus 1 into, I get C plus C into 2 plus C into 3 plus so on plus C into n, which is nothing but order of n square. Therefore in worst case quicksort might take as a worst case time of order of n square. So what is that worst case? Whenever the pivot is going to put the element, either at the beginning of the list or at the ending of the list, in that case I am going to get a worst case complexity of order of n square. Therefore the best case time complexity of quicksort is theta of n log n, and the worst case time complexity of quicksort is order of n square. What about merge sort? Either it is best case or worst case, it is always order of the theta of n log n, right? But here the worst case can go to as bad as order of n square. Now we shall see some kind of inputs, then we shall analyze if it could be done, if it is always going to be order of n square, or is there anything better than that. Okay, let's see some examples on this. So there are some kinds of problems like optimization problems. What is optimization is, I would like to either maximize a property or minimize a property. So given a graph, what is the shortest, what is the minimal spanning tree, right? Which means I want to either minimize the cost or maximize the profit or maximize the reliability, or let us say I want to minimize the risk. So these are all called optimization problems. So either I want to maximize some properties or I want to minimize some properties. Okay. So given a problem, if I try to maximize or minimize a property, then it is called optimization problem. And there are various ways to solve such problems. So I'll just show you with an example. Let us say there is a graph like this, and these are nodes, and these are edges. Say these are the nodes A, B, C, D, E, and every edge is given some weight. Okay, something like this. Now the question is, what is the shortest path possible from A to C? If I start from A and if I have to go to C, what is the shortest path? Then one way to solve it is using exhaustive search. Exhaustive search means find out all possible solutions, which means find out all possible paths from A to C, and then you find out in all those paths what is the one with the least value, right? So for that it might take exponential time, order of 2 power n, isn't it? So where, let us say there are n edges, okay, there are n edges, then in the path a edge could be present, or edge might be present or might not be present. In that case, for every edge I have 2 chances, therefore I might have to examine total of order of 2 power n edges, right? A total of I might get 2 power n paths, and in these paths I have to find out the minimum. So it is going to be order of 2 power n algorithm. So we want to see if we could do something better than this. Obviously finding out all the solutions and then finding the minimum is going to take lot of time, given that the size of the problem is large, right? Therefore we want to see some other methods using which we could solve such problems easily, optimization problems especially. So we found out that there are 2 programming paradigms. One is called greedy, and other is called dynamic programming. So greedy method and dynamic programming are 2 programming paradigms which could be used to solve optimization problems. Okay. Now with examples I'll show you which one is better and which one to be used for a problem. But just let me introduce you these methods. So using greedy method, we will not be able to solve all the optimization problems. The problem should have some properties, then only we can apply greedy method. So first thing you should remember is, using greedy method we may not be able to solve all the optimization problems, but only for some of the problems we will be able to give greedy method, right? And coming to dynamic programming, we will be able to solve any optimization problem with dynamic programming, but then some programs, even after applying the dynamic programming method, might go to exponential time. Okay. So dynamic programming, using dynamic programming we could get order of n power k solutions. That is what we need. If for a problem, if we can get order of n power k solution, then that is why we actually apply dynamic programming. But to some other problems we might get order of 2 power n solutions, which means exponential time solutions, and it is as good as applying the this exhaustive search method. Okay. So again, just remember that using greedy method we will not be able to solve all the optimization problems, which means given a problem we might not get the optimal solution by applying greedy method. There are only some subset of problems out of the optimization problems for which we could apply greedy method. I will show you all such problems, or at least some of the problems for which greedy method could be applied, and after these examples I will tell you how the greedy method is actually working. And coming to dynamic programming, the main, dynamic programming can solve any problem, any optimization problem, but that is not what we wanted. We want to apply dynamic programming if it could do something better compared to exhaustive search, right? So when we apply dynamic programming, the problems which used to take order of 2 power n time in exponential, in exhaustive search method, might take polynomial time, order of n power k, but still there will be some problems for which even after applying dynamic method, we might end up getting a exponential time, which means order of 2 power n, but that is not what we wanted. If we get order of 2 power n time, then we could have we would have as good, it is as good as applying the exhaustive search method, right? So for some of the problems, greedy method could be applied. For all the problems, dynamic method could be applied, but the time complexity of dynamic programming could be either polynomial or exponential. So for the problems where the polynomial time, where we get polynomial time using dynamic, that is where we apply dynamic. Otherwise, it is not a good thing to apply dynamic at all, right? So if you see all the set of problems, optimization problems, greedy method could solve only some of them, and dynamic method could solve all of them. If I apply greedy method, generally the solution will be polynomial, order of n power k or n log n, something like this. If I apply dynamic method, then the solution could be order of n power k or order of 2 power n. And for these problems, we say that applying dynamic method is beneficial. And for these problems, if you are not able to reduce the time complexity to polynomial time, it is as good as applying exhaustive search, right? So it is better, instead of talking about the theory and what are the characteristics that a problem should contain, I'll take the problems and we shall see how these methods could be applied. So after seeing examples, these points will be very much clear for you. So now let us see about greedy method, and we shall solve all the problems, or at least some of the problems for which greedy method could be used. Okay. Let's see one problem for which greedy method can be applied. This problem is called knapsack problem. So knapsack means bag. And one more thing, for this greedy methods, I'm referring to the book Design and Analysis of Algorithms by Sahani and Horowitz. Design and Analysis of Algorithms by Sahani and Horowitz. Okay, you please refer to that book. That has got all these examples. I have taken the example from that book. Okay, and I am going to take even more examples to explain this. In order to, if you have to refer to that any book, you please refer to that book. And till now, the sorting algorithms, all the sorting algorithms and divide and conquer methods, I have taken them from that Coreman book, Introduction to Algorithms by Coreman. Okay, so now see this. The problem is, it is called knapsack. Knapsack means a bag. So the problem statement is like this. Now we are given a bag of capacity 20 kgs, which means the bag can hold 20 units. Let's say 20 units of any product. Okay, that is the maximum capacity of the bag. And now we are given three objects, object 1, object 2 and object 3. Every object has got some profit provided that you sell these many units of that object, which means if you sell 18 units of object 1, you are going to get a profit of 25. If you sell 15 units of object 2, you are going to get a profit of 24. 10 units if you sell, you are going to get a profit of 15. Now the question is, how many what are the objects that you want to place into the bag in such a way that we get the maximum profit? Okay, that is the question. Understand it? We are given a bag of maximum capacity 20, which means you will not be able to place more than 20 units, right? And now what are the objects that you want to pick and put it in this so that you get the maximum profit? So one thing is, you might try to put all the objects available into the bag, but then the bag has a capacity of 20 units, but if you see all the objects, this is 18, 15, 10, so we cannot even put more than one object there, right? Therefore putting all the objects is not possible. Then what do you want? Which object do you want to put first? There are various strategies. Let us say my strategy is, I'll try to be greedy about profit. I'll be greedy about profits, which means since I want to maximize the profits, I'll take the object which is having maximum profit. Therefore it seems like if I take this object first and put it in the bag, I'll get the maximum profit, right? So if I do that, let's see what happens, which means I'm going to pick the one with maximum profit. So what is the one with maximum profit? I'll pick object 1, right? If I pick object 1, then what is the weight of it? If I pick object 1, then what is the weight of it and what is the profit I get because of that? If I have to pick 18 units of object 1, then only I'll get 25 profit, right? Therefore 18 units is already filled. Then what is the remaining space? I have only 2 units, isn't it? So I have to fill 2 units, and the next item available with maximum profit is object 2, but total amount, no, if you sell 15 units, then you are going to get 24 as profit, but how much space you have? You have only 2 units, isn't it? See this, first unit is already filled, which means I am going to put 18 kgs of first unit, because of which profit I got is 25. Then what is the capacity remaining in the bag? Only 2 units, right? But if I take the second object is 15 units is present. If I sell all the 15 units, then I get a profit of 24, isn't it? But then I don't have that much amount of space here. So if I sell 15 units, then I get a profit of 24, but I have space to sell only 2 units, isn't it? If I sell 2 units, then how much profit do I get? 2 by 15. So this is the profit I get, isn't it? Therefore of object 2, I am going to place only 2 kgs, because that is the maximum I have. That is also called as fraction, right? So in greedy method, remember that we are even going to allow the fractions. So if the space is not enough to put the entire item, I am going to put fraction of that. So out of 15, I am going to place only 2 units. So if I would have sold 15 units, my profit would have been 24, but then I am selling only 2 by 15th part of it. Therefore my profit would be this much, right? So that is what I do if I think about only profits, isn't it? Then what is the total weight of the knapsack? Total weight of the knapsack is 20 now. Then what is the total profit I get? If you add these two, the profit I am going to get is 28.2, right? So if I fill the bag with 18 units of first one and 2 units of second one, I am going to get a profit of this. So is this the maximum? Is this the best possible solution? So what is the solution here? I want to maximize the profit. So is this the maximum solution, or are there any other methods which I could apply and get the maximum solution? Let's observe that instead of being greedy about profits, what I'll try to do is I'll try to put as many objects as possible into the bag. If I have to put as many objects as possible into the bag, then definitely what is the strategy I should follow is I should take the object which is having least weight and I should put it first, so that the bag could be filled with many objects, isn't it? So second strategy is greedy about weights. I'll try to be greedy about weights. So if I try to be greedy about weights, I have to take the one with the least weight and put it first. Then what is the one with the least weight? Object 3. Therefore I'll place object 3 first. What is the weight of it? 10. What is the profit I get? 15. If I place 10 units of object 3, I am going to get a profit of 15, right? Therefore I am going to put all the 10 units and I am going to get a profit of 15. Then how much empty space I have? 10 units, isn't it? Then what is the second pick? The second object with the least weight is object 2, right? So if I pick object 2, I cannot put all the 15 kgs of it, right, or the 15 units of it. I can put only 10 units of it. So I am going to put 10 units of object 2, and the profit I will get is 24 into 10 by 15. The reason is, if I would have placed the entire 15 kgs, I would get a value of 24, but then I am not going to place the entire 15 units. I am going to place only 10 units of 15 units. Therefore the profit is 10 by 15th of this, right? So if I use this strategy, then the entire knapsack is filled with 20 units, that is the maximum capacity. and the profit I'll get because of it is 31 units, right? So I found out that if I am greedy about weights, for this problem, for this instance, I got more profit. It is not applicable for all the instances. See, only for this problem, if I am greedy about profits, I got some value, and if I am greedy about weights, I got some value. But for this problem, for if I am greedy about weights, I got more value compared to profits. It does not apply to all the problems, right? So this method is also giving me some answer, therefore I feel that optimal answer is 31, but I am not very sure. So what is the other property which I could be greedy about so that I could get maximum profit? So intuitively we feel that instead of using profits only or weights only, I could say what is the net value per unit, which means what is the profit we get by selling one unit of each object. So if I can find out that, and if I could place the objects accordingly, then I get maximum profit, isn't it? Therefore the third method is, don't go either by profits or don't go either by weights, you go by a ratio of profit by weight, which means what is the if I sell 1 unit of this, what is the profit? If I sell 1 unit of this, what is the profit? If I sell 1 unit of this, what is the profit? You go in that method, you might get a better solution. That is what we feel intuitively, right? So let's see what are the values of this. 25 by 13, 24 by 15, 15 by 10. So if you see 25 by 18, the value of 25 by 18 is 1.4, and 24 by 15 is 1.6, and 15 by 10 is 1.5, right? Now we found out that if I sell 1 unit of object 1, I am going to get a profit of 1.4. If I sell 1 unit of object 2, I am going to get a profit of 1.6. If I sell 1 unit of object 3, I am going to get a profit of 1.5. Therefore obviously now you feel that the one with the maximum profit per unit, that has to be placed in the knapsack, isn't it? Then I'll take the knapsack. Then you are going to see that this object has to be filled first. The reason is it has the maximum profit per unit. Therefore object 2 will be placed completely, isn't it? If I place object 2, what is the total weight available and what is the profit I get? Total weight available is 15 and the total profit I get is 24, right? Therefore total weight, I'll fill it up, is 15. Then what is the remaining space available? 5 kgs, isn't it? Then next object I have to place is object 3, which means I am going to place object 3. How many units? I cannot fill completely, I can only take 5 units. I'll take 5 units. And what is the profit for that? The profit for it is 15, provided that I have to have filled 10. But then since I am filling only 5, 15 into 5 by 10, right? Now if you take the total profit I get, the total weight in the knapsack is 20, and the total profit I get is, if you sum it up, I think it is 31.5. Okay, so that is the maximum value we get. Yeah, so 31.5. So you found out that either by being greedy about profits, I don't get the maximum value, or either by being greedy about the weights, I don't get the maximum value. But if I am greedy about profit by weight ratio, then I am going to get the maximum value, which is 31.5. You could find out all other possibilities by placing object 1, object 2, any other possibility. You will see that we are going to get maximum value only for this way, right? Therefore what is the algorithm? We are going to find out profit by weight of all of them, and then we are going to place them one by one in the decreasing order of profit by weight till the bag gets full, isn't it? Now let's see the algorithm for this, and then I'll explain you with even more examples. Let's see the algorithm, analyze the time complexity and space complexity, and then we shall go on to see. So let us see how the algorithm works. I'll explain you with an example. Then we shall analyze the time complexity. Okay, So this is the iterative version of the algorithm. And one more thing, if a program can be implemented using iteration, you could implement the same program using recursion. So recursive programs can be written in iterative version, as well as iterative version can be written in recursive. But most of the time, if I go for recursion, I might have to use the recursive stack, right? And because of which space taken for such programs, recursive programs, might be bigger. Writing recursive programs is simpler, but then while executing it, space taken might be more compared to iterative versions. So whatever I'm showing you here is iterative. Okay, so let's see this. Now objects are given, 1 to 7 objects are given, and they are saying that capacity of the knapsack is 15 and number of objects are 7, and every object is having profits and weights. Okay, so see this in the algorithm. First step is for I equal to 1 to n means the number of objects. So how many objects are there? 7 objects. Compute pi by wi, which means compute the ratio profit by weight. So you compute for every object what is the profit by ratio value. There are 7 objects total. I am just computing profit by weight ratios. Okay. Okay, so these are the profit by weight ratios. That is what is done. And next one is sort objects in non-increasing order of profit by weight, which means take the objects one by one and then sort them in a decreasing order of profit. Non-increasing means decreasing order, right? So non-increasing order of profit by weights, right? So what are the objects? Now we are going to write the objects in decreasing order of profit by weight. So which one is the highest profit here? If you see the profit by weight ratio, which one is having the highest? Object number 5. So we get object number 5, then object number 1, then object number 6, isn't it? After 6, 5 is greater, then 4.5, right? And then I have 3 and 3, so you can take anything. So let me take the 3, object number 3, and then object number 7, these two, right? And then next one remaining is 1.6, so 2, and finally 4. So that is what I did. So that is the next step. Okay, first step is computing P by W, profit by weight ratios. Second step is sorting the objects in this P by W order, and next one is for I equal to 1 to n, I am going to take each value, and if m is greater than 0, which means if the knapsack is still having capacity to hold more objects and the chosen object could be completely placed in the knapsack, which means knapsack is having some capacity, even more free space, and I should be able to put the chosen object completely into the knapsack. If that is so, then I will be decreasing the capacity of the knapsack, this one, and then I will increasing the total profit. So whenever I add any object to the knapsack, I have to increase the total profit. So I am going to increase the total profit, right? So if this is true, which means if either the knapsack has to have some free space, and moreover the chosen object we should be able to place the chosen object completely into the knapsack. If these two conditions are met, then I am going to add the object, right? Otherwise break, which means I'll come out of for loop. And finally I'll check if the knapsack is still having some empty space into which I could place the fraction of the object. That is what I'll check. I'll just take this, I'll just explain this algorithm using this program. So first step is profit by weight ratios have been computed, and second step is I sorted them out, and now I'm going to take each object one by one. So actually this each object one by one should be from the sorted list, okay, from sorted list, not from the original list. So I'm going to take it in the sorted list, right? So check this. First one I'm going to see is, let us say this is the knapsack, and I am going to add objects one by one. What is initial capacity of the knapsack? Initial capacity is 15, isn't it? Now I am going to take object number 5. So see this, object number 5. What is the weight of it? Weight is 1. And what is the capacity I have? 15. Therefore definitely I can place 1 kg because 1 unit, because it is able to hold 15. So after placing object number 5, what will be the remaining capacity? So initially the capacity was 15. Now the remaining capacity will be 1 has to be decreased. Therefore remaining capacity is 14, right? And because of adding object number 5, what is the total profit I gained? So since I am adding completely object number 5, the total profit I gained is 6. Got it? Now I'll see the next object to be added. Next object to be considered is object number 1, right? So go to object number 1. What is the total weight of it? 2. So can I put the entire 2 units in the knapsack? Yes, because the remaining capacity of the knapsack is 14. Therefore you can put the total first object here, right? After placing 1, then the remaining capacity will be 12 kgs, and because of which, what is the total profit I gained? Total profit I gained is 10 units. Therefore I am going to write 10. Got it? And next, what is the object? I have to consider 6th object. Go to the 6th object, and what is its total weight? 4. So can I add 4 kgs into the knapsack? Yes, because the capacity remaining is 12. Therefore I can add completely 4 kgs. So I am going to add 6. After adding 6, what is the remaining capacity? So see this, from 12 you have already added 4. So what is the remaining capacity? 8 units. Then what is the total gain in the profit? After adding these 4 kgs, you are going to gain a profit of 18. Therefore the total profit is plus 18, right? And next one I should consider is 3. If I consider object number 3, what is the weight of it? 5, right? What is the capacity remaining? 8. Therefore definitely I could add it. Therefore I am going to add it. Then after adding object number 3, then what is the remaining capacity of the knapsack? So object number 3 weight is 5. Therefore the remaining capacity will be 3. Then what is the total profit gained? Total profit gained is 15. Isn't it? Then what is the next object I should consider? 7. So see object number 7. What is the total weight of it? 1. What is my capacity? 3. Therefore I could definitely add completely object number 7. So I am going to add it. Then what will be the remaining capacity now? 1 weight is already added. Therefore remaining capacity is going to be 2, right? And what is the profit gain? Profit gain is going to be 3, right? After adding 7, the profit gain is going to be 3, right? And what is the next object I should find out? The next object is 2. So the next object, the weight is 3, but my capacity is 2. Therefore I cannot add completely. So this is where you should stop. Whenever any object cannot be added completely, you stop there and see how much could you wait, how much could you add. So my remaining capacity is 2. Therefore here the weight is 3. I cannot add 3 units, but I am going to add 2 units, because of which profit gain will be, if I would have added 3 kgs, profit gain would be 5, isn't it? But then I am adding only 2 kgs. So if I would have added 3 kgs, I would get the complete profit. Otherwise I will get only 2/3 of the profit, right? And now completely it is filled. Therefore it is, the capacity is 0. Last item added is 2. But then here I am not going to add the complete. I am going to add only a fraction of it. Okay. So that is what is being done. So what did we do? Given objects, I have found out profit by weight ratio and then sorted the objects in the profit by weight ratio, and then I have iterated over these objects and I'll see whether every object could be added or not. So what is the condition? The stack should have some empty space, that is first condition, and second condition is whatever you are trying to add, that should entirely fit into the stack, into the knapsack. Then only I am going to add it, right? If the knapsack is not having the capacity to get the entire object, I am going to stop there and then I am going to compute the fraction that could be added, isn't it? That is what this algorithm is doing. See this, for I equal to 1 to n from the sorted list, which means from this list I am going to see if the knapsack is having some free space. If it is having some free space, then I am going to add an object. While adding an object, I'm even checking that the entire object could be added or not. If it cannot be added, I'm going to break there, and next I'm going to check how much amount I could add, right? What, depending on the free space. So what is the remaining space? M, out of which, see, if I add Wi, I'll get profit Pi, but since I'm adding only M, I'll get a profit of M by Wi of Pi, right? So what is the total profit? If you sum it up, you are supposed to get 55.3. This is the total profit you are supposed to get, right? And what are the objects that are added? 5, 1, 6, 3, 7 and a fraction of 2, right? Now let's see the time complexity of this. Now for I equal to 1 to n, I have to compute Pi by Wi. What is the time taken for this? Since it is going to run for n times, the time taken is order of n. Then sort all the objects in non-increasing order of Pi by Wi. If I have n objects and if I have to sort them, what is the time taken for that? The best sorting algorithm, the best comparison based sorting algorithm known as merge sort. You can even think of heap sort also. So time taken will be order of n log n, isn't it, for sorting. And then I am going to do an iteration from I to 1 to n on the sorted list. So for which, in worst case, all these lines might run for n times, therefore time complexity for these lines is order of n, right? And finally this is a constant time, order of 1, right? So what is the total time taken? We have to add all these, n plus n log n plus n plus 1, which is nothing but the leading term or the dominating term is n log n. Therefore time taken by this greedy knapsack algorithm is order of n log n. This is the time taken by this algorithm, right? So one thing you should observe is, here I am sorting the list because I always wanted the value which is having the maximum value of Pi by Wi. So if I don't want to apply sorting algorithm, what is the other option we have? You can go for max heap, isn't it? So if I implement this greedy knapsack using a max heap, then how can you implement it? In order to find out, first thing is you have to build a max heap. So for that time taken will be order of n. So first thing is you have to build the max heap, and then every time you have to delete the max, isn't it? And how many times you are supposed to delete the max? Nearly n times, right? And every function call to delete max is going to take order of log n. Therefore I might have to call delete max n times, and every time it is going to take order of log n time. Therefore it is going to be order of n log n. Again, we didn't get any advantage compared to sorting. Okay, here you might think that if I am applying delete max on the max heap, how is it going to be log n all the time? Because we are actually deleting the elements, right? So first time it should be log n, second time it should be log n minus 1, and third time it should be log n minus 2, isn't it? So you might think that the time would be less than n log n, but if you analyze it, I'll just do it here. I'm talking about why n calls to delete max is still going to be n log n time. The reason is this. Let us say this is the heap, and we already know that it is a kind of complete binary tree or almost complete binary tree. Now we are going to, how are we going to apply delete max? We are going to take the last element, remove it and put the last element here, and we are going to call max heapify, right? And max heapify function is going to take order of log n. Now what is the time complexity for order of log n is, max heapify is order of height, which is nothing but order of log n. So for first time when I delete one element, the height of the tree is not going to change. The height of the tree is going to be, in the worst case, again order of n only, right? Order of log n only. So how many such deletions should I do before I change the height of the tree is nearly n by 2. So for nearly n by 2 calls, the height of the tree is going to be order of log n in worst case, and for the first n by 2, nearly n by 2 calls, every call to delete max is going to take order of log n. That is why the time complexity is going to be order of n log n, right? So for nearly order of n times, it is going to be order of log n, therefore it is going to be order of n log n. In case if you delete one node, if the height of the tree is going to change, then you might argue that it is not order of n, it could be less. Maybe you could say order of n minus 1. But then just by deleting one element, the height is not going to change much, right? So nearly after deleting n by 2 elements, in worst case, I am talking about the worst case, then in best case maybe by just deleting one element, which is the only leaf available in the last level, you might change the level of the height of the tree. But then in worst case, nearly you have to delete n by 2 elements in order to change the height of the tree. Unless you change the height of the tree, that delete heap is not going to change its time complexity. Therefore, even if you apply a heap for such a problem, it is going to take n log n. So there one more implementation is, what you could do is, for compute pi by wi and then build a heap for all the elements using the value pi by wi, and then instead of going traversing the list, what you could do is, for every time you could delete a max element and then you try to place it there. So both are going to take order of n log n time itself. Either you apply sorting or you apply heap, right? We shall see more examples on this. Now let's see one more example for knapsack. Given that m equal to 15, which means capacity of the knapsack is 15 units, and we have 5 items, and these are the weights of each item. Okay, so 1 unit, 4 unit, 5 units, 3 and 3, like that. And now the question is, what is the maximum profit we could get out of it? So what is the algorithm we have seen? Find out profit by weight ratio and sort the objects in profit by weight ratio, and then keep adding them one by one in a descending order, right? So what is profit by weight ratio? It is 2, it is 7, it is 5, it is 6, it is 3, right? So and now you sort them in a decreasing order. So if I sort them in decreasing order, the first one is object 2, isn't it? And the next one is object 4, and the next one is object 3, and next one is object 5, and next one is object 1. So 2, 4, 3, 5, 1 are the descending order of the profit by weight ratio, right? And now you keep on adding them one by one to the knapsack. So first let me add the object 2. So initially capacity of the knapsack is 15. If I add the object 2, what will be the remaining capacity? If I add object number 2, it is going to take up 4 units, therefore remaining capacity is 11, because of which I'll gain a profit of 28, right? And next one is I have to add a object 4. So if I add object 4, then my capacity is 11, therefore I can add 4, because 4 weight is only 3. So capacity of the knapsack will be reduced by 3, which means capacity of the knapsack will be now 8. And what is the profit I gain? 18, isn't it? And next I add object 3. If I add object 3, this one, then can I add object 3? Object 3 weight is 5 and my capacity is 8. Yes, I could add. Therefore let me add object 3. Then what will happen to the capacity? It will reduce, right? By how much? By 5. Therefore remaining capacity is 3. What is the profit gain I have? I am gaining a profit of 25, right? And next one is, let me add next object 5. So can I add object number 5? Object number 5 weight is 3 and I exactly have weight as 3. Therefore I could add object number 5. If I add object number 5, capacity is going to be 0, and what is the profit gain I get? 9. Therefore this is the maximum profit I get. And what are the objects that are added? 2, 4, 3, 5 in that order, and all of them put together weight is going to be 15. Therefore there is no chance that I could add any fraction here. So completely object number 1 is left out without even adding any fraction, right? Fine. Now one special interesting case of this knapsack is all of them have the same weight, isn't it? When all of them have the same weight, let us say 2, 2, or let us say 3, 3 or 4, 4, all of them are having same weight, okay? Then you need not sort them out. You need not find out profit by weight ratio and then sort them. You can directly sort them using the profits, because the if you divide these profits with the same number, obviously we are going to get proportional numbers, right? So if all the weights are going to be same, you just sort out the numbers using the profits and just go in descending order and you keep on adding them. Okay, that is a special case. Okay, now we shall see next model. And let's see the problem, job sequencing with deadlines. The problem is there will be some jobs given like this: job 1, job 2, job 3, job 4, and some profits associated with them, which means if I perform this job J1, I'll get a profit of 6. If I perform this job J2, I'll get a profit of 8, like that. So for every job some profits are given, and moreover some deadlines are given, which means from the starting point, if you perform this job within this deadline, then only you are going to get this profit. That is the problem statement. Okay, let me restate the problem again. Every job is going to take 1 unit of time to get completed, and if you finish one job, you are going to get this much profit. For every job there is profit associated with that. And next one is, but you will get this profit provided that you finish the job in this deadline. So how to measure the deadline is, from the starting point you have 0, and from there 1, 2, 3, like that, which means if I start at this point, see this, now this is 0, this is 1, this is 2, right? So every job is going to take 1 unit of time. So if you place J1 here, which means if you are performing job J1, then you cannot perform job J2 in the same slot. So every job is going to take 1 unit of time, and by the time you finish the job, you just look at the deadline, right? And if the deadline is met, then you are going to get the profit, right? So let's see how to solve such a problem. One approach is, we want to maximize the profit always, right? So how can I maximize the profit in this case is by choosing the jobs which are having highest profits. So which means this job is having highest profit, and next this job is having highest profit. So I want to do J1, J2 and J4. Okay, so first highest profit is J4. So if I place J4 here, isn't it? Next highest profit is J1. So already J4 is occupied, so only, sorry, J2, already J4 is occupied, therefore only space available is here, right? Now I have to place J2 here, isn't it? But if I place J2 here, the deadline of J2 is 1, but I am crossing the deadline of J2, so I will not get any profit. I cannot put it there, isn't it? Then what is the other one? Next possibility is this one. I'll try to put J1 here. Let me see if J1 is allowed. Is J4 allowed? Yes. J4 deadline is 2, and here the deadline is 1. So J4 is done within its deadline. Very well ahead of the schedule, right? Then what about this? What about this J1? J1's deadline is 2, and I am putting it before its deadline. Therefore, I am able to finish J1 and J4. Then what is the total profit I got? 16, right? But is this the only way possible, and is this the maximum profit possible? It turns out that we could do even better if I would have used some other way, isn't it? See? So what is the highest profit? J4. And what is this deadline? 2. Then place J4 as far away as possible. So don't place J4 here. The reason is, next jobs which has lesser deadlines may sit here, isn't it? So if I place J4 here, the highest one, placing it as far as possible. And what is next highest? J2. Also place it as far as possible. So only place is this one, right? Now this is one other combination. So if I go in this combination, then what is it? J4 and J2 are going to take 18 units profit, isn't it? And moreover, this scheduling is feasible, isn't it? Why? J4 is done within its deadline and J2 is done within its deadline, which is 1. So this is the highest profit, right? So what did I do? I had taken a job which is having the highest profit and I placed it as far away as possible, right? And then I had taken the next one, right? So let me explain you the same with more examples. So how many jobs are there? 1, 2, 3, 4, 5, 6. 6 jobs are there, but what is the deadline? 5, right? Therefore, how many jobs can I complete? I can complete only 5 jobs. So I am preparing a Gantt chart. This is also called as Gantt chart. Okay, and how many jobs can be placed? Totally 5 jobs. So this is 0, this is 1, this is 2, this is 3, this is 4, and assume that this is 5. Okay, now again let's use the highest profit model. So what is the highest profit here? Highest profit is 300, right? So if I put 300 right in the beginning, then I might face some problems later. So see, one way is if I directly take 300 and if I put J4 here, right? And now what is the next highest profit? Next highest profit is, I think, 190. 200 is there. 200, right? Then what is the deadline for this one, J1? Deadline is 5, but then if I put it here itself, then I get J1 here. Yes, deadline is 5, but I'm finishing it by deadline 2, right? I mean by time 2. Therefore, I will get this profit also. Then what is the next highest? Next highest is 190, right? So 190, what is its deadline? 3, and is that slot available? Yes. Therefore, I am going to put J3 here, right? And what is the next highest? Next highest is J2, isn't it? Now what is its deadline? 3, but then all these slots before 3 have already been occupied, so I'll not be able to place J2. Then what is the next one? Next highest profit one is 120, right? So what is its deadline? Deadline is 4, so I can put it here, right? So if I put it here, what do I get? Deadline is 4. So what is the profit? J5. Then I get the profit of 120. What is the next one? Next one available is 100, whose deadline is 2, but then the slots 1 and 2 already occupied, so I cannot place J6 here. If I put J6 here, it means that I am performing it after its deadline. So after its deadline, there is no use even if you perform the task. So only these are the things I got, right? So what is the order I followed? I have taken the maximum profit and I sorted them accordingly. Obviously, we have seen that this is one order we got, and we didn't get 5 jobs. Let me follow the other order. What is the other one? I am not going to place the highest profit one in the beginning slot, in the starting one, right? I'll place it as far as possible. See this? So first one is, I'll take the job with the highest profit. So what is the job with the highest profit? This one, isn't it? Then I'll place it as far away as possible. So J4 will be placed as far away as possible. So what is the worst case slot in which I could execute it? Slot number, by deadline 2, which means here, J4. I cannot go beyond it. Why? Because it will be crossing its deadline, right? So J4 has to be placed here. What is the next highest? Next highest is 200, isn't it? So if I take this, then what is the worst case slot in which I could place? Here, isn't it? So J1 can be placed here. The reason is I need this deadline is 5, and I need not go beyond it. I'll be able to finish it by its deadline, right? And what is the next highest? Next highest is 190, isn't it? Then what is its deadline? Deadline is showing as 3. Therefore, I could place it. The worst case placement of J3 is here. Done. Right? And what is the next one? Next highest is 180. Previously we were not able to put 180 anywhere, right? But now I am able to put this. See this? Now what is its worst case? Its worst case deadline is 3. So can I put it here? No. Can I put it here? No. But this space is available. Therefore I can put J2 here, isn't it? So J2 can be placed at this point, right? And what is the next available? Next available is 120. So can I place what is the deadline of 124? So is there any slot available from 4 onwards? Yes, this slot is available. So I can put J5 here, right? So obviously I am able to do more jobs, if I follow this order. So what is the order? First place them in the descending order of profits. Take the job with the highest profit and place it as far away as possible, right? That is the method I used. So what will be the time complexity for such algorithm? First thing is, look at the deadlines and see the maximum deadline and you create that array. Yes, I created it. And next thing is, you sort out the jobs. If there are n jobs, in order to sort them out, how much time does it take? Order of n log n. Sort out all the jobs and then take each job and then start from the point where its deadline is given. If its deadline is given as let us say 5, then you start from this slot and you keep searching for a vacant location. If you find any vacant location, you are going to place it there, isn't it? So there are n jobs and for every job I might have to search n slots. Therefore total time in worst case will be order of n square. Again, listen to this. How does the algorithm work? First step is, I am going to create a this array whose size is equal to the maximum deadline given, which means 5. For that, constant time is required. And second thing is, I am going to sort out all the jobs based on the profit. So sorting, if there are n jobs, then sorting is going to take n log n time, right? And then I'll take the jobs one by one in the decreasing order of profit, okay? And I'll try to find what is the placement. So how do I start it? I go to the worst case, which means the deadline of it, and from there onwards I'll keep on searching for a empty slot. In worst case, I might end up searching all the n cells, isn't it? Therefore I am going to take a time of order of n. For every job I have to search, and searching is going to take n. Therefore the time complexity for such an algorithm could be order of n square, right? Let's see more examples on this. Let's solve next two problems. See, one problem is this. They are given profits and deadlines, and now let's follow the algorithm. So first step is, create an array whose size is equal to the maximum deadline. So maximum deadline given is 4. Therefore, how many jobs can you complete in 4? Maximum is only 4, but how many jobs are given? 5. You have to choose what are the jobs that you have to take and what is the sequence in which you can finish them, right? It is not always possible that even if you have chosen the jobs, you could finish them. Therefore, even the placement is also important. So for that reason, I have to create the array. So what is the array? Array size is going to be 4, right? 0, deadline is 1, 2, 3, and deadline is 4. Yes. So now I have constructed an array with deadline 4, and I could place only 4 jobs in this, right? So let me take, next step is, you have to sort out the jobs in the descending order of profits, right? So just see the profits and then sort them out. So what is the highest profit one? J5, isn't it? J5, first one. And what is the next highest profit? J5 and J2. What is next highest profit? J3. What is next highest profit? J1. Next one is J4, right? So I have sorted out all the jobs in the descending order of profits, right? And now you take each job one by one and you see where we could place it without where we could place it in the schedule. So I have to place J5. Where can I place J5? Come in the descending order of the start with the deadline and come in the from right end to the left end. So what is the deadline of J5? J5 deadline is 4. So start from the 4th point and you try to place it there. Can I place it there? Yes, it is available. Therefore I am going to place it there, right? And what is the next available one? J2, right? So where can I place J2? See this, the deadline is 3. Therefore you have to start from here and you have to go on to the left. So J2's deadline is 3. Therefore I can definitely place it here, J2. Isn't it? And now what is the next one? J3. Just see the deadline of J3. Deadline of J3 is 3, which means I have to start from here and I keep searching, and wherever I get an empty slot I am going to place it. Therefore J3 has to be started here, and here I got the empty slot. So I am going to place J3 here, right? And what is next one? J1. So what is the deadline of J1? J1 deadline is 3, which means I have to start from 3 and I have to go to the left side. So when I am going to the left side, I got J1 here, isn't it? And that is all. So J4 is left out. So J4 cannot be placed anywhere, right? Because all the 4 slots are filled. Now what is the profit that we get is, J1's profit is J1 is done, therefore profit is 2, and J3 is done, therefore profit is 3, and J2 is done, profit is 4, and J5 is done, profit is 10, right? So if we add all of them, the profit is going to be 19. That is the maximum profit we get. You use any other method, we will not get more than 19. Okay, that is how the algorithm is done, right? So what is the algorithm? First create an array. So what is the time taken? Order of 1. Next you sort all the jobs. So what is the time taken for sorting? Order of n log n. And next thing is you have to take each job one by one, which means I have to take n jobs and then find the slot. How am I finding the slot is I am starting from its deadline and at the right, and I am moving to the left. In worst case, its deadline could be given as the last cell, which is nth cell, and I might go till the first cell, which means I might have to traverse n in worst case, right? Therefore it is going to be order of n square. For every job I might have to do this n times, right? Therefore it is going to take order of n square time. The algorithm is going to take order of n square time. Now it is going to take order of n square time provided that the number of cells are also equal to n, isn't it? It may not be equal to n, but it will be close to n. So one thing is, there is no way, if one of the job is going to have a deadline of 100, you need not have that 100th array, a of 100. The reason is, just see how many jobs are there and you could limit the size of the array by the maximum. See, if I have 5 jobs, even if the deadline is let us say 100 for the 5th job, I need not create a array of 100 and then place it at the end. So what you could do as a minor modification is, first of all, in the question we are not going to get deadlines very larger than number of jobs available. The reason is it is meaningless, right? So always we are going to get deadlines less than the number of jobs available or very close to the number of jobs available. Then the size of the array is going to be order of n. That's it. Even if the deadline is very high, you need not create that big array. So you could even write a small line saying that if number of jobs is less than the highest deadline, then you could limit the size of the array with the number of jobs, which is n. Okay, fine. Let's see this. How many jobs are there? 9 jobs are there. And what is the maximum deadline? 7. So even if it is possible to place all the jobs, I'll be able to do only 7 jobs. The reason is, beyond 7 there is no point in performing that job. We will not get any profit, right? So maximum possible jobs present in this will be 7, even though 9 are given, right? Now first step is you create an array whose size is equal to the deadline of the maximum job, isn't it? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is the maximum deadline available? 7. So only 7 are required, 8 and 9 are not required. So always see that this array size will be less than n. Therefore even if I write order of n square, it doesn't hurt, right? And next step is sort out all the jobs based on the profits. So which one is having the highest profit, or write them in the descending order of the profits. Which one is having highest profit? The one with the highest profit is, I think, J3, isn't it? J3. And the next one is the highest profit is, after 30, I think 25, right? J9. And next one is after 25, I see 23, J7. So I'm just sorting it out, okay? And after 23, I see 20, which means J2. And after 20, I see 18. So J4 and J5 both are having 18. And after J4 and J5, I see 16, which means J8. And after 16, I see 15, J1, and then J6. So first you sort out all the jobs, create the array, constant time, and then sorting out order of n log n. And now you take one by one job. So you run a for loop for all the jobs in the sorted order. Now I'll pick J3, right? J3 is picked up and I'll see the deadline. So what is the deadline for J3? deadline is showing as 5, which means it could be placed as far as 5, which means you have to start from this cell and you have to traverse all these cells until you find a empty cell, isn't it? So in worst case, for every job, I might start at the beginning and I might traverse till the ending. That is why I am saying the algorithm is going to take order of n square, right? Now for J3, deadline is 5, isn't it? Therefore, we are going to place it for J3. I am going to put J3, right? So we are going to start it from here. So I am going to place it here. Since the cell is available, I am going to place it. Next one is J9. Just see J9. What is the deadline? Deadline is 3. So where are we going to place it? We have to finish it by 3. Therefore, I am going to place J9 here, right? And next one is J7. So what is the deadline for J7? J7 deadline is 2. Therefore, we are going to place here, right? And next one is J2. So what is the deadline for J2? Deadline for J2 is 2. Therefore, I have to start from 2 and keep traveling to the left side. And whenever I get an empty slot, I am going to put it there, right? So J2 deadline is 2 here, and I am going to come down. So J2 can be placed here, right? And next one is J4. So see where J4 can be placed. J4 has a deadline of 3, which means I have to start from here and I have to search for all this. And now it turns out that J4 cannot be placed anywhere. So J4 is not possible, right? And now what about J5? J5 deadline is 4, which means I have to start from here and I have to travel all of them till I get the empty slot. So empty slot is present here. So I am going to place J5 here, right? And next one is J8. What is the deadline of J8? 7, isn't it? So I can place it right here. So J8 is placed here, right? And what is next one? J1. So where can I place J1? Just see the deadline of J1 is 7, which means I can start from here and I can come till the left, and I found out that I could place it here. So J1 is placed here. What is the next one? J6, right? So what is the deadline for J6? 5. So from here, even if you start, I cannot, everything is full. So I have filled all the 7 jobs. So only 7 jobs can be kept in the at max, and I have filled them all the 7 jobs, right? So what is the total profit we have gained? Total profit we gained is from all the jobs that could be sequenced here, right? So what is the profit for 3? For J3 profit is 30, plus for J9 what is the profit? 25, plus for J7 what is the profit? 23, for J2 what is the profit? 20, and for J5 what is the profit? 18, and for J8 what is the profit? 16, for J1 what is the profit? 15, right? So that is how I got the profits. So the time complexity for this algorithm is going to be order of n square. Okay. This is the Dijkstra algorithm I have taken from the Coreman book. So I'll explain you what are these steps. What about each step? I think you have already seen the examples. From examples you understood that initially we are going to have all the vertices with some numbers in it, which means this source is going to have 0 and all the other nodes are going to have infinity. That is what we have seen. And later what did I do? I am going to take the node with the least weight, which is nothing but 0, and then I am trying to relax the edge of every outgoing edges. I am trying to relax them, isn't it? So how am I going to implement it? Is heap is the best implementation. I am going to put all the vertices in the heap, and then whenever I try to relax any edge, actually relaxing is nothing but decreasing the distance of the node, which is nothing but decreasing the key. Decrease key operation of the min heap is nothing but relax operation here. If we implement it as a heap, right, then how much time? Okay, let's see one by one, step by step, what is happening here. Initially they are saying that initialize g comma w. Before that a graph G is given. So from G you can understand how many vertices are there and how many edges are there. And then a W is given. W is nothing but the weight matrix. Weight matrix means what is the weight of every edge. And S is given. S means the source. What is the source? And now initialize single source G comma S. They are saying that first before you do anything, just initialize the values. So what does it mean is, if we have a graph like this, so we did it, the source is taken as a value 0 and all the other nodes are taken as values infinity. It is initialization. So So initialize the single source, which is nothing but give the values to every node. And second one is, oh, capital S is not the source. Actually, capital S is a set which contains set of all vertices whose shortest paths have been decided. So initially there will be no vertex whose shortest path is actually decided. Okay. Later we shall slowly decide, take one by one edge vertex and keep adding to the S. And then Q equal to G comma G dot V. So we are going to build a heap with the vertices as the members of the heap. It is nothing but build heap. It is build heap method, isn't it? And we know that build heap method is going to take order of n if n is the number of elements, and in this case order of v because v is the number of vertices. While Q is not empty, after adding all the vertices to the Q, we are going to take out one element from the Q each time as long as there are elements in the Q. While Q is not empty, U equal to extract min. Extract min is nothing but I am taking the smallest one. This is the first one. So this one will be deleted from the Q. It will not be in the Q. And add that to the set of vertices whose shortest weight is already found out. That is logical. Which means I am taking out a value from the Q and adding it to the set which says that its shortest path has already been found out. And then for each vertex V adjacent to V belongs to G adjacent to U, which means once you have taken this, now whatever vertex is adjacent to this, you are going to relax them. That is what they are doing. So simple, the way we did on the algorithm, that example, the same way they are doing it, but then they are doing it using a heap so that the operations can be easier. Okay, so they are taking the minimum one which is 0 and then they are relaxing every adjacent vertex. So if I relax it, let us say from infinity this value drop to 2, and if I relax this, let us say from infinity this value drop to 10. The reason is 10 and it is 2. It is what has happened. Then what happens again? Again we will go back and Q is not empty, right? And these values are 2 and 10 in the Q. Therefore the next time minimum value will be 2, and when we extract min next time, the next one with the minimum value will come out, and again we are going to do the same. Take it out from the Q, add it to the S, and whatever are the nodes adjacent to this, again we relax them. We keep on doing it, and whenever we relax them, these values will change, right? And again we take the minimum one and again we relax. That is what is happening. For that we are going to use the heap. Now how to analyze the time complexity of this? We shall use some kind of aggregate analysis. Aggregate analysis is, I'll see what are the main operations that are involved in this algorithm, and then I'll count how much time is taken for each activity, and then I'll see how many activities are there. Okay, see, simple. I'll just write down each one. What are the main activities in this? First one is initialization. Initialization means writing all the nodes to infinity, which is going to take order of V time. So we don't worry about it. It is very less time. And next one is S equal to 5. No, not much. And next one is build heap. Build heap is going to take again order of V. Why? We are going to add V vertices to the heap. If we have to build a heap from the scratch, the time complexity is order of n, I told you. And now here we are going to build a heap from scratch for V vertices, therefore time complexity is order of V. And next thing is extract min is going to be used. That is an operation, right? So extract min is going to be used, and extract min time complexity is order of V if there are V elements in the heap. Therefore in worst case there will be V elements in the heap. So in worst case time complexity for extract min is order of V. And next time we are going to do relax. Relax operation means if there is already a node inside the heap, and when we relax, what happens is the weight of the node in that heap is going to decrease. It is nothing but decrease key. So the relax operation in general comes down to decrease key operation inside a min heap. Okay, so I hope that you are getting this point. The reason is whenever you try to relax, the distance of a node is going to reduce, isn't it? And if this node is already in the heap, and whenever you reduce the value of a node in the heap, then that is actually decrease key, right? So one more operation we have is decrease key, right? Now let's see how many times and what is the time taken for decrease key. Oh, extract min is not order of v, right? Extract min is order of log v. Sorry for that. Extract min is order of log e. You please refer to that heap concept. And decrease key is again order of log v. Either you want to decrease the key in a min heap or extract the min, both time is going to be order of v. Now the entire time complexity of the algorithm depends on how many times these operations are actually performed. So how many times are you going to extract the min? We are going to extract the min until q is not equal to empty, which means until there is one element in the queue. Even if there is one element in the queue, we are going to extract that element. Therefore, how many elements are extracted one after the other? Totally v elements are there. All the elements have to come out of the heap. Therefore, v times I am going to apply this operation. So the total time complexity for extract min is order of log v into v, which is nothing but order of v log v. And what about the decrease key? How many times are you going to apply a decrease key? That depends on how many times we are going to look at a vertex from some other vertex, isn't it? So if you count the number of times we apply this decrease key, that depends on the total number of edges. So I'll just tell you few points. You just think whether it is right or wrong. See, now the number of decrease keys is equal to the number of relaxes, isn't it? Because relax is the operation which is going to call decrease key. And now the number of relax operations is equal to the number of edges, because in worst case every edge will be relaxed at least once. If you look at that graph in the previous examples, I have relaxed every edge at least once whenever I see the originator of the edge. If an edge is from v to w, then whenever I see v, then I am going to relax the edge which is going out from v, isn't it? Therefore, every edge is going to lead to a relax, and every relax is going to lead to a decrease key. Therefore, the number of decrease keys is actually equal to the number of edges. Therefore, the number of extract mins is equal to the number of edges. So, overall, how many times are you going to decrease the key? That is equal to the number of edges. Therefore, the decrease key operation is performed, that is equal to the number of edges, right? So extract min is performed v times and decrease key is performed d times. So what is the total time complexity of this algorithm? Order of, to initialization it is v, the first step, and then to build the heap it is v, and then extract min is actually performed v times, and each extract min is log v, therefore it is v log v. And then decrease key is, I think this point is very difficult to understand. Maybe please try it. See, relaxing is done on edges, and every edge is relaxed at least once, exactly once. Every edge is relaxed exactly once. Therefore, the number of relaxations will be equal to the number of edges, and every relax in worst case might lead to decrease key. It is not sure that every relax is going to decrease the key, but then in worst case every relax might lead to a decrease key. So in worst case, how many decrease keys would we have been called is, that is equal to number of edges. Number of edges equal to number of relaxes. Number of relaxes is equal to number of decrease keys. Okay, so I don't know whether you are following it or not, but please watch this video once again and watch the examples once again. You will understand this point. Therefore, for this decrease keys, the time complexity is e into log v. Got it? So this is the entire time complexity of Dijkstra algorithm. The leading term in this is e log v. The most significant term is e log v. All these terms are actually less than this. Therefore, you can say that order is e log v when we implement Dijkstra algorithm using a min heap. Generally, all the implementations are done using min heap. If you use any other algorithm, any other implementation, sometimes it might be better like Fibonacci heaps, but Fibonacci heaps is not in the gate. In case if I have time at the end, I will discuss about Fibonacci heaps, but it is not in the gate syllabus. But for now, you just fix yourself to this. Heap is used and Dijkstra complexity is order of e log v. Got it? There is always no guarantee that you will be able to find out the shortest path in every graph. So for some of the graphs, even though there is I'll just take an example and explain you. See, first thing is, if there is no path between the source and the destination, which means if the graph is disconnected, there is no way that you will be getting a shortest path from the source to destination. That is one thing. So in case of disconnected graph, there is no way we can find out the shortest paths. So first thing is, if the graph is connected, then only we can apply any shortest paths algorithms, any shortest anything, right, any algorithm. And second thing is, even if the graph is connected, there is no guarantee that we will be able to find out the shortest path in case if there are negative weight cycles involved. I am not talking about the negative weight edges, I am talking about the negative weight cycles, which means in case if there is a negative weight cycle, then we will not be able to find out the shortest path. I'll just give you an example and explain you. Assume that there is a source here, S, and it is going through A, B, and there is a destination D. Now I want to find out the shortest path from S to D. So if the weights are like this, 1, 2, minus 1, negative weight, right? So let's see what happens. What is the shortest path, shortest distance to D? So from S to this 1 plus 2 is 3, and 3 minus 1 is 2. Therefore shortest path to D is 2. So we can find out the shortest path to any node in the graph, even if there is a negative weight edge present. Therefore negative weight edges doesn't mean that if you see a negative weight edge, you cannot say that we cannot find out the shortest path. Even with having a negative weight edges also, we will be able to find out the shortest path. But only problem arises when there is a negative weight cycle. For example, if I have 1, 2, 3 here, and here there is a negative weight minus 3. Now see this, there is a cycle and the cycle weight is negative, right? So let's see what is the problem with this. So if you don't take the cycle at all, and if you go from S to D on a straight path like this, the total weight is going to be 1 plus 2 plus 3, which is going to be 6. So 6 is the minimum weight, right? But then in case if on the way, while going from S to D, if you take the cycle once and again you continue the journey, then the weight is going to be decreased. See this, from S to A it is going to be 1 and A to B 2, and from here to here minus 3. See, 1 plus 2 is 3 and 3 minus 3 is 0. Therefore the shortest path to A is now 0, not 1, isn't it? So shortest path is actually getting affected. It is 0, and 0 plus 2 is 2 and 2 plus 3 is 5, right? So here the shortest path is now 0, and here the shortest path is now 2, and here the shortest path is 5, right? In case if I would have taken this loop 2 times, then what happens? Then it is 1 plus 2 is 3, and 3 minus 3 is 0, and again 0 plus 2 is 2, and 2 minus 3 is minus 1, which means this is going to be minus 1, and minus 1 plus 2 is going to be 1, and 1 plus 3 is going to be 4. Therefore the shortest paths of A, B, C, A, B, D are going to be decreased the more times I take the loop. So it will be like this. Next time it will be minus 2, next time it will be minus 3, next time it will be minus 4, here it will be 0, minus 1, minus 2, and here it will be 3, 2, so on. So it will keep on decreasing, right? So you cannot stop at any point and say that, see, I got this number and this is the minimum. Even if you come up with such an answer, what I'll ask you is, why don't you just go and take the cycle one more time, you'll get a better path. Then you'll keep on taking it. Therefore there is no way you can find out the shortest path in this. You cannot say that minus infinity is the shortest path. Minus infinity is not a number. By saying that we can find out the shortest path, what I mean to say is, you should come up with a number, not with minus infinity, right? So for the graphs which contain negative weight cycles, there is no way you can ever find out the shortest path. But for the graph which contain negative weight edges, there is a way. I mean, for some of the graphs it is possible, which means, see, previously I gave you this example, right? So if I have something like this, here 1, 2, minus 1, something like this, even though there is a negative weight edge, you will be able to find out the shortest path. But here, even though there is a negative weight edge, you will not be able to find out the shortest path. Therefore, having a negative weight edge doesn't say anything. I mean, you cannot say that if there is a negative weight edge, it doesn't imply that you cannot find out the shortest path. But if there is a negative weight cycle, you can definitely say that there is no shortest path possible, right? So the algorithms which will work well when there is negative weight edges, the algorithms which could differentiate between two cases, which means if your algorithm has the capacity to differentiate between these two cases. What are the two cases? Negative weight cycle is present and negative weight cycle is not present. If you have an algorithm which has the capability to differentiate between these two cases, then such an algorithm can happily allow negative weight edges, because at the end it can find out there is a negative weight cycle, therefore the answers which I gave you is wrong, which means therefore there is no solution. But then if your algorithm does not have the capacity to say that there is a negative weight cycle, and if you take such an algorithm and give it a graph with negative weight edge, it will give you wrong answers. Dijkstra is one such algorithm. Now the problem with Dijkstra is it does not have the capacity to say that there is a negative weight cycle. Therefore, if you give it a graph which is having negative weight edge but then no negative weight cycle, it works fine. Whatever answer you get out of Dijkstra is right. But then if you give it a graph in which there is a negative weight edge as well as there are negative weight edges as well as negative weight cycles, what it will do is it will give you some answers. In that case, actually answers might not be possible. The reason is negative weight cycles will never give you shortest paths, right? But then Dijkstra does not have the capacity to differentiate between these two cases, negative weight cycle and no negative weight cycle. Therefore, it is better that you avoid negative weights completely in Dijkstra algorithm. That is the reason in Dijkstra algorithm people don't allow negative weight edges, because it does not have that capacity to differentiate it, right? But it doesn't mean that negative weight whenever a graph has negative weight edges, Dijkstra completely fails. It is wrong. In case if there is a negative weight cycle, it fails. In case if there is no negative weight cycle, it gives the right answers. Therefore, some of the graphs in which there are no negative weight cycles, you can happily apply Dijkstra algorithm and it will give you correct answers. Okay. Let's take some few examples of graphs which are having negative weights, and when the Dijkstra algorithm is applied, let's see how the algorithm works on that. So I'll take small examples and then we shall complicate it. So assume that this is a directed weighted graph, and we have three nodes. I'm taking a simple example just like that, A, B, C, and here the distance is 10 and here the distance is -1, negative weight. I allowed the negative weight for the Dijkstra algorithm. Let's see how the Dijkstra algorithm behaves. So initially, as you know, we start with the nodes which are having, we start with the nodes in the heap like this, A, B, C. So you can think of it like a heap. I am not actually giving you the heap, I just wanted to represent it like this. Now we know that initially A will be having 0 and all the remaining elements, all the remaining vertices will be having infinity, which means the distance of the shortest path from A to A is 0 and all the others we don't know yet. Then what is the first thing we do is, if this is the heap, if heap contains all these elements, we always keep on deleting the minimum one, right? So what is the minimum distance one here? A. Therefore we are going to delete A first. Yes, we are going to delete min. So that is the operation that we are performing on the heap. And now once we delete the min, then what is that we are going to do next is, we are going to relax all the edges, outgoing edges from A. Therefore if I relax the outgoing edge from A, only one outgoing edge is there. We have to relax it provided that the other element is in the heap. Yes, the element B is in the heap, therefore I am going to relax it, right? So when I relax it, the value here is going to be 10. So only one outgoing edge and one that is deleted, there is a decrease Q operation correspondingly on the B, right? And next we are going to find out the next minimum. So what is the next minimum? Minimum is B, and again we are going to delete it. So when I delete it, then I get the value of when I delete it, it means that see, one more thing, whenever we are deleting the element from the min heap, we are doing it under the assumption that we have already found out the shortest distance for that element, for that node, and we are not going to consider it for further investigation, which means later on there is no way that we are going to get a better path next. If you have now here, if I deleted the element with 10, it means that later on there is no way I could get a distance which is shorter than 10 to the node B. That is what you should keep in mind. Okay, and now B is deleted, and whenever we delete any node, we are going to relax all the edges outgoing, provided that the other node is inside the heap. Now outgoing edge is this one, and the other node is already inside the heap. Therefore you decrease you again relax it. So when I relax this edge, then what is that I am going to get? Here the value is already 10, here the value is 0. Therefore if I relax it, the value I get is 10 minus 1 is 9. So 9 is what I get. And finally you have to delete it. So once I delete it, there is nothing to relax, no more nodes. So that is how our algorithm works. Therefore Dijkstra algorithm in this case has actually worked fine. It found out that the shortest distance from A to C is 9, right? So then why are we not allowing negative edges? I'll show you some examples why we should not allow negative edges in the Dijkstra algorithm. So the reason is this. Let's take one more example, small example, and investigate it further. A, B, C, say D. I have 4 nodes, 1, 2, 3, and assume that I have a negative weight which is -4 from D to B. Okay. So now what happens is Dijkstra algorithm works this way. Initially A, B, C, D will be in the heap. A, B, C, D will be in the heap, right? And initially we initialize the values of A, B, C, D as A has 0 and B, C, D as infinity, 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 which means we don't know the distance to B, C, D, but then the shortest path from A to A is 0. And now we perform delete min. So when I perform delete min, the first node which is going to be deleted is A. Yes, that is deleted. And now we take all the outgoing edges from A and we relax them, right? So if we relax them, can I relax this? We can relax the edge only if the other end of the edge is already in the heap. Otherwise min heap is not, decrease min is not possible. If it is already decreased from the heap, then we cannot do it. That is why the other end B has to be in the heap. Then only I am going to decrease the key. So if I relax it, so already it is infinity. So if I relax it, it is 0. 0 plus 1 is 1. I got 1. So only one edge to be relaxed, and these values they remain unchanged, untouched. And next thing is we are going to delete B, right? So whenever I delete B, it is under the assumption that the shortest path to B is 1, which is already found out, and later it is not going to change. That is a mistake where I know that is the reason why Dijkstra fails with the negative weight cycles. I'll show you. And now we have taken this B and find out all the outgoing edges. Only one edge is B to C. You have to relax it. So here the value is 1. I have to relax B to C edge. But then is C already in the heap? Yes, C is in the heap. Therefore you can relax it. So what do I get? 1 plus 2 is 3. Therefore for the value of C I get 3. And what about D? It remains same because there is only one outgoing edge. That is why I relaxed it. So now there are only 2 elements in the heap. One is C, other is D. Which one is having minimum? When I do the delete min, then the node which comes out is C. So when C comes out, you have to relax all the outgoing edges from C. So what are all the outgoing edges from C? Only C to D, and then D is already in the heap. Therefore you can relax it, right? So when I relax it, when I delete it, the distance to C is already, minimum distance to C is already found out. That is what is the assumption, right? Now 3 plus 3 is 6. So when I relax it, I get a value of 6 here, right? Therefore next one which is going to be deleted is D. So when I delete it, I get 6 here, and now I have to relax all the outgoing edges from D. So I have to relax this edge, but then B is already deleted from the heap, isn't it? Now B is already deleted from the heap. Even if I relax this edge, what do I get is 6 minus 4 is 2, but already found out distance to B is 1. But now if I take from D to B, the value is going to be 2. Therefore in this case we are not going to relax it, and moreover the reason why we are not going to relax it is B is not in the heap. That is why we are not going to relax it. And moreover, even if I relax it, then also it is of no use because already we got the shorter path and it is not going to be of any use. So in this example also we are able to find out the shortest path correctly even if there is a negative weight edge, right? But then just examine what happens, what would have happened in case if this is not -5, -4, it is -6. In this case just check what happens. Now in case if I reach D by taking a distance of 6, and again if I go back to A, B by taking 6 plus 6 minus 6 is 0, isn't it? Therefore if I go from D to B, there is a better shorter path whose value is 0, but our Dijkstra doesn't consider it because it has already deleted B as if its value is already known and it is not going to change later. But then we found out that even after deleting element from the heap, there is a chance that we might get a better shorter path in case if there is a negative weight edge. Actually it is not just a negative weight edge, it is a negative weight cycle if you see it, right? So therefore because of the negative weight cycle, it is not just B, the shortest weights are going to be changing and we will never be able to find out the shortest weight paths, right? So if you apply Dijkstra algorithm on this question with -6 here, you are going to get the distances as 0, 1, 3, 6. In fact, the shortest path doesn't exist at all. The reason is the shortest path from A to B could go to -infinity. You can keep on decreasing it, and the shortest path from 0 to C, it too could go to -infinity, and shortest path from A to D, it too could go to -infinity. Therefore if there is a negative weight cycle, even though there is a negative weight cycle, our Dijkstra algorithm is stopping and saying that the shortest paths are 0, 1, 3, 6. It is completely wrong, right? But then it is going to work well in case if you don't have any negative weight cycle. In case if you have -4, it works well and your answers are right. All these answers are right in case if it is -4, which is a negative weight edge. Therefore having just a negative weight edge is not going to lead to a incorrect result in Dijkstra algorithm. But why are we actually not considering negative weight edges is our Dijkstra algorithm that does not have capacity to find out that there is a negative weight cycle, because of which it will give you the answer as if the answer is right. In fact, the answer is wrong in case if there is a negative weight cycle, and since it is not able to find out the difference, we are completely avoiding negative weights at all. Completely we are avoiding negative weights, right? So in this case it is going to work well, and in this case also Dijkstra algorithm is going to work well if it is -4. It is not going to work if it is -6. So remember that Dijkstra algorithm works fine for some examples where there are no negative weight cycles, and it fails for the examples where there are negative weight cycles, and there is no way Dijkstra algorithm will differentiate between these two cases. That is why we are completely eliminating negative weight edges. Okay. Now let's talk about Bellman-ford algorithm. Bellman-ford algorithm has the capability to find out whether, it's very simple, understand it, to find out whether a graph is having negative weight cycle or not. So whenever you give a graph to the Bellman-ford algorithm, let us say this Bellman-ford algorithm, now whenever you give it some graph as the input, then it has the capacity to say no, I cannot find out the shortest path because there is a negative weight cycle. It can say no, negative weight cycle is present, or it has even capacity to say yes, I can find out the what is shortest path because there are no negative weight cycles, and then it can even give you the shortest path weights also. Got it? So Bellman-ford has this special feature that it is able to detect whether there is a negative weight cycle or not. So any algorithm which is having this special feature can handle even the graphs which are having negative weight edges. Therefore you can give a graph which is negative weight, which contains negative weight edges, without even worrying whether there is a negative weight cycle or not. Just it is not like Dijkstra. In Dijkstra you should even think whether there is a negative weight cycle or not before you give the algorithm to the graph to the algorithm. Therefore Dijkstra might fail whenever there are negative weight edges, in some cases when there are negative weight cycles, but Bellman-ford will work even if there is negative weight edges with a negative weight cycle. Got it? And now it doesn't come with all the benefits. So the other disadvantage is, compared to that Dijkstra algorithm, Bellman-ford is bit slower. So the time complexity of Dijkstra algorithm is better compared to Bellman-ford. And moreover, in many of the practical algorithms, we always generally we have positive weight edges. We don't have negative weight edges in many of the real-time scenarios. For example, if you are laying down the roads, then the length of the distance of the road, or if you are trying to construct a computer network, then between two routers, the delay. So these values are going to be positive. So Dijkstra is widely popular and widely used. The reason is it is more practically applied to positive weight edges. So even though it is not able to work with negative weights, but still many of the problems are positive weights. Therefore Dijkstra is very popular compared to Bellman-ford. But in case if you have a negative weight this cycle or negative weight edges, always go for Bellman-ford, but the time complexity is more. Now Bellman-ford basically works on this rule that if you have a graph with n nodes, then the shortest path in the graph will never contain more than n minus 1 edges. Okay, which means if I have a graph with 3 nodes like this, then the shortest path will never contain more than 2 edges. Either let us say this is A, B, C. A to B distance will be containing, the shortest path will be containing one edge which is A to B, or it will contain one edge which is A to C, C to B, which means what I mean to say is our shortest path is never going to contain more than n minus 1 edges. So in case, okay, what happens if I have n nodes and I have a path in which I have n nodes and n edges, I have a graph. Just think about it. If I have 3 nodes 1, 2, 3 and it is a simple graph, which means there are no self loops. 3 nodes I have and then 3 edges like this, right? Then definitely there is a cycle. So if whenever you have n nodes and n edges, the problem is definitely there will be a cycle possible with these n nodes and n edges, right? And now if your shortest path is containing n nodes and n edges, which means the shortest path is in fact a cycle. If cycle is the shortest path, what you could have done is you could have removed one of the edge and then you could have got a better shorter path, provided that this cycle is positive weight cycle. In case if there is a negative weight cycle, obviously we cannot find out the shortest path, isn't it? So I am talking about the case in which there are no negative weight cycles, only positive weight cycles are there. And now I am talking about the thing that in case you have n edges or n nodes, then at most n minus 1 edges are enough in the path, right? I'll just take an example and I'll tell you how our this Bellman-ford algorithm works. It will give you a better idea. Say we have 3 nodes like this, A, B, C, and the the distance is, this one is 4, this one is 1, this one is 2, right? So you know that if I have to find out the shortest path from A to B and C, or I'm more interested in finding out the distance from A to B, you can find out that in one edge the shortest path possible is 4, but in 2 edges the shortest path possible is 3, right? So anyway, now let's see what happens if I apply Bellman-ford algorithm. Bellman-ford algorithm says that if you have n edges, n nodes, 1, 2, 3, 3 nodes, then relax every edge n minus 1 times, which means you have to relax every edge 2 times here. Okay, but how does that concept work is, I'll just tell you here. So now we are going to start with 0 here, and then B is infinity. This is how we are going to start, and then C is infinity, right? And these are the edges, 4, 1, 2, right? So I'll just put them down here, A 0, B infinity, C infinity, right? Now just think about it. A to B distance is, now I'm trying to relax every edge exactly once. If I relax this edge, then wow, if I relax this edge. Okay, so when you're relaxing, don't look at this newly formed graph, look at the old graph. If I relax this edge, what do I get? 0 plus 4 is 4, therefore this value is going to be changed to 4, right? This one is relaxed. And now if I relax this, what do I get? See, I'm relaxing it in this graph and writing the number here. Okay, if I relax this one, 0 plus 1 is 1, therefore here I am supposed to get 1. And if I relax this one, it is infinity plus 2 is simply infinity, therefore nothing is going to change, so it is already 4 and it is going to be same like that, right? So what did you understand from this? If you relax this all the edges exactly once, see, whenever I am relaxing it, I am just taking the previous graph and I am applying here. So just understand this point. So whenever you are relaxing the edges, when you relax them one time, it is nothing but we are finding out the length of the shortest path where each path is maximum one edge, which means what is the shortest path from A to B which contains only one edge, which is nothing but 4. What is the shortest path from A to C which contains only one edge, which is nothing but 1, right? But even though the shortest path from A to B is 3, it is containing 2 edges which we will get at the second round of relaxation. So understand it, when we relax all the edges one time, it is nothing but length of all shortest paths which contain a maximum of one edge. If I relax everything 2 times, it is nothing but it gives us length of all shortest paths which contains a maximum of 2 edges. Okay. Now since there are 3 nodes, the shortest path could be as big as our shortest path could contain as many as 2 edges. Therefore we had to relax it one more time. So I am going to take it and relax it one more time. 0, 4, 1. Now I am going to relax here. So if I relax here, 0, 4, what do I get? 0 to 4 is, again 0 plus 4 is 4. Now if I relax this, what do I get? 0 plus 1 is 1, 0 plus 1 is 1. If I relax this edge, then 1 plus 2 is 3, but the known distance there is 4, therefore it is now reduced to 3. Got it? So in the first round of relaxation, we get the length of all shortest paths which contain at most one edge. In the second round of relaxation, we get length of all shortest paths which contains at most 2 edges. Got it? Therefore here you are supposed to stop. The reason is length of the shortest path will never contain, or the shortest path will never contain more than 2 edges if there are 3 nodes. Got it? And now one more thing is, if you stop here and declare that these are the shortest path, you might be wrong. The reason is there might be negative weight cycle which you might have to declare, which you might have to find out. So what you do is, after doing n-1 times relaxation, you do one more time relaxation, right? In that case, if you still get a better values for the vertices, it means that definitely there is a negative weight cycle. The reason is, after including n-1 edges in the graph to find out the shortest paths, if you are able to do one more relaxation, means you are finding out the shortest paths which contain n edges, which means we are finding out the shortest paths which contain loops. And now if loops are giving you better values, which means if the values of the nodes are decreasing, which means loops are giving you better values, then definitely the chances are that, or definitely it is true that there is a negative weight cycle. Therefore after relaxing n-1 time, you just see for one more time. If there is a decrease in the value, you can say that, oh, something is wrong. What is wrong? That there is a negative weight cycle, therefore we are getting lesser values for one more time relaxation. So the thing is, we are not able to get the shorter paths because there is a negative weight cycle. That is how Bellman-ford will declare that it is wrong. I'll take more examples and explain you this algorithm. Let's see with an example how Bellman-ford will find out that there is a negative weight cycle. Okay, I'll take a small example which we have already seen for Dijkstra algorithm. A with 3 nodes, A, B and C. Distance is 1, 2 and minus 3. There is a negative weight cycle, isn't it? So how will this, how many times with if this is the input given to the Bellman-ford, how many times we should run it is depending on number of nodes. How many nodes are here? 3 nodes. Therefore, how many times Bellman-ford should run? Exactly 2 times, right? So after running it for 2 times, we are going to arrive at some values, right? And then we'll try for one more time. If those values are going to change, which means that introducing a loop in the graph is giving us better values. So what does mean? There is a loop which is having negative weights, or it is a negative weight cycle. Therefore we can say that our algorithm, or for this graph, there is no answer of shortest path, right? So let's see this. So initially we are going to start with 0 for the source, and then for the others there will be infinity, and the distances are like this. It is B, it is C, distances are 1, 2, right? So now first round, so I am going to relax it for the first time. When I relax it for the first time, all the edges have to be relaxed exactly once first time, right? So when I relax this edge, then what do I get? 0, 0 plus 1 is 1, which is better than infinity known. Therefore I am going to write it as 1. Okay, this is relaxed one time, and now I am going to relax this again first time. So here infinity, infinity plus 2 is infinity, so already known value is infinity. The value doesn't change, infinity remains like that. Okay, so when I relax it, infinity is going to be like that. And next I relax it. So infinity minus 3 is again infinity. So already known value here is, as of now, is 1, but this one is showing infinity. Therefore even if you relax it, we are not going to get anything. So A, B, C. So if we observe it, it is nothing but length of the shortest path to the vertices in which the path will contain only one edge. That is how it acts when we relax it one time. Now how many edges can be present at maximum in this graph in any shortest path? Since there are three nodes, the shortest path may contain as many as 2 edges. Therefore relax it one more time. So if I relax it one more time, the same one, this one, see this, A is going to be 0, and if I relax this one is going to give me only 1, which is already there. For B it is going to be 1, and if I relax this one, this 2, then I am going to get 1 plus 2 is 3. Therefore here I get a value of 3 for the node C. And if I relax this one, infinity minus 3 is infinity, but known value is 1, therefore it will not change anything, 1 will still remain there. So minus 3, got it? So now just observe this. We got the shortest path from A to A as 0, and we got the shortest path from A to B as 1, and we got the shortest path from A to C as 3. So this is what you get if you are going to stop the algorithm there after exactly 2 rounds. That is what actually Dijkstra algorithm arrive at. See, Dijkstra algorithm will follow a different procedure, but then it will arrive at this answer 0, 1, 3, and it will stop there, saying that these are the final answers. I know, but then they are wrong, isn't it? So what will Bellman-ford do is, even though it is supposed to run only n-1 times to find the answer, it will try to go for one more round of relaxing. Therefore it is trying to see, by including n edges in a shortest path, will we do better. If we do better, it means that there is a cycle of negative weight. So now if you relax it one more time, what do we get is, here 0 is for A, and if I relax this edge, then what do I get? 0 plus 1 is 1, so it is going to be same for B. And if I relax this one, again I'll get 1 plus 2 is 3 only, it is going to be 3, isn't it? This one is relaxed, this one is relaxed. But if I relax this one, what do I get is 3 minus 3 is 0. Therefore if I relax this edge, then 3 minus 3 is 0. This value need to be changed to 0. That is the problem, right? So now we found out that even after including 2 edges, if I include 3 edges in the shortest path, 3 edges is what? 1, 2, 3 edges. Actually 3 edges, if you are including it, then definitely there is a cycle somewhere and we are getting a better value. Definitely that cycle must be negative weight cycle. So whenever the values change after n-1 rounds, if you go for one more round, if the value keep changing, at least if one value changes, that is enough. You need not look for more values. At least if one value changes, you can stop there and say that no, our algorithm cannot find out the shortest path because the graph does not contain any shortest path. It is going to be minus infinity, right? So that is how our Bellman-ford algorithm is going to stop. Got it? So how many times is our Bellman-ford actually running is v minus 1 times plus one more time. Therefore v times we are going to relax e edges. Therefore total number of relax operations by this Bellman-ford is v into e relax operations, right? And now how much time is relax operation going to take? Going to that Dijkstra algorithm, their relax operation is actually decrease min. The reason is the nodes are maintained inside a heap. Why did we use heap in Dijkstra algorithm is there we had to delete the min, but then here I need not find out min at any time. Therefore I don't need any heap at all. So what I could do is I could represent all these nodes as elements in the array. Then whenever I try to relax, I'll just decrease the value. I'll just directly go to that particular element and decrease it. Therefore every relax is going to take only order of 1 time. So what is the time complexity of Bellman-ford algorithm? V into E. So how did I do this? V times I am going to relax it. Why? V minus 1 times to find out the answer, and the last time to check out whether there is a negative weight cycle or not, and each time I am going to relax E edges, right? And that is why total number of relaxes is v into E relaxes. And whenever you try to relax any edge, it is simply we are maintaining them in an array, and directly we can go into that array index. So whenever you try to relax the value of, let us say, node B, and assume that node B is represented at some fixed location in the array, so you can directly go into that node B and decrease the value of B. Therefore it is going to be order of 1, unlike Dijkstra algorithm where it is order of log B, because all the elements are maintained in the heap and relaxing is nothing but a decrease key. So decrease key is going to take log B. There we had to maintain it in the heap because we had to find out every time the minimum value and delete it from the heap. But here we need not find out the minimum value, we are continuously relaxing them, right? So the time complexity of this one is V into E, but the time complexity of Dijkstra is E log V. Dijkstra is better compared to Bellman-ford, but Bellman-ford is better if you have negative weight edges, because it is definitely saying that I can compute the value or I cannot compute the value. Dijkstra, if you give it any negative weight edge graphs, it will definitely say that yes, I can do it, and it will give you some wrong answer in case if there is a negative weight cycle. Got it? So let's see the algorithm of this Bellman-ford and I can analyze it. Now let's look at the programming paradigm called dynamic programming. So it is different from all the others we have seen. Till now we have seen the divide and conquer and greedy. Dynamic programming is bit different, and it is very much similar to divide and conquer, not greedy. So greedy is fine, but then dynamic programming and divide and conquer are actually similar. I'll just take an example and I'll show you how or when we should be using. So why is it called dynamic programming is, programming doesn't mean that we are writing any programs, or it is not related to any programming language. Programming means that we are going to use some tables. I'll tell you where the tables are used. And dynamic means we dynamically decide whether to call a function or to use a program. That is why it is called program in the sense table, or to use a table. That is why it is called dynamic programming. Okay, I'll just take an example and explain you what it actually means. See, divide and conquer, what we did is, if there is a problem, we divided the problem into 2 halves, and then we actually solved both the problems separately and we merged the solution. That is what is divide and conquer, right? And in case if these sub problems are overlapping, which means let us assume that we have a problem like this, or we have a problem, very big problem, and in order to solve it we are going to divide it into 2 halves. And in order to solve this problem, we are going to divide into halves. One half is this and other half is this. And in order to solve this one, if I have to divide it like this, and this problem again needs this small part. So it is better I'll take an example and explain you. It is not clear, which means if this small part, this sub problem, is going to be repeated when I solve this big problem, as well as this problem, as well as this problem, if this small part is going to be required in all the solutions, then if you apply divide and conquer, what happens is divide and conquer will end up solving this small part recursively over and again without actually knowing that this is already computed long time back. So whenever our main problem requires solving many sub problems which have already been solved, then instead of solving them over and again, we could maintain the solutions in a table and we could use them again. Okay, I don't know whether you understood this or not. What I'll do is I'll take an example and I'll make this point clear. See, main advantage of dynamic programming is here. So I'll take the example of the classic example is Fibonacci series. So if I have Fibonacci series like this, f of n equal to f of n minus 1 plus f of n minus 2, or it is equal to 1 if n equal to 1, and it is equal to 0 if n equal to 0, and it is equal to this otherwise. Then how are you going to write this program for this? Now let us say Fibonacci of n, you are going to write the program like this. If n equal to 0, then we are going to return. I hope that you know what Fibonacci series is. Fibonacci series is like this. So 0 and 1 are the initial. For n equal to 0, then the Fibonacci of n is 0, and for n equal to 1, Fibonacci of n is 1, and then for n equal to 2, Fibonacci of 2 is you have to add these two. Then what do I get? 1. For n equal to 3, Fibonacci of n is you have to add these two. I get 2. For n equal to 4, you have to add these 3. I get 3. So you have to continuously add these two and get the next one. You have to continue it like this, right? That is Fibonacci series. Further, this is the program. I mean, these are the recursive equations, and for that, if I write a normal program, normal recursive program, how will it look like is this way. If n equal to 0, then we are going to return 0. Else, if n equal to 1, we are going to return 1. Otherwise, we are simply going to return f of n minus 1 plus f of n minus 2. So if this is the program written and if this is the recursive equation, if you try to implement it, let's see how much time is it going to take. So we know that how many recursive calls are going to be made. So let's take a small example. I want to find out Fibonacci of 5. So Fibonacci of 5 is nothing but it is not equal to 0, it is not equal to 1, therefore it is f of n minus 1 plus n minus 2, f of n minus 1 plus n minus 2. In order to compute this, you are going to call f of 4 and f of 3, and again f of 4 is going to call f of 3 and f of 2, and again f of 3 is going to call f of 2 and f of 1, isn't it? And now f of Fibonacci of 3 is going to call Fibonacci of 2 and Fibonacci of 1, and Fibonacci of 2 is going to call Fibonacci of 1 and Fibonacci of 0, right? And Fibonacci of 2 is going to call again Fibonacci of 1 and Fibonacci of 0. The same thing here, Fibonacci of 1 and Fibonacci of 0, right? So this is how all the function calls are made. You just fill it out if I miss anything. In case if I missed anything, you please fill it out. So now, how does the recursive, what is the order in which recursive calls will be made is, I told you that we have already seen it, how to, I think in recursive functions like merge sort and quick sort, I told you how a recursive function works. You have to write down the tree and then traverse it top down left to right, and that is the order in which the recursive calls are made, right? So initially you will be calling this one, right? And Fibonacci of 5, this one will be calling Fibonacci of 4, this one will be calling Fibonacci of 3, this one will be calling Fibonacci of 2, and finally this one will be calling Fibonacci of 1. When n equal to 1, it will simply return 1. So this one is going to return 1 to you back, and again you are going to call f of 0, and again n equal to 0, therefore you are going to return 1, right? Now Fibonacci of 2 is, you are going to add these two, and now you are going to return to 2 to this value, right? And again you are going to call Fibonacci of 1. So this is the thing. See this? Already Fibonacci of 1 is computed, and now again you are computing Fibonacci of 1, isn't it? So anyway it is going to return 1. So now the value is 3. Now 3 will be returned to this. Now Fibonacci of 4 will call Fibonacci of 2. This is again the misery. See, already Fibonacci of 2 is computed. Now again you are trying to compute Fibonacci of 2, which is completely a waste. So if you keep on calling all of them, nearly order of 2 power n function calls have to be made, even though the time complexity taken for each function call is order of 1. The total time complexity is going to be order of 2 power n exponential. So what could you have done better is, before, whenever you compute any value, since you know that that value is going to be of use next time, you can save it in a table, and then before calling a function you could check whether the function is already computed, and in case if it is computed and stored in the table, you could have used that. That is a better thing, right? So instead of putting all this, what you could have done is you could have maintained a table. In that table you could have maintained like this. You could leave out n equal to 0 and n equal to 1. They are simply going to return 0. You can start from 2, 3, 4, 5 like this. Okay. So whenever you computed this one first, so you could have written some small thing here. Before calling the actual functions, any function, you could have written a code saying that check whether the value is already computed. In case if the value is already computed, you please go to the table and take the value. In case if it is not computed, then you compute it. Got it? So before this writing this code, what you could have written is, instead of this part, this last part, what you could have written is, before that, whenever you are going to call the next function, check the table. Check the table for, let us say, t of n, and if it is available, we are going to use it. If it is not available, if t of n is empty, if it is not available, then you call f of n. So if you could write such a statement, then you are not going to incur these many function calls. So what you could have done is, see this here now, and if it is empty, then whenever you compute it, now after computing it, if t of n is empty, you could write t of n equal to f of n, which means if in case if it is empty, you could fill it up. So now how does this algorithm look like is, or how does this algorithm work is like this. See this? Initially you are going to go till here and again come back. So whenever you compute f of 2, you are going to write it in the table as the 2 value is 2, right? And next time when you are trying to compute f of 2, function call will not be made. This one will not be made, this entire tree will not be called. So only what will happen is we refer to the table and we get the table value directly, which is 2. Now 3 plus 2 is 5. Now we have computed f of 4 value, or in fact f of 3 value is also computed. We are going to store f of 3 value as 3 and f of 4 value as 5. And now when f of 5 wanted to call f of 3, before calling it, it will just check the table. In the table it is already available, therefore it is going to take that value from the table and put it there, right? So using this dynamic programming, in case if the subprograms are repeating, we could do them faster, in the sense we are going to call only one time. So in effect, how many function calls will be made is, f of 0 will be called once, f of 1 will be called once, and f of 2, f of 3, f of 4, f of 5. So 1, 2, 3, order of nearly n. Order of n function calls will be made. It is not order of 2 power n, by just using a small technique called as tabularization. Tabularization means saving the values in the table and then using them later. That is also called as programming. Now why is it called dynamic programming? Means before actually calling a function, we are checking the table, and if the table is empty, then only we are dynamically calling it. We are not always calling it. That is why it is called dynamic programming. If a problem is having some recursive equation, and if the recursive equation shows that the problem is having overlapping subproblems, we are lucky. We could decrease the time using dynamic programming. But then there are some problems in which there will be recursive equations, but then there will be no overlapping subsequences. For example, like merge sort. In merge sort, even though there are recursive functions, right, you are going to solve this one first and this one first and then merge them, right? So no problem is actually repeated. So once you are going to divide it and divide it, so once you solve it, that is over. So you need not solve a problem repeatedly. Therefore, dynamic programming is useful for only some of the problems. If you are lucky and if you find such a problem, we could solve it faster. And there are some problems in which there is exponential number of recursive callings. Okay, we shall see. Instead of talking about all those things, I'll take examples and I'll go one by one. So I'll take the most popular examples which are being asked in GATE and which are generally used in all the colleges and interviews. We shall solve them one by one. By that you will gain some insight into this dynamic programming, and later once I am done with all these problems, then I'll show you some of the problems for which dynamic programming is not going to be of much help. Okay, so we shall take the examples first. Now let's look at how to multiply the matrices in general. So if you have two matrices like this, I'm talking about matrix multiplication. Okay, let us say I have two matrices A and B. This is a matrix A and the dimensions of this is 3 by 2. So 3 by 2 means 3 rows and 2 columns. Assume that we have the elements like this: A11, A12, A21, A22, A31, A32. So this is 3 by 2 matrix. 3 rows are there and 2 columns are there, right? And now we have a matrix B, and assume that the dimensions of B is 2 by 3. So 2 by 3 means 2 rows and 3 columns. So which means, assume that B is kind of like this: B11, B12, B13, and B21, B22, B23, right? And now I want to multiply these two matrices. So first of all, is it possible that we could multiply them? Whenever you try to multiply two matrices, see that they are compatible. Compatible means the number of columns in the first matrix should be equal to the number of rows in the second matrix. You must be knowing this from your 10th class mathematics. It is straightforward. Then what I want to know is, if I multiply these two matrices, what is the size of the resulting matrix? So the resulting matrix is obviously 3 by 3. Okay, so we are going to get a 3 by 3 matrix. Let us say this is the product matrix is called C, which is going to be 3 by 3. So how many elements are going to be there here? In this 3 by 3 is nothing but 9 elements are going to be there. Let's leave it 3 by 3. Now, in order to compute each element, what I would like to know is how many multiplications are we doing. So when I talk about this, I am talking about the scalar multiplication. Scalar multiplication means element to element, not the matrix to matrix. So if I want to compute the first element C11, I have to take this element and multiply with this. So I have to take each row and multiply with the first column. So if I want to have the C11, I have to take the first row of A and multiply with the first column of B. Then add this, add the result, all the multiplications, right? Now how many such multiplications should I do for the entire one matrix multiplication? In order to perform this one matrix multiplication, how many scalar multiplications are we really doing? See this? Now, in order to compute this element, how many multiplications we needed is 1 and 2. So I multiply this one with this one and this element with this element, and then I add them. So in order to find out, or in order to perform one multiplication, I'm actually doing in order to find out one element, I'm actually doing two multiplications. And what are the why two multiplications? Because all the elements of one row should be multiplied with corresponding elements of one column. So number of number of columns in this as well as number of rows in this are both equal to 2. Therefore, in order to find out one element, the number of multiplications I am performing is 2. Totally there are 3 into 3 elements, and every element needs 2 multiplications. Therefore, the total number of scalar multiplications to find out the product of two matrices is 3 into 3 into 2, isn't it? So that is what we found out from this example. In general, if I have two matrices like this, one matrix is let us say I have two matrices and the dimensions of one matrix is P by R and the dimensions of other matrix is R by Q. So observe that here if there is R, here there has to be R, otherwise multiplication is not possible. Then how many elements will be present in the resulting matrix? P into Q elements, isn't it? So total number of elements present in the result is P into Q, and if these many elements are present, in order to find out each element, we have to take every element of one row. How many elements will be there in one row? R elements, and then multiply them with every elements of all the elements of one column. How many columns will be there? R columns, isn't it? Every element of one row, how many elements will be there in one row? R elements, and we have to take and multiply them with every element of one column. And how many columns will be there? How many elements will be there in one column? So R elements. So how many multiplications we should do? R. So totally the result is going to contain these many elements, and in order to find out one element, we need to do these many multiplications. Therefore, how many total multiplications? Scalar multiplications. Scalar multiplication means element to element. How many total multiplications we are supposed to do in order to do one matrix multiplication is P into Q into R, or you can even write it as P into R into Q. This is what we are going to use. Okay. So from now on, if we have two matrices, each of dimension like this, if I have two matrices and dimension of one matrix is P by Q, and the dimension of other matrix is Q by R, then in order to find out the multiplication of these two matrices, the total number of multiplications required is P into Q into R. That is the convention I am going to use for this problem, right? So in order to multiply two matrices, these many multiplications are required. Just remember it, write it down. Now let us say we have to multiply three matrices like this. I have three matrices A, B and C, A, B and C, and I want to multiply these three, provided that, so first of all, if you have to multiply them, they have to be compatible, isn't it? So let us say they are compatible, which means let me write it like this. I have three matrices A, B, C, and the dimensions of A is 2 by 1, and the dimension of B is 1 by 2, and the dimension of C is 2 by 4. I have taken small dimensions. Actually it could be extended. You take big numbers and you just do it. Maybe you take 200, 100 like that. Then it will be even better. You'll understand more things there. So now there are many ways that we could actually multiply these three matrices. One way is, actually there are two ways. One way is you could multiply these two first, A, B, and then the resulting matrix you could multiply with C. Or other way is you could multiply, if you have A, B, C, you could multiply B, C first, and then you could multiply the resulting with A. So either you do this one, or either you multiply like this or you multiply like this. The final answer is going to be same, because matrix multiplication has a property called as associativity. So whatever way you multiply them, the final answer is going to be same, and moreover it has to be consistent. Okay. And now see this. Let us see what is the dimensions of this and how many matrix multiplications are required for each one of them. If I have to multiply these two, let us say the result is D. What will be the resulting matrix dimensions? The dimensions of this is 2 by 2. The resulting matrix dimension will be 2 by 2, right? And in order to multiply these two, how many scalar multiplications are required? I told you that P into Q into R, which is nothing but 2 into 1 into 2. Therefore, the total number of multiplications required is 4 in order to multiply these two, right? And the result is this one. If I multiply with 2 by 4, what is the scalar multiplications required here? So 2 into 2 into 4, 2 into 2 into 4, right? So which is nothing but 16. Therefore, the total number of multiplications required in order to finish the multiplication is 4 plus 16, because for this one 4 multiplications are required and for this multiplication 16 are required. So total number of multiplications required is 20 if I go in this way. And let us say the resulting matrix is E. What will be the dimensions of the resulting matrix? 2 by 4. That is not of our concern, but just doing it. What we are trying to do is how many multiplications are required. If I go in this way, it is 20. right? Now let's see about this one. If I go in this way, so what are the dimensions? It is 2 by 1, it is 1 by 2, and it is 2 by 4, right? So if I multiply these two, let us say I get a new matrix D whose dimensions are 1 by 4, right? And now I have to multiply this 1 by 4 matrix with a 2 by 1, and they are compatible, isn't it? And now let's see the scalar multiplications involved. In order to do this multiplication, how many scalar multiplications are involved? 1 into 2 into 4, which is nothing but 8. And in order to do this multiplication, how many scalar multiplications are involved? 2 into 1 into 4, so which is 8 again. So in order to multiply this one as well as this one, 8 and 8 scalar multiplications are required. Therefore, the total multiplications required, if I go in this way, is 16. So you can find out that we have saved some cost. Every multiplication is going to take a lot of time, I mean the one operation, and by doing this way we have seen that cost is actually saved. See, the dimensions are taken very small. If these dimensions are significantly large and over a big, over big matrices, you could save substantial amount of multiplications. Therefore, it is not a negligible amount, even though here you might see that only 4 are saved. Whatever it is, the way we parenthesize means the order in which you multiply. Parenthesize is nothing but dividing like this. A and B are parenthesized and then the resulting is did like this, right? This is called parenthesizing. So the way we parenthesize or the way we multiply a chain of matrices is going to have a significant impact on the number of multiplications required to solve a question, right? And it is always important that we want to keep that number as little as possible. If we have only 3 matrices, we got 2 ways to do it. Let's see what happens if I have more than 2 matrices, like if I have 3 matrices or 4 matrices or 5 matrices. Let's see how many ways we could parenthesize them and see which one is better in that. So the first thing is, if you want to apply dynamic programming for any problem, you should be able to find out one thing is optimal substructure. Optimal substructure. Substructure means I'll tell you what it is, and then you should be able to find out recursive equations or recursive solution. So these are very important if you want to apply dynamic programming. So optimal substructure means the given problem should be, we should be able to split the given problem into smaller optimization problems. That is called optimal substructure. And after taking this optimal substructure, we are going to write the recursive equations. Recursive equation is nothing but solving the problem by calling the same function again and again. That is called recursive substructure. So let's see how to do this, and before going ahead, it is better that we introduce some notational conventions to represent the matrices and the resulting product. I am going to write some notations. You need not by heart that. See, in GATE you need not by heart anything. Just look at the problems that we have solved and you can solve it directly. Problem is given. Otherwise, they will give you some notational conventions. You can follow them. I am following some notational conventions here. If you are comfortable, follow them or write your own conventions. Okay, try to follow what I am saying here. In GATE they will give you some other conventions. Don't get confused. Just in place of A they will put B, and in place of something alphabets will be changed. That's it. Now I want to multiply n matrices. Then I could assume that I am going to represent them as A1, A2, A3, so on an, without loss of generality. I could represent them, whatever the name of the matrix is, I can represent like this, right? And along with that, I'll represent with one more array the dimensions of each of them. So the dimensions will be represented like this. Dimensions of A is P0 by P1, and dimensions of A2 is P1 by P2. So remember that these two have to be same, and dimensions of A3 is, let us say, P2 by P3, so on. Dimensions of an will be Pn minus 1 by Pn, right? So any matrix Ai is given, its dimensions are nothing but Pi minus 1 by Pi. So this is what the dimension of every matrix. So what I mean to say is, I am using the notation A in order to represent a matrix, and the notation A1, A2, A3, so on an in order to represent the chain, and then I'm representing the dimensions of every matrix using P, so that when we write the substructure it will be easy. And now I'm just generalizing this. Let us say I have a chain of matrix AI, AI plus 1, AI plus 2, so on, AJ. So given problem will be 1 to n. Now I am taking a subpart of it, or you could even assume that I is 1 and j is n. Now what I mean to say is there is something called as a substructure. Substructure means if you have to find the optimal parenthesizing, which means minimum number of scalar multiplications required from I to aj, you could actually parenthesize it either here or here or here or here, and then the resulting matrix again you could parenthesize, which means if I have ai to aj, I could have written it as, you parenthesize it anywhere between k and k plus 1, which means ai plus 1, so on. You could take it till a k, and then you could multiply it with a k plus 1, so on, aj. It means that in order to multiply or parenthesize this entire problem of I to j, you could first parenthesize from I to k and then parenthesize from k plus 1 to j. What is this k is, you could do this splitting. This is called a split, isn't it? The original chain is split into two parts now. This split can be done after ai or after ai plus 1 or after ak. Therefore k can run anywhere from how we could write it is, I is less than or equal to k is less than j, which means you could split it at any point, right? So now whenever you split it at this point, what does it mean? In order to parenthesize this entire matrix, this sequence of matrix, chain of matrices, we are parenthesizing this first of and then the second of. Some cost is associated with these two, and then whatever result we get, we have to again multiply those two. Now can you guess what will be the dimensions of this one? So if the dimension of ai is pi minus 1 and pi, and if the dimension of ak is ak minus 1 and ak, then what will be the dimension of this entire matrix? Simply pi minus 1 by pk. You could check it out later, right? And what will be the dimensions of this entire matrix after multiplication? So the dimensions of this entire matrix after multiplication is p k by pj, right? So if you have a split at k, then we are going to get two chains of matrices which have some cost associated for their multiplication, and then after that cost you are going to again incur some more cost of multiplying these two. Now I'll get two matrices. Let me represent it like this. A I to k is one matrix after multiplying these two, and then a k plus 1 to aj is other matrix after multiplying all this. Now we are going to get these two matrices and we are supposed to multiply these two matrices. So this matrix is of this capacity and this matrix is having these dimensions. Now when I multiply them both, then what will be the cost associated with? How much? pi minus 1 into pk into pj. This is the cost associated. Therefore there is a substructure in the problem. So the original problem can be split at any point, and then you could compute half of that wherever you split, and then compute the remaining half, and then you join those two. That is why we got the some kind of division or splitting, that is called as substructure, right? And now using this substructure we can form the recursive equation. So let's see how to form the recursive equation. I hope you understood. And what are the various choices of k? You could split it at either I after I or I plus 1 or I2, and this can be generalized to 1 to n, right? You need not by heart this, just understand what I am doing, so that in exam if they give you some other conventions you can easily cope up with them. Okay, now let's try to form the recursive equation for this. So recursive solution is, recursive equation or recursive solution is writing the problem in terms of the same problem. So let us introduce one more term m. So m of I comma j is nothing but minimum number of scalar multiplications required in order to parenthesize ai to aj. So let us assume that we have the matrix ai and ai plus 1 so on aj. These are the matrices I have. Now m of ij indicates that if I have to parenthesize from I to j, what is the minimum number of scalar multiplications required. So one thing you should observe here is whenever you write any recursive equations, you should come up with the base condition. Base condition means where is that recursive equation going to stop. So base condition is this: whenever you have only one matrix to multiply, which means a1 with the same one, there is no need of multiply. If you have only one matrix, there is no need of multiplications at all. Therefore, if there is one matrix, the number of scalar multiplications required is 0. So whenever I have I equal to j, which means mi to mi, like that, only one matrix, then the number of scalar multiplications required is 0. So when is it possible? When I equal to j. And the other case is whenever we have more than one matrix, then we should actually do the multiplication, right? Then what I do is, whenever I is greater than I is less than j, then what we could do is split it up at somewhere. So first I will do split from m of I to k, which means I will find out the cost associated for multiplying from some matrix, the starting matrix I, to some matrix in the middle k, and then I will multiply the remaining. I will find out the cost to multiply the remaining m of k plus 1 to j, and after multiplying these two, which means after finding m of ik and k plus 1 to j, I get two more matrices, right? Like I shown you in the previous, just before, we get two matrices. And now the dimensions of each matrix here is, I'll get a matrix of dimension I minus 1 pi minus 1 by pk, and here the dimension of the matrix will be pk by pj, right? Now, and moreover, see this, these two are equal, therefore they are compatible and they could be multiplied. So I have split the main problem into two sub problems, and now these two matrices which are resulted, they have to be in fact multiplied with each other, right? So for that multiplication, the number of scalar multiplications required is pi minus 1 by pk into pj, right? And now the actual question lies here. So you understood that we are going to split it, but how do you know where to split? Actually, we don't know where to split, right? Which means if I have ai plus 1 and ai plus 2 so on aj, now if you are splitting somewhere, then this is the mik is from here to here, and mk plus j is from here to here, and then this part is multiplying these two. But then how do you know that we have to split exactly here? We don't know where to split, therefore we have to consider all possibilities. How many possibilities will be there? The number of possibilities will be j minus I. Why? Because the split can be anywhere from I plus 1 or I plus 2 or so on j minus 1. Therefore the number of possibilities we get for k is j minus I. These many possibilities we get, so we have to inspect every possibility and we have to take the minimum of it. So how can I write this problem? In order to find out the minimum number of multiplications required from I to j, the chain, you have to find out the minimum number of multiplications required from I to k and k plus 1 to j, and then multiply them. And this k could actually be anywhere from, we have these many choices, I is less than or equal to k is less than 0. So you could have split it anywhere here, right? So this is the solution we got. This is the recursive equation. I hope you understood this. So m is a notation which I introduced to represent the minimum number of scalar multiplications required to optimally parenthesize, after optimally parenthesizing I and j, right? Then I have split it up like this. Now it is nothing but a recursive equation. So the first thing is, whenever you want to apply any dynamic programming, you should make sure that there is one optimal substructure and there is two recursive equations, right? And the next part that you should be very careful, or you should actually inspect, is whether there are overlapping subproblems. So let's see whether there are overlapping subproblems here or not. with an example. I'll take an example and explain you this. Now for the previous recursion equations, let's write the recursion tree. Recursion tree will show us what is the order in which the recursion calls are made if that particular recursive equations were implemented as a program. Okay. For the previous recursive equations, for example, if I call it over a matrix of or a chain over 4, A1, A2, A3, A4, which means M14. In the previous equations, I hope that you have written them down. So please look at the equations. I am going to solve the example here. Now let us say, what is that I am interested in is recursion tree. So recursion tree is nothing but what is the order in which the recursive calls are made in order to solve the previous question. So I am taking a small example and the equations are already written. So equations you know them, right? So I am just writing here for the sake of your information if you don't know them. So Mij is equal to minimum of, you have to split anywhere from I to j minus 1, right? And m of I to k plus m of I plus k plus 1 to j, k plus 1 to j plus p of, so that is fine, that is not a recursion. I am just writing it just like that, p of I minus 1 pk and then pj, right? So this is how you are going to write the recursive equation. So if you write this in terms of a program, how does the program look like is, let us say I want to solve it for 4 matrices A1 to A4. I have 4 matrices A1, A2, A3, A4. Therefore, the solution for this problem will look like M1 to 4, right? So now let's see how to solve them. Initially, the first call will be made to M of 1 comma 4. This is the first call. Now whenever the first call is made, we are subsequently going to make the recursive calls in order to solve the main problem. So if I have 1 to 4, what are the various ways I could split? I could split it here, which means 1 to 1 and then 2 to 4. Therefore 2 function calls will be made in order to split it at M of 1 to 1 and then M of 2 to 4, isn't it? Or you could split it here, which means M of 1 to 2 and M of 3 to 4. M of 1 to 2 and then M of 2 to 4, right? Or I could split it here, which means M of 1 to 3 and M of 4 to 4. M of 1 to 3 and then M of 4 to 4, right? So there are these three possible splits we could make. So how many? 3. Why? I is 1, j is 4, j minus I is 3. So 4 minus 1 is 3. How many k's are possible? From I plus 1 to j minus, I to j minus 1, which means 4 minus 1, 3 splits. One split will call these 2, other split will call these 2 and other split will call these 2, right? And now 1 will simply return 0, that is the base condition. Remember, M of II is 0 because if you have only one matrix, the number of scalar multiplication required is obviously 0. Now let's see about this 2 to 4. If I have 2 to 4, what are the various splits? How many splits are possible? 4 minus 2, which is nothing but 2 splits are possible. So one split is M of 2 2 and M of 3 4, and other split is M of 2 3 and M of 4 4, right? And other split, this M12 is going to be split into 2 parts. So one is M of 1 1, only one split is possible, right? M of 2 2. Why? This I minus j is 1. And what about this? Again 2 splits are possible. 4 minus 2 is 2. So one split is M of 2 2 and then M of 3 4, and other split is M of 2 3 and m of 4 4, right? And what about this m of 1 3? Again 2 splits, so this space is actually not enough. Now let's say it is here, somewhere here. I'm just writing it down. Since this space is not enough, I'm just writing it down. Maybe you could think of it as the same continuation. So m of 1 3 we have split at m of 1 1 and then m of 2 3, or one more split is m of 1 2 and m of 3 3, right? There are the various splits possible. Now look at this. This one will return, this one will return, this one is again going to call two more functions. So one will be m of 3 3 because you could even split it, right? M of 3 3 and other is m of 4 4, and is going to again write two ways. See, this is not the only way you could do it. Maybe you could optimize it better, but anyway in worst case you are going to get these many, okay? And m of 2 2 here and m of 3 3. And what about the others? This will return, this will return, this will return. This one is going to call again m of 3 3 and m of 4 4, right? And what about this one? This one is also going to call m of, again I'm going to write it here, m of 2 2 and m of 3 3. This one will return, and this one is also going to call m of 2 2 and m of 3 3. And what about this one? This one is also going to call m of 1 1 and m of 2 2, m of 1 1 and m of 2 2, right? So it is very big, isn't it? So just observe this. Now how will the recursive functions be called is, this function is going to call this function and it is going to return, and again this function. So the order in which it will be called is, you can do top down traversal from left to right. You might have already seen it in our merge sort, quick sort. I told you how to evaluate the recursive functions, right? So what I mean to say is, for this question, if I have m1 to 4, which means 4 matrices, the depth of the recursion tree, the depth is going to be, see this, the worst case depth is m of 1 4 2 4 3 4 4 4. Therefore the depth is going to be order of n, isn't it? Now it is kind of a binary tree. It is a kind of binary tree, even not binary tree, even bigger than a binary tree, and the height of it is order of n. Therefore you can take it as, in worst case it is going to have, if it is going to be complete, in worst case it is going to be bigger than even our binary tree. So it is even around 2 power n. So number of nodes in this, if you count the number of nodes, they will be as big as order of 2 power n. If a binary tree is going to have a depth of n, and if it is almost complete, it is going to have order of 2 power n nodes, isn't it? So similarly here, it is even bigger than a binary tree, and it is, in case if it is going to be almost complete, or at least if it is half full, I am not even talking about completely full, even if it is half full, it is going to have as many as order of 2 power n nodes. Therefore even if the time complexity taken at every function is order of 1, which we need not worry about, the total number of function calls made will be order of 2 power n. Therefore it is exponential time algorithm. So in algorithms we generally avoid the algorithms which are going to take exponential time, like order of 2 power n, right? But then we are lucky that most of the problems are repeating. So see how the problems are repeating. See, now we need to compute this m11, and we need to compute m24, and we need to compute m22, and then m34 and m33, m44 and m23 we need to compute it. But look at this, already m22 is computed, it is repeated, you need not compute it again. Therefore if you can use dynamic programming by storing the problems which are already computed in a table and later referring to that table, so that we need not compute the same problem again, we need not call 22 because it is already computed, and we need not call 33 because it is already computed, and we need not call 44 already computed. And what about 12? 12 we need to call, but then we need not call 11 already computed, 22 already computed. What about 24? Yes, 2 4 we might have to call, but then 2 2 we need not call. What about 3 4? 3 4 is already computed, no need. What about 2 3? Computed, no need. 4 4 computed, no need. 1 3? 1 3 is not computed, I think. So 1 3 you might have to compute, but then 4 4 computed, no need, right? And 3 3 computed, 4 4 computed, 1 1 computed, 2 3 computed, it is already computed, and 1 2 is already computed, right? And 3 3 computed. So all these are already computed. So that is the advantage we get if you use dynamic programming. If you don't use dynamic programming and if you directly try to implement it, what happens is the number of recursion calls taken will be as big as order of 2 power n. How order of 2 power n is? If the height of the tree is order of n, even if it is half full, if it is completely full, the number of nodes are going to be order of 2 power n. If it is half full, the number of nodes are going to be order of 2 power n by 2, which is again order of 2 power n, right? So even if it is half full, we are going to get as many as 2 power n nodes, right? So don't directly implement this as a recursive function. It is going to be of exponential time. So what we could do is, we could do two things. One thing is prepare a table and then use the bottom up method. I'll show you what I mean by that. And the second thing is, yes, go in this top down method only by using the recursive functions, but then before calling a function, see whether that function call is required or not, which means whether previously we have computed that value and stored in the table. In case if it is present in the table, use that value. By doing that, we need not make these many function calls. All these circled out function calls can be eliminated completely, right? So what we can find out is, I think M24 is also done, and 13 is not done. Okay, so what I'm trying to say is, you need not compute these many function calls. You have to find out only unique function calls, and all the remaining can be, unique function calls can be stored there, and whenever you have to compute it again, you can see it. So there are two ways. One is start with the table, no recursion at all. Take the table, purely tabular method, take the table and then do it bottom up. Bottom up is nothing but you start with 1 1, 2 2, 3 3, 4 4 and then 1 2, 2 3 like this, right? So use only table, no recursion calls. That is called bottom up method. And other method is use recursion calls, but then before making a recursion call, look into the tables. Both methods, that is top down and it is bottom up, both methods are equally popular, and both methods are dynamic programming only, because both of them are going to use tables, right? So I'll show you with both the algorithms what is the time complexity. Both the algorithms are going to take a time complexity of order of n cube. Okay, why order of n cube is, if you want to see how much time does it take for us to compute it, is the number of unique functions here will be order of n square. I'll show you how. The number of unique functions, if you take them, they are going to be order of n square, and then in order to evaluate every unique function call, the time taken could be in worst case order of n. Therefore order of n square into order of n, which is nothing but order of n cube. That is how you could compute the time complexity from this. I'll again tell you this anyway. And if you use the tabular method, in the table, that is the bottom up method, in the table the number of entries are going to be order of n square, and in order to compute every entry, the time taken is order of n. Therefore again it is order of n cube. Okay, so anyway I'm going to take both of these and tell you. So before that, I'll take an example and explain you how the tabular method can be used, and bottom up we shall see. Before going ahead, let me talk about subsequence. There is a basic difference between subsequence and substring. Let us say there is a word or a string. Let's call it a string like this: Ravindra, Ravindra. A subsequence is substring is, you have to take contiguously. RAVI is a substring, RAV is a substring, RAVI is a substring, VAN is a substring. So the substrings substrings should be contiguous, and subsequences, you can miss out some of the symbols and you can choose any one of them, and they are going to, and you can choose remaining. I'll just take this example, it will help. See, let us say the indices are like this: 1 2 3 4 5 6 7 8. Now you choose some of the indices, and all those indices should be in the increasing order. And if you write those letters or characters at those indices, that is nothing but a subsequence. For example, you could have taken 1 2 3, 4, which means RAVI. It is a subsequence. Or you could have even taken 1, 3, 5, 8. So as long as these numbers are in the increasing order, they are all called as subsequences, which means you have missed out 2, you have missed out 4, you have missed out 6 and 7. That is called subsequence. You could miss some of the characters in the middle as long as you have all of them in the ascending order. So what is the subsequence formed by this? 1, 3, 5, 7 is nothing but 1 is R, 3 is V, 5 is N, and 7 is R. This is subsequence, right? Or you could have even taken some other length, which means 2 and 7 is also a subsequence. What is 2? A. And what is 7? R, right? Or you could even taken it as 1, maybe 2, and then 5, and then 8. Let us say 6 and 8, 5. So what is 1? R. What is 2? A. What is 5? N. And what is 6? D. And what is 8? A, right? So again, this is a substring. These are all the substrings, right? And even you have a substring of length 0, which is nothing but 5. 5 is also a substring. So for this string, we could get these many number of substrings, isn't it? And how many substrings can we get for any given string? Simple. For any given string, you could actually take a character from it, or you can leave it out. Therefore, every character will have two possibilities. It could be either included in the substring, or it could be left out alone, isn't it? Now 1, 2, 3, 4, 5, 6, 7, 8. 8 characters are there, and each character is going to have two possibilities, which means that character could be included in the substring or it could be left out. Then 2 into 2 into 2 into so on 8 times, which is nothing but 2 power 8. In general, if I have a string whose length is, let us say m, then how many substrings will be possible of the further string? 2 power n substrings will be possible, right? So these many substrings are there. Now why is this problem interesting is there are many applications, a lot of applications for this problem. One common application is this. Now our DNAs, there is a term called as DNA, and our DNAs, you might have heard about it, right? So genes and DNA, that is how they derive how a biological animal behave, right? So how similar the animals are, or how similar the species are. Now let us say a species is having a DNA as a string of or strand of some molecules. So actually there are 4 molecules A, C, G, T. Don't worry about the names. There are 4 molecules using which DNA will be made of, and the names are not relevant, but they are going to start with these 4 characters A, C, G, T. Therefore in the DNA we are going to represent these 4 molecules using those 4 characters. For example, a DNA might look like this: A, G, C, C, T, C, A, G, T, something like this is a DNA. Which means if you take this strand of the DNA, strand is nothing but a string. So if you take this strand of a DNA and if you write it out, right, it might look like this. Now if I take 2 species and 2 DNAs of each species, I mean one species and the other species, right? And now if I want to compare how close they are, then what I try to do is I'll take one DNA and compare it with the other DNA. Let us say I got DNA D1 as this one, and I got DNA D2 as maybe GCCT, some strand. So you need not, actually what happens is DNA will be a string which will be repeating over and again. Therefore we will be taking the some part of it or some significant part of it, right? So they'll give you, so you need not worry about which part is DNA, they'll give you completely. So this is DNA of one species, and this is DNA of 2 other species. Now if they are similar, first thing is, if they are similar, if both the DNAs are equal, I mean if both the DNAs are equal, you can assume that they are coming from the same parent. Or if they are very much similar, if one DNA is a subset of the other, substring of the other, which means if this one, look at this is a substring of this, isn't it? Therefore they are very similar. How could you measure similarity is, first thing is, if both are equal, then they are 100% similar. Second thing is, if one DNA is a substring of the other DNA, substring means this is a part of this, right, or this is a part of this, anything. If one DNA is a substring of the other, and we can say that they are very much similar, right? And now if they are not substrings of each other, then we would like to know how similar they are. The similarity depends on what is the longest common subsequence. Longest common subsequence means if you have 2 power n subsequences here and 2 power m subsequences here, now you see you try to find the subsequence which is present in both of them and which is longest. That is called longest common subsequence. So two DNAs are very similar. I mean, the similarity depends on how long the common subsequence is. If both of them are having a very long common subsequence, then it means that they are very much similar. For example, in this case they are very similar because they are one is substring of other. They are very similar, and in some cases they may not be substring directly. Therefore, in that case we would like to find out the similarity by finding out the longest common subsequence. For example, if I have 3 DNAs D1, D2 and D3, and I want to find out which two of them are very close to each other, then what I do is I find out the common subsequence of D1, D2, all the common subsequences, and I find out the all common subsequences of these two, and I find out all the common subsequences of these two for all the pairs. Then I'll see what is the length of the maximum length of the common subsequences, right? For example, here I got the common subsequence as only one common subsequence, which is let us say ACG, and here I got a common subsequence ACGT, and here I got a common subsequence AAGT G, something like this, right? Then the length of the longest common subsequence here is, among all the subsequences, assume that is the longest common subsequence. The length of this longest common subsequence here is 3. Longest common subsequence here is 4. Longest common subsequence here is 5. Therefore, we can say that D1 and D3 are very much similar compared to any other pair. Got it? So, how can we compare the similarity or measure the similarity? Take one string or take one DNA and take the other DNA, and you find out all the common subsequences, and then see among all the common subsequences which one is the longest, right? And that longest number indicates how similar they are. The longer the subsequence, the common subsequence, the more similar they are. Okay, so I'll just take a small example and explain you how to measure this. Let's see this. Let us say I have a string like this. I'm not talking about the DNA, some string, and let us say I have one more string like this. Now I want to compare between these two strings what is the longest common subsequence. So you can find out that only longest common subsequence is A. Check it out, you can check it out later. Anyway, this doesn't have J and it doesn't have Y. So A and A is present in this as subsequence, as well as A and A is present in this as subsequence. Therefore, this is the common subsequence, and one more common subsequence is simply A, isn't it? Because both of them contains A, and one more common subsequence is phi, because phi is a common subsequence of everything, right? So among all these three common subsequences, the longest common subsequence is AA, isn't it? So the longest common subsequence is 2. How similar are these two? 2. In case if they would have been DNAs. Therefore, given two DNAs, you find out all the common subsequences, and then you find out whether after you find out the common subsequences, now you can find out whether they are actually in the same order or not. I mean, which one is the longest, and then you can compare them. So how to write an algorithm to find it out is, let's see, one basic algorithm is like this. You find out all the subsequences of one string and then check if that is a subsequence of the other string, isn't it? Let us say the string length here is m. Then how many substrings we get? We get nearly 2 power m substrings for this string. Now you take each substring and you go to the other string and you find out if that is a substring of this string or not, isn't it? In case if that is a substring of this, you can write it down. Now how long does it take in worst case to find out whether a given string is a subsequence of this? Okay, by mistake I think I am using the word substring. It has to be subsequence. Okay, whenever I say substring, you please correct it. It has to be subsequence. Okay, again I am saying that if the string length is m, the total number of subsequences I get is 2 power m. Now you take each subsequence and you go to the other string which is of length n. Both of them need not be of same length. Observe that two DNAs need not be of same length. It will be of some length and the other one will be of some length. What we are interested is common subsequent, which is. Now how long does it take in worst case to find out whether a subsequence of this one of one string is a subsequence of the other string or not? You take the subsequence and you might have to scan the entire sequence, right? It is going to take order of n time, right? So first thing is, obviously it is very simple. Every subsequence cannot be a subsequence of this. You can see the length and then rule them out. If the length of this subsequence is greater than the length of this, it is a rare case, then you could rule it out. And in case if the length of the substring is less than the length of this, length of the subsequence here is less than the length of the string here, then you could easily have a scan it. You just you just have to scan it using 2 pointers, and then let us say you have a subsequence a here. Then you want to see whether this is a subsequence of this one or not. Have 2 pointers, 1 pointer here and 1 pointer here. Whenever there is a match, you increment it, right? And again you keep on incrementing this, and whenever there is a match, you increment it. You increment both of them. So it can be implemented in order of n, right? Therefore, if you go with that algorithm, what is it? Find all these subsequences. Find all subsequences of, let us say this is the subsequence, this is the sequence A, and this is the DNA B. Find all subsequences of A. So how many will be there? 2 power m. And then find for each subsequence whether it is a subsequence of B, isn't it? So take each one and you go there and you can find out whether it is a subsequence of that or not, right? And now and you can write it down. So once you get all the subsequences, then you could find out which one is the longest. Then find the longest among common subsequences, right? So these are the 3 steps. Now first step, we have to find out all the subsequences of A. So how many will be there? 2 power m. Therefore it will take order of 2 power m time. Now second step is, for every subsequence you found here, you have to go and see if it is present in the other sequence. For that, the time complexity is going to be order of n into 2 power m. The reason is there will be 2 power m subsequences, and in order to test each one, it is going to take order of n time. Therefore total time is order of n into 2 power m, right? And then find the longest among them. So how many will be there? Nearly order of 2 power m will be there, right? Then you have to find the longest among them. So in order to find the longest among them, then it is going to be order of 2 power m, a linear search, right? So anyway, this is the time complexity. Now I have a doubt. Should we not find out the subsequences of the other sequence also? You need not. If you have found out all the subsequences of one, right, and if you are talking about the common subsequences, then those common subsequences will already be present in the subsequence of the first one. It is like this. Let us say this is set which contains all the subsequences of A, and this is the set which contains all the subsequences of B. Now we are interested in this common part, and definitely this common part is already present in A. Therefore finding out the subsequences of A is just going to find out all, even the common subsequences. You need not find out the subsequence of B as well, right? Because the required part is already present in A. Now just find out everything and then test how many of there are in B, which means this part, and you just write them down, and among them you can find out the longest common subsequence, right? So that once you find out that longest common subsequence, that will give you the similarity among between the two DNAs. But the problem with this algorithm is it is going to be exponential, which means order of n into 2 power m. 2 power m is exponential time, and we generally avoid such algorithms because implementing them is going to be computationally infeasible, right? Then what is the other method? Now can we apply divide and conquer or greedy method or dynamic programming and improve the time complexity? It turns out that we can actually apply dynamic programming. Now in order to apply dynamic programming, I told you that there have to be two things. One is optimal substructure and the recursive equation. You should be able to find out these two, and next thing is there should be overlapping subproblems. Then only dynamic programming can save us. If we don't have these two characters, even dynamic programming cannot save us. We are lucky that in this case dynamic programming could save us. Okay, we shall see how to apply dynamic programming on this. Now let's see if there is an optimal substructure. So what is optimal substructure? If you are able to write the main problem in terms of a smaller problem in such a way that the solution to the smaller problem is going to be the part of the solution to the main problem. Okay, what does it mean is optimal substructure. So for any dynamic programming, if you had to apply any dynamic programming, you have to check it, right? Then we can apply this. So optimal substructure says this is the main problem, which means if I have two DNAs, two strands of DNAs, now I want to find out the longest common subsequence. Let us say one DNA is X and other DNA is Y, and it contains X1, X2, so on, Xn, and then it contains Y1, Y2, so on, Ym. They need not be of same length. Okay, then what we could do is I'll first compare these two, Xn and Ym. In case if they both are equal, then what did that mean? We found out one character which is in the common substring, right? Then we'll take that as we found out one, and then we'll go ahead finding out the longest common subsequence in the remaining strings, right? Which means x1 to xn minus 1, y1 to yn minus 1. In case if there is no match, then what I do is I'll take this entire x and then I'll compare with this one, right? The reason is there is no way now you take this and compare it. Anyway, we found out that it is not going to be matching. Or what I do is I'll take this entire string and then I compare with this one. See, it is very logical and simple. Try to understand it. What I'm trying to do is if I have two DNAs, x1, x2, so on, xn is one DNA, and then y1, y2, so on, yn is other DNA. This x1, x2, xn and y1, y2, yn are nothing but the characters in the DNA. This is a sequence of characters, and these are all the characters. Now we want to find out the maximum common subsequence or the longest common subsequence between these two DNAs. First you compare these two. If they both are equal, what does it mean? We found out one character which is going to be in the final answer, right? You could either come from the beginning or go from the ending, not an issue, but then I'm trying to do this. Now if they are equal, then you find in the remaining sequence remaining what is the longest common subsequence, and once you get that, you can append that one with this one. Let us say from this one you got the common subsequence as something, and you can take that common subsequence and you can append either xn or yn, which are both same in this case, and then ym, and then you can say that we get a longer subsequence, which means the longest subsequence in this entire string can be written as the longest subsequence of the smaller strings. This is in the case when these two are equal. What if these two are not equal? Then you are not going to include them. Now you could either remove ym and you can find out the longest common subsequence from x1 to xn and from y1 to ym minus 1, or you could remove this one xn and then you can find out the longest common subsequence from x1 to xn minus 1 and y1 to ym, right? Therefore, anyway, we are able to write out the big problem in terms of smaller problem. How small is the problem every time? Either we are going to reduce the sequences of both x and y by 1, or we are going to reduce the sequence of x by 1 and y is going to remain same, or y by 1 and x is going to remain same. Anyway, by taking one decision, what is the decision here? Whether the last two characters are equal or not. By looking at that condition, that is called a condition, sorry. By looking at one condition, we are able to decrease the size of the problem into a sub-problem, and now the solution to the sub-problem is going to be solution to the main problem. Therefore, we got the optimal substructure, right? And after finding out the optimal substructure, you should be able to write the recursive equations, right? Now let us say I have two sequences x and y, and I am not worried about whether they are from 1 to n or so. I just generalize it. Now assume that x is containing from 1 to xi, and then y is containing from again 1 to yi. If I have two sequences or two strings given as x1, x2, x3, so on xj, which means one is x1, x2, so on xi, and other is y1, y2, so on yj. Now the intention is to find out what is the longest common subsequence between these two. Now I am going to use the representation Cij to represent the length of the longest common subsequence among x and y, where x is running from 1 to I and then y is running from 1 to j, right? That equal to, first thing is it is 0. When is it 0? Whenever you have, if you don't have any strings in either x or y, which means if either x or y is simply empty set, then we cannot find out the common subsequence at all. I mean, the common subsequence will be simply a null set. If one of them is null, then the common subsequence is null set. It is nothing but the base condition where we are going to stop the recursion, right? Whenever you write any recursive equations, remember that you should give the base condition, which means when are you going to stop without calling the sub problems. So this is the base condition. When is it? Either I equal to 0, which means either there is no x string, or j equal to 0, right? And what is the other case? In case if these two are equal, which means if xi and yj are equal, then you have already found out the subsequence of length 1, isn't it? Then 1 plus, then what do we do in the remaining substrings, in the remaining sequences, apart from the other than the last one, these last two characters have to be removed, and in the remaining whatever strings we get, we have to find out the longest common subsequence. So we already found out one character, that is why it is 1 plus, right? 1 plus I minus 1 j minus 1. So what does it mean? It means that we are trying to find out the longest common subsequence, and already we found out one character in the longest common subsequence. Therefore 1 plus in the remaining parts you find out the longest common subsequence, and already we have 1. So you add them both, then you are going to get a longest common subsequence in the entire string, right, in the two strings. Then when is this condition true? First thing is I and j, they have to be greater than 0, they should not be zeros, anything should not be zeros, and xi should be equal to yj, then it is possible, right? And what is the other case? If these two are not equal, what is that we are going to do? So first one is, if these two are not equal, then we are going to find out two cases. So we are going to remove the last character from x as useless, and then in the remaining strings we find out the maximum, or we are going to remove the last character from y as useless, and in the remaining strings we are going to find out the longest common subsequence, which means we are going to remove this one. If I remove this one, what do I get is I minus 1 comma j, right? Or if I remove this one, then what do I get is I have to find out the longest common subsequence in I comma j minus 1. Now I'll see which one is maximum among these two, then that is going to be the maximum longest common subsequence, right? I'll take an example and explain you how this works. But then this is how you could write the recursive equation, right? So why are we trying to do this? Because that exhaustive search method or the first algorithm which I have shown you is going to run in exponential time. Therefore, I am trying to write it in terms of recursive equations and then see if this is going to be better, okay? And then when is this possible? I and j both have to be greater than 0 and xi is not equal to yj, right? Then I am going to find out the longest common subsequence in the resulting sequences, and whichever is longer, that is going to be the answer, right? So using these recursive equations we can solve this question. So okay, fine. So once we get the recursive equations, what could we do? I'm not talking about dynamic programming. In general, if you have the recursive equation, you could have implemented it as a recursive function, and now that recursive function is going to be implemented as a recursive program, and that recursive program is going to call many functions, right? Then the time complexity and space complexity depends on the recursion tree. I'll take an example, and first let's take an example and see how this recursion works, recursive equation working, and then we shall see how many function calls are actually required, okay? Let's talk about multi-stage graph. Before solving this question, let me explain you what we mean by multi-stage graph. So it is definitely, graph means the graph which you know, I'm not going to define it. And then multi-stage, stage means at every stage we are going to have some nodes and there will be many such stages. So why do I call them as stages is, we can divide the nodes or the vertices into some groups, some sets, in such a way that there will be no edges within one set and there will be edges from one stage to the other stage. So I'll just take this example and show you. In this example, I can say that it is a graph. Definitely it is a graph, right? Directed weighted graph. And second thing is, if you see this, all the nodes are at some stages. So I can say that S is in stage 1 and like this. S is in stage 1 and A and B and C, A, B and C are in stage 2 and D, E, F are in stage 3 and T is in stage 4. So what are the main characteristics of this multi-stage graph is, within one stage, which means A, B, C, there will be no edges between them. Within one stage, no edges. See this? Within one stage, there will be no edges between them. If there is an edge, that will definitely from stage I to stage I plus 1, which means from 1 to 2 there will be edge, but then 2 to 1 there will be no edge, right? And moreover 1 to 3 there will be no edge. So edges will be there only from Vi to Vi plus 1. If you have such a graph, then that is called multi-stage graph, right? And now let's define the problem. This is what is called multi-stage graph, and now the problem is, at stage 1 we have one source. At stage 1 we have a node which is called as the source, and the stage n, which means the final stage, this fourth stage, we have a node called as target or sink, generally source and destination. And now from source to the target, I want to find out the shortest path. That is the question, simple, right? So we have a multi-stage graph, and now I want to find out the shortest path from the source to the destination, right? And how many paths are there? There are many paths. See this? I could have taken like this, or I could have taken like this. There are many paths, isn't it? So one solution is, you could find out all the paths, right? And then you could find out the cost of each path, and then you could find out the minimum. But that is the brute force method, which is very, very inefficient. And second best solution which we know is, maybe you can start single source shortest path algorithm from S. We have already seen Dijkstra algorithm, and you can apply definitely Dijkstra algorithm. Why? Because there are no cycles, therefore there is no problem of negative weight edges, therefore no problem of negative weight cycle, since there is no cycle at all. So you can happily apply Dijkstra algorithm. But the problem is, if I apply Dijkstra algorithm, actually that is designed to find out the shortest path from one node to all the other nodes, right? That is single source shortest path, which means from one node to all the other nodes. and so it will end up finding the shortest path to all the nodes before finding the shortest path to destination, right? But then I don't want the shortest path to all the nodes. I want the shortest path from source only to destination. Now what happens if I keep on finding out the shortest path to all other nodes is, it is unnecessarily going to take more time, isn't it? So the time complexity of Dijkstra algorithm, if you remember it, is order of E log B, isn't it? I don't want it is good, but then I would like to find out if there is any better way to find out, because the graph is not a normal graph, it is having some special characters. I would like to take the advantage of the special characters that the graph has. And the second thing is, I would like to know if there is any other way we could explore these characters and get the time less. So obviously we can go for Dijkstra algorithm, but we are not going for it, right? So what is the next method? We have already seen that there is a strategy called as greedy method. So if I apply greedy method to this, let's see what happens. So greedy method means, see, from this stage I have to go to this stage. I have three options. Either you could take this one or this one. What will greedy method do? It will take the least cost, because since we want the entire path to be minimum, it will assume that if I take the least cost now, successively it will be minimum. But then let's see what happens with that approach. If I take the greedy method, how much time will it take is, if I take the greedy method, at every node I might have to check all the edges, isn't it? Therefore all the edges will have to be checked at least once. It is going to take order of E time, but then the answer which we get might not be right. So remember this, greedy method when applied to optimization problems. What is optimization problem is? Finding out maximum profit or minimum cost, whatever. Either you try to maximize something or minimize something, that is called optimization. So whenever you are trying to do optimization, we have two strategies mainly. One is greedy, other is dynamic. The problem with greedy method is, if you apply this method to optimization problems, there is no guarantee that you will always get an optimal value. It will give you some value, but then that need not be the optimal. But then the advantage of greedy method is, it runs faster compared to dynamic. But dynamic method on the other hand will always give you optimal answer, but the disadvantage is it will take time more than greedy method. So if you are lucky that greedy method is giving you some answers to the problem, optimal answers to the problem, you are lucky that your problem can be solved in very less time. In case if you are not able to find a greedy method, then we go for dynamic, right? And in the dynamic problem, there have to be some characteristics. And if you are not lucky, even dynamic problem will also fail to give you a better algorithm, which means dynamic algorithm will definitely solve the problem and give you optimal answer, but then the time complexity required might not be polynomial, it might be exponential. Okay, we shall see about it later with some other examples. Now let's focus on this question. Now let's see what happens if I apply greedy method to this. So if I apply greedy method to this, it will say that from S you could take S to A, because among all the alternatives present, the simplest alternative or the shortest alternative is S to A. So greedy method says that you take from S to A first, and then now we are at A. When you are at A, among all the options you have to take the shortest option. So among all the options we have these two options, 4 and 11. So take the shortest, which is 4. Therefore we are going to D, right? And now we are at D. There is no option. You have to definitely take 18. You have to definitely take D to T, right? So what is that we got here? 1 plus 4 plus 18. I think it is 23. So the length of the shortest path here we got is at 23. But then it is clear that you could observe some other nodes, some other paths which will be better than that. For example, look at this path, S to C, C to F and F to T. It is clearly 9, right? I could have got 9. 9 is the best possible answer. But then, okay, how do you know that 9 is the best possible answer? Because I solved it beforehand. So don't think that by magic, I am finding out directly without any algorithm. No. Now 9 is the best possible path, but then we are getting 23, right? So definitely greedy method does not work for all the graphs, for all the problems. This is one such problem for which greedy method fails. So now we cannot apply the greedy method. Now let's see how we could apply the dynamic method here. Okay, I hope that you have already watched the video of greedy knapsack. Now there I defined what a knapsack is and what do you want. So I'm just guessing that or assuming that you have already watched it, and I'll just continue with this problem. Let us assume that there is a bag, knapsack, and whose capacity is 6. And now the 3 items have to be placed in it, 3 objects, and each object is having a weight and corresponding profit. So if you place an object inside the bag, then you are going to get the profit from that object. Okay. And now the concept is, or now the problem is, previously we have seen in greedy, the knapsack in greedy algorithm. There I have told you about the fractional knapsack. So actually knapsack is of 2 types. So knapsack problems can be generally of 2 types mainly. There are various types, but then popular ones are this. So one is fractional and other is 0-1 knapsack. Fractional knapsack and 0-1 knapsack. So what do I mean by fractional knapsack is, in this fractional knapsack, objects are in such a way that you could even cut the object into a fraction and put it in the bag, right? For example, you can think of it like this. Maybe if you are buying, what can I say, what are the fractional objects is, if you are buying, let us say, chicken, they'll give you half kg chicken or 250 grams chicken. So you could actually divide it. Okay, if you are not non-vegetarian, then you can take some other example, which means you need not buy everything in a bulk. For example, if you are buying a let us say watermelon, you are not supposed to buy it half, you are supposed to buy it full, even though they'll cut and give you, let us assume that, okay, see, for example, if you are trying to buy a pants, if you want to buy pants, then you cannot cut the pants into half, isn't it? Either you take it completely or you don't take it, that is 0 or 1. You take it, which means 1, or you leave it, which means 0. But then you should not say that I want half pants, right? Which means you cannot take a fraction of it. So some objects are not allowed to be cut into fractions and some objects are allowed to be cut into fractions. And in the previous example of greedy, whatever we have seen there, the objects are under the assumption that they could be cut into fraction. That is called fractional knapsack. In fractional knapsack, we are lucky that we found out the greedy algorithm. Now 0-1 knapsack means we are not supposed to cut the objects, either you put them full or leave it. If there is no capacity to put the object, then leave it, don't put the fraction of it. Now coming to the 0-1 knapsack, it turns out that our greedy method fails, clearly it fails, and this is the example I have specially created just to show you the difference. Now with this example you can find out the difference between how does the fractional knapsack work, I mean the greedy method, how does the greedy method for fractional knapsack is working, and how will it fail in order to find out the 0-1 knapsack solution if I use the greedy method. So observe this. Now here assume that it is 0-1. So now we are talking about 0-1 knapsack, not fractional. Fractional is over in the greedy methods. You please watch that video. I am talking about 0-1 knapsack. So now the capacity of the knapsack, the bag, is 6 units and the weight of each one is 1 unit, 2 unit, 4 units, and the profits are this. If you apply that greedy method, right, what will it do is, it will first find out profit by weight and then sort out the elements according to that and then take the element one by one, and then the last element is going to put the fraction if it doesn't have the capacity. Now let's see how that greedy method works. We are going to find out profit by weight ratio. Profit by weight ratio for 1 is like this. Now I am going to find out profit by weight ratio. Profit by weight ratio is, for this one it is 10, and for this one it is 6, and for this one it is 7, I think. Yeah, right. So profit by weight ratio turned out to be 10, 6 and 7. And now that algorithm is going to take the first element, that greedy algorithm is going to take inside the knapsack. The first element will be the one with the highest P by W ratio, which is nothing but 1. So it is going to put the first element whose weight is how much? 1 unit, and the profit is 10. And next element that will be placed is this one, right? So whose weight is 4 units. So the weight of this is 4 units, and then the profit associated with with it is 28, right? Then what is the total profit we got? 38. Then how much is the space remaining? The total capacity is 6, therefore space remaining is 1. Now when it tries to put the next element remaining, which is nothing but object 2, object 2 weight is 2, but here we have a capacity of 1, which means we could accommodate only half of the object 2. But then I told you that it is 0 1. Either take it completely or leave it, but then don't cut it, like you cannot cut the pants, right? So then what is the answer according to that greedy method we got is 38. 38 is the answer. Now is this actually the maximum possible answer, or is it the optimal answer for 0 1 knapsack? In case if this would have been fractional knapsack, then it would have filled this fraction with the fraction of the third one, and definitely that would be the optimal answer in that case, fractional knapsack. But for 0 1 knapsack, here we got the answer as 38 if I apply the greedy method. Now greedy method is clearly failing for 0 1 knapsack. In case if I get any better answer, see this, I could have got even better answer like this. Instead of filling up, this is item, which one is filled? Item 1 is filled first, and then item 3 is filled. 1 and 3 are accommodated, and that is how I got a profit of 38. Instead of this, if I would have filled up item number 2 first, if I fill up item number 2, what is the profit? 12. And then if I fill up item number 3 next, item number 3 whose profit is 28, then what is the total weight? Weight of this one is 1, item number 2 weight is 2, and item number 4 is 4. So completely it is 6. They both can be filled. Using this combination, I got a profit of 40. This example clearly shows that whatever that greedy method is going to fail for 0 1 knapsack. The reason is, we shall see the reasons later, but now you just understand that greedy method cannot be applied to this. So in this example, if I apply, if greedy method is, what is the time complexity of greedy method? If I have n objects, I have to find out profit by weight ratio and then sort them out. Therefore time complexity is n log n. If greedy method would have been applicable for this problem, we would have been lucky because we'll get a polynomial time algorithm, order of n log n. Now we cannot apply greedy method to this because it is not giving us the optimal answer. So we have to find some other options, right? So what is the next option remaining for optimization problems? Dynamic programming. In order to apply dynamic programming, we have to do three things. One thing is find out the optimal, substructure, and then find out the recursive equations writing these substructures, subproblems, and then find out whether these equations are repeating or not, whether these subproblems are repeating or not. And let's see whether dynamic programming could be applied to this. Right now we cannot say that directly, since the greedy method is failing, we can apply dynamic programming. Dynamic programming is not going to be beneficial unless these three conditions hold. Now let's see about the three conditions. Okay, let's see with one more example why this greedy strategy is definitely not going to work, or why, see, for some of the problems this greedy method is definitely going to give you optimum values, optimal values, but then for some of the problems it is going to fail. Let's see what are the characteristics that should be present in the problem, or what are the types of problems that will definitely make sure that greedy method will fail. If I have a problem like this, assume that the capacity is W, capacity of the knapsack is W, and let us say I have two objects, object number 1 and object number 2, and object number 1 is having, let me write it this way, I have two objects like this, object number 1 and object number 2, and one object is having profit weight. So object 1, it is having profit of 2 and the weight of 1, and the object 2, let us say, is having profit of W and weight of W. Okay, if the problem is of this type, then greedy method will try to find out the profit by weight ratio, isn't it? So it is going to take, and W is just here a variable, I am not writing it as a constant, so for some W, any W, right? And now assume that W is greater than at least 1, greater than 1. Now our greedy method is going to take this. It is going to find out profit by weight ratio and to find out that it is 2, and here it is going to find out profit by weight ratio, it is going to find out that it is 1. Therefore obviously greedy method will choose this one over this one, which means object 1 will get higher priority compared to object 2. Then what it will do is, inside the knapsack it is going to fill it up. What is the total capacity of the knapsack here? It is given as W. So inside this it will fill the object 1 first. So it is going to put object 1 whose weight is 1. Therefore the remaining capacity of the knapsack is going to be W minus 1. And now the profit which we get out of this is 2, right? Now we cannot put the next element, next object, because its weight is W but I have only W minus 1 capacity. Now think about it. If this would have been weight is 10 and profit is 10 for the object 2, or whatever it is, if it is 1000, 1 million, even if it is so big, then even then our greedy method is always going to take this one. Right? So definitely our greedy method is going to fail for all this. It will always give you the answer as in this case it will always give you that the profit is 2, whatever this number is. Actually the profit should be W whenever this weight is greater than 2. If the weight is 3 and 3, obviously this one is going to win, isn't it? So that is the case where greedy method will definitely fail. Then we have to go for some other strategy. Let's see that. Let's examine this problem at depth now. Assume that we have n objects, 1, 2, 3, 4, so on, n objects, and now we have the knapsack. Now let us see if there is any substructure in this. So how can I find it out is whether I will be able to, how can I decrease the size of the problem into smaller problems. That is what I wanted to know. Now I'll consider an element, one element, and then I'll observe whether is there any way, what are the choices that I could make coming to this element. In the final answer of the knapsack, either that element could be included in the knapsack or you might choose not to include it. We have two choices, right? So for every element, finally, either it could be included in the knapsack or it could be left alone, right? In that case, this element has two chances, either it could be included or not. And similarly next element have two chances, either included or not. Next element has two chances. Likewise, every element is going to get two choices, right? Then how many solutions are we going to wind up with? 2 into 2 into 2 into 2 into so on n. Therefore it is 2 power n. We might have to examine 2 power n solutions in order to find out the optimal answer, right? Now let's see in these solutions, let's see the recursive equation. Let's try the recursive equations for this solution and then examine is there any repeating subproblems. If we have any repeating substructures, then maybe we need not actually execute 2 power n times the function. We could do better by storing those repeating substructures in the table. Let's examine that first. So for that I would like to write the equations. First I'll write the equations, recursive equations, and then I'll see the recursion tree and then check whether anything is repeating or not there. First of all, for that let us say Ks represents knapsack and assume that the problem is 1 to I, which means I have the elements from 1 to I, or let's include the weight also. Ks is I comma some W. Okay, what does it mean is, now I have I elements to be considered and the capacity of the knapsack remaining is W. Then I would like to know whether I could include I, or I know I would be better off without including I. I don't know which one I should be making. See this? Therefore I'll try to include I. So assume that every element I, see this I represents that we have elements from 1 to I, and now I'm talking about, I'm standing at the object I and I want to take a decision. What are the two decisions possible? Either you include it or you leave it. Now the assumption is every element is having, ith element is having weight of Wi and profit of Pi, which means the ith element is having profit Pi and it is having a weight of Wi, right? Now you just tell me what are the various cases we have. One thing is, if I include it, what happens? If I include it, I'll be increasing the profit of the knapsack, isn't it? By how much? I value, whatever the profit of the ith element, right? So pi plus, now in the remaining, I should again make the find out the maximum profit in the remaining elements. How many elements are remaining? I minus 1 elements are remaining, but since we have already included the ith element, the capacity of the knapsack is reduced by Wi. Therefore, W minus Wi. This is one case. And the second case is, you might choose not to include it. So if I choose not to include it, then what happens? The profit will not increase, but the advantage is the space is remaining, right? So you need not consider it, which means you need to consider only I minus 1, and then the space is going to remain the same. So which decision you would like to make, either to include it or not include it, that depends on which one is going to give you higher profit, isn't it? If Ks of I comma W represents the profit, maximum profit we could get from including I elements into the, not I, including I elements means some sequence of I elements, some subset of I elements into W is equal to, if I include the ith element, I am going to get this profit, and the remaining problem is going to be this. If I don't include it, that is the profit. Okay. Now whichever is maximum, so I'll find out the maximum among these two, and whichever is maximum, I am going to do that. So provided that, right? So before doing this, I need to check these conditions. One condition is, if I equal to 0, which means if there are no elements to consider, or if W equal to 0, which means there is no capacity in the knapsack, then I should not be doing that, which means in that case profit is completely going to be 0. Or in case if the available capacity is less than the weight of the object, which means our object is having high capacity, which means the weight of the object is very high compared to the capacity available. For example, if capacity of the bag is, remaining capacity is 10, but the weight of the object is 11, then obviously we cannot put it because it is 0-1 knapsack. Therefore, we should even consider that case. If the capacity of the object Wi is greater than the available capacity of the knapsack, then we are not going to put it. Then what happens? We should not consider it. So you leave it, and then you take the remaining sequence and examine it. Then what is it? Then the knapsack profit will be, you are going to leave it out. So simply you are going to leave it out, and you have to consider this one, right? These are the equations. So just examine this. If I have elements 1 to I and the capacity of the knapsack is W, in case if there are no elements, which means if I equal to 0, then the knapsack profit we are going to get from that is 0, right? In case if the object weight is, the ith object weight is greater than the available capacity, obviously we cannot put it. So leave it and then compute the problem for remaining I minus 1 elements, assuming that the capacity available is W, which is initially given. Or if the element is eligible to be kept inside the bag, which means the capacity of the knapsack is greater than the weight of the element, then we have these conditions. Either you include it or you don't include it. Then your decision is going to depend on which one is greater, which means either this one is greater or this one is greater. Therefore, depending on this, you need not make all possible function calls. Depending on which one is greater, you need to call only that. Okay, we shall go to that later. First you understand these equations. This is how we should write the equations. Now once we have written the equations, what is the final answer is, given n elements, then if you have to compute knapsack of n elements are given, and let us say capacity of the knapsack is C. You are going to call this one. So if you call this one, if you write these recursive equations, and if you write the recursive function, let's see what happens by seeing the recursion tree. Okay. Now we shall consider the problem of subset sum. So it is given a set of n numbers like a1, a2, so on, set of n numbers. Question is there any subset of this set whose sum, which means when I add all these numbers, whose sum is equal to some number W, right? So given a number W, can you find out some subset from this which is equal to this, right? I'll just take an example and explain you. Let us say we have some numbers like this, 6, 2, 3, 1, set of 4 numbers. The question could be, is there any subset of these 4 numbers whose sum is equal to 5, right? So what is the answer? Yes, there is a subset. And what is that? 2 plus 3. This problem is exactly, or I cannot say exactly, but this problem is similar to the 0-1 knapsack problem. Same as 0-1 knapsack problem, we could characterize this, we could characterize the sub-problems, and we could write the equations, and we could even solve the problem the same way we did 0-1 knapsack. There is a correlation between this, right? So let's examine this first. How can we solve it? First of all, without using dynamic programming, can we go with greedy? So greedy is definitely not applicable here. If you try to be greedy, you don't know whether to take the smallest number or the highest number. So there is no way you could go with greedy. So if you take greedy, then it will obviously say that if you try to be greedy on smaller numbers, it will say that you take 1. So if I take 1, then the remaining sum is going to be 4, right? So there is no number which is 4. Therefore greedy doesn't work there. And what is the other method? Brute force method, right? So brute force method is you take all possible subsets. How many subsets will be there? If I take the all possible subsets, an element can be present in a subset or it may not be present. An element may be present in a subset or it may not be present. Therefore, every element has two choices. Either it could be present in a subset or it may not be present. Therefore, how many subsets we get? If I have n elements, then I am going to get number of subsets equal to 2 power n. Then examine the sum of each subset and see if it is equal to W. So that is one algorithm, the brute force method, which is obviously going to take 2 power n time, right? Now let's write some equations, recursive equations, and see if that could be written in terms of a recursive function, and let's see if any functions are repeating, so that we could use the tabular method and dynamic programming. For that, let's write the recursive equations. So after seeing all these three examples, matrix chain multiplication, longest common subsequence, and 0-1 knapsack, you should be able to understand this question very fast. See this? Let us assume that I am using subset sum from, I want to consider from A1 to AI. So if I have I elements and I want to find out, is there a subset among these I elements whose sum is equal to, let us say, some W. Let's not say W, let us say whose sum is equal to some S, some S, right? Now what are the conditions? In the final subset which you wanted, whose sum has to be equal to S, the element at ith location may be present or it might not be present, right? Now let's take two cases. Now it would be possible in case, okay, first thing is, let's write the base conditions. If I equal to 0, which means if there are no elements, is there any sum which is possible for S? I equal to 0 and S is not equal to 0, which means there are no elements, but then we want to produce a sum of some number. Is that ever possible? Which means if there are no elements at all, can I produce a sum of 5? No way, right? So for this, the answer is false, which means it is not possible. The answer is no. Now, if the sum is, if there are no elements, let us say the other case is I equal to 0 and S equal to 0, which means if there are no elements, is the sum S equal to 0 possible? Yes. Or is the sum S equal to 0 possible? A sum S equal to 0 is always possible, and the simplest way is don't choose anything, then the sum is going to be 0. Null set is always going to be sum is 0, right? So for this, it is always true. So these are the base. If the sum is equal to 0, it is always possible. Or if I equal to 0, which means if no elements are there, then if you want some sum, it is not possible, right? So these two are the base conditions, and from there we can derive the other conditions. Now, if this sum using I elements, if this sum has to be possible, then there are two cases. If I include the ith element in my subset, right, then a sum of S minus AI should be possible with the remaining I minus 1 elements, which means if you have A1, A2, so on, ai minus 1 ai. Now if you include this in my set where I wanted to make this sum as s, if you include it, then using this ai minus 1 we should be able to get a sum of s minus ai, which means if I have array like this, if I have elements 1, 2, 3, 4 like this, okay, and if I wanted to form a sum of 10, then if I include this 4, then with the remaining elements a sum of 6 must be possible. If the sum of 6 is possible from these numbers, then only a sum of 10 is possible from all these numbers. That is the meaning of it, right? Therefore this sum is possible using I elements. In case if I include the ith element, then using those I minus 1 elements, the sum of s minus ai should be possible, or which means either using I minus 1 element, this one should be possible if ai is included, or if ai is not included, which means if I remove ai directly, then si minus 1 comma s. If I don't include ai, then the sum of this swing is possible with I elements. If I don't include ai, then with I minus 1 elements if this is possible, right? These are the two cases. It is exactly same as that knapsack. There also we did the same thing, but then there we have even included the profits. We are taking ith element, and in that if you remember that 0 on knapsack, we are taking the ith element, and if we include the ith element, we are going to reduce the capacity of the knapsack. Here also we are going to reduce this sum, isn't it? There we have added the profit, but here I am just ORing it. So this symbol is nothing but OR, which means true or true is true, true or false is false, true or false is true. It is nothing but AND, right? So sorry, OR. True or true is true, true or false is true, false or true is true, false or false is false. And then there is one more case. So one more case is if there is no possibility that I could include this element at all. There is no possibility that I could include this element and get a sum of s. So when is that possible? Whenever the required sum is less than this element value, which means in case if the required sum, what is the required sum? Required sum is s. If s is less than ai, then there is no way you could include ai. If I include ai, the sum is going to exceed the required sum s. Then what is that? Then in that case leave out I, and then in the remaining elements you find out the sum s. Then what about this one? This one is provided that s is greater than ai, right? So these two conditions are exactly same as that of the knapsack. If you can recollect it, they are exactly same. Okay, please do that. And now let's see, if I implement this program, if I implement this recursive equation as a recursive program, let's see what happens. Let us take for example ss of 10 comma 10. I have 10 elements and I want a sum of 10, right? Then it is going to call ss of 9 comma 10 minus some value, or ss of 9 comma 10, which means if you assume that the 10th one's weight is the 10th element weight is 1, in worst case it is going to be 1, just like how we did it in the knapsack. If I assume it like this, then it is going to be ss of 9 comma 9 or ss of 9 comma 10, and again this one is going to be subset sum of 8 comma 8 or subset sum of 8 comma 9. This one is going to be subset sum of 8 comma 9 or subset sum of 8 comma 10, right? So you can see that the problems are repeating, isn't it? And now you can even see that the depth of the tree is going to be order of n. The depth of the tree is going to be order of n, same as that 0-1 knapsack, and the number of nodes could be as many as order of 2 power n. Therefore, if I implement this program directly, it is going to take an order of 2 power n time. But then we are in some luck here because the problems are repeating. Now if you count the number of problems which are repeating, if you just count all the problems which are repeating, you can find out that we have nearly, if the problem is subset sum of n comma w, which means n elements are there and the number, and what we wanted is to see that there is a subset whose sum is w. Then we can form it, we can find out the number of unique subproblems will be n into w. Therefore we could use the tabular method in which there will be n rows and w columns exactly like 0 1 knapsack, and then we can find out we can fill each entry one by one, right? Let's see the table. I'll take an example and I'll take a table and I'll show you this. Okay, so anyway it is exactly same as 0 1 knapsack, right? I'll just take an example. I'm not going to give you the algorithm. The algorithm is same as the modification to 0 1 knapsack. I'll just take an example and explain you, and finally we shall prove that the time complexity is going to be n into w, right? First I'll define about this traveling salesman problem. The problem is this. Let us assume that there are some cities. I'll just take an example. Let us assume that there are 5 cities like this, and all these cities are connected through roads, and just for the sake of this example, assume that every city is connected to every other city. I just wanted to take the worst case. Okay, so let us say it is city A, B, C, D, E. Now there is a salesman who is living in city A here at this point, and his job is this: every day he has to wake up and then take some goods and go to every other city. Let us say these are not cities are too far, so let's say they are villages. Let us say he's living in one village. Every day morning he'll wake up in that village, and now he is going to go to every other village and sell the goods, and by the end of the day he has to come back to his city and then sleep, right? So he cannot afford to be at any other city, so he has to take an entire circle and then come back, right? So what is the problem here is, you have to pass through every vertex exactly once. What happens if you are passing through a vertex more than once is, you are unnecessarily visiting a village 2 times. That is definitely a waste of time. If you are going from this village, and if you are passing through all the villages exactly once, and if you are coming back, that is what you wanted. You wanted to sell your goods to every village exactly once in one day, right? But then if you are trying to visit a village 2 times, then what has happened is, you are unnecessarily taking a long path. If you are taking a path by visiting a village 2 times, then you could have taken a better path by visiting the village once, because there must be a cycle inside that cycle, right? So what is that? This problem is also visiting every vertex once, exactly once, and again coming back to the same vertex. It is also sometimes called as, or it is popularly known as, Hamiltonian circuit or Hamiltonian cycle, right? And Hamiltonian cycle, finding a Hamiltonian cycle is one thing, and this problem is even bigger. The reason is, it is not just about finding the Hamiltonian cycle, it is even finding out the minimum cost. The reason is, every road or every link here is having the weights. So I want to traverse exactly those edges, which will help me in visiting every vertex once, every city once, and now the total cost put together, it should be less, as minimum as possible. Let us say the distances are like this: 1, 2, 3, 4, 1, 2, 3, 4, 5, something like this. Now given all these distances, the problem is, how can you find out the set of edges which, when traversed, is going to cover all the vertices, so that the total sum of the weights on the edges is as minimum as possible, which means without traveling too much distance, or by traveling as minimum distance as possible, I want to visit every vertex, right? So that is the traveling salesman problem. It has many applications. Maybe you could think about it as the mail delivery. Let us say a postman, he wants to cover, distribute the postcards to all the villages, right? Or it could be even a truck which is going to deliver the goods to all the places. Then the problem is, what is the minimum distance that they have to travel in order to cover all these points and exactly ones, and again come back to the same point, right? So that is about the traveling salesman problem. So how to solve it is, one way is exhaustive enumeration, or that is also called as brute force method. So brute force method says that find out all possible paths, and then you count the, you find out the weights of every path and you take the minimum. That is the brute force, right? So if I try to find out all possible paths, so there will be many, by A, B, C, D, E, and again A. This is one path. Or A, C, B, D, E, A. This is again one more path. Or A, I can start with D, and then B, and C, and E, and again A. So there will be many paths, right? So how many paths? If you fix the starting vertex and the ending vertex, which are nothing but one and the same, and how many are remaining? N minus 1. You will have as many as n minus 1 factorial. If I have n nodes, you will have these many permutations, and therefore these many cycles are possible, and now you have to find out the minimum among all these cycles, right? Therefore it is exhaustive enumeration is nothing but it is order of n square algorithm. You have to find out all these paths and then the distances and then the minimum, right? Order of n square is even worse than 2 power n. See, we have already seen some problems like subset selection 0 1, subset sum and 0 1, 0 1 knapsack, and then subset sum. If you go for the enumeration or brute force method, these problems have produced complexity of order of 2 power n for brute force methods, right? And now for the brute force method, this problem is producing a space of order of n factorial, and n factorial is very much greater than 2 power n. So this is the worst possible case you could imagine, right? So yes, there is algorithm which you could solve, but then look at the complexity. Order of n square is nothing but order of n factorial is nothing but order of n power n. It is even worse than order of 2 power n, right? It is the biggest of all the problems that we have examined till now, right? And now if you have to solve it, exhaustive method is not going to help. That brute force method is not going to help. Only method that might help is dynamic programming, in case if you are able to write this problem in terms of small problems, which means substructure should be there, and then if you are able to find out the recursive equation and see if there are any repeating sub problems, right? Or count the number of problems and see if there are any repeating sub problems. If there are repeating problems, we shall apply it. Okay, let's see that. Till now we have been seeing the problems where we have one source and many destinations, which means we have been trying to find out the single source shortest path, which means from one source we want to find out the shortest path to all other nodes, right? But there is some other problem which is actually kind of this, which is not exactly. It is called all pairs shortest path problem. All pairs means we have to take every node and we have to take every other node, and we have to find out the shortest distance between those two. So I'll just take an example and I'll show you. See, till now we are saying that we have a node called as source, and we have all the remaining nodes, and we wanted to find out the shortest path from this source to all the other nodes, all of them, okay, shortest paths. But now the problem is we want to find out shortest path not just from single source, from all the sources. So what we want to do is we want to find out the shortest path from this one as the source to all the other nodes, and this one as the source to all the other nodes, like that. It is also called as all pairs shortest path, which is nothing but we can find out the shortest path between every two pairs. But if I apply the single source shortest path, in this the pair is always going to contain S, which means S comma A, shortest path from S to A, shortest path from S to B, shortest path from S to C, right? Like this the single source shortest path is going to have. But if I say that we want all pairs shortest path, what I mean to say is between every two, which means I can find out the shortest path from A to B like this, as well as I can find out the shortest path from S to A, as well as I can find out the shortest path from A to C. So every node is going to be a source and every other node is going to be a destination. Got it? So now what is the relationship between single source shortest path and all pair shortest path is, you could run the single source shortest path from every vertex, then it will become all pair shortest path, but it is actually computationally slow. For example, if you apply the Dijkstra algorithm, you know that Dijkstra algorithm, when implemented using a min heap, there are various other implementations like Fibonacci heap which are not in the syllabus, but if you apply the Dijkstra algorithm using binary min heap, we know that the time complexity taken is order of e into log v. Remember why? We are going to decrease the key. For time taken for decreasing the key is log v, and we are going to decrease the key exactly, in the order of e times. Therefore, time complexity of Dijkstra algorithm is this thing. And now, if this Dijkstra algorithm is applied for every vertex, then the total time complexity for all pairs shortest path using Dijkstra algorithm is order of v into e into log v. And we already know that a number of edges is always order of v square. So it doesn't. It is also true that in case of dense graphs, you can write this as order of, in place of e, you can write v square. Then we are going to get order of v cube log v. In case of dense graphs, in case of sparse graphs, you can leave it like this. Got it? So Dijkstra algorithm might go as much as order of v square log v. For all pairs shortest path, but the problem with Dijkstra algorithm is it cannot work for all the negative weight edges. That is why we have to go for some Bellman-ford algorithm if you have the graph with negative weight edges. So if you take the Bellman-ford algorithm, the time complexity of Bellman-ford algorithm is, we already know that it is order of v into e, right? And now if I have to run this Bellman-ford algorithm on every vertex, if there are v vertices, then the total time complexity taken by the all pairs shortest path implemented using Bellman-ford algorithm is order of v square into e, and we know that e is order of v square in the dense graphs. Therefore, it is going to be order of v power 4. So if I use Bellman-ford algorithm for all pairs shortest path, it is going to be order of v power 4. And if I use Dijkstra algorithm for order of shortest path, it is going to be order of v cube log v. So what our intention is, both this order of v power 4 or order of v cube log v is actually too much. So we wanted to decrease it. It turns out that using dynamic programming, if we go using dynamic programming, then we can implement it in a better way. So for example, one more thing, Dijkstra algorithm is greedy algorithm. So keep that in mind. Dijkstra algorithm is a kind of greedy algorithm. The reason is always we are going to take the minimum and then compute it. Got it? And now we are going to go for dynamic algorithms, dynamic programming methods in order to compute the all pairs shortest path, which is better compared to either implementing it through Bellman-ford or Dijkstra algorithm. Okay, so we shall see that. Let's see how to apply dynamic programming to all pairs shortest path. So before applying it, we should find out whether there is any substructure. We should formulate the question and then see whether there is any substructure, and then if it is possible, then write the recursive equations and then see if the recursive equations are repeating, if any subproblems are repeating, and then we shall apply the dynamic programming method. Okay, watch this. Let us assume that there are two nodes. First of all, the set of all vertices in the graph are 1, 2, 3, so on n. All the vertices are numbered like this, 1, 2, 3, so on n. And then we are going to have ij be two vertices which belong to V. Now I represent Dij. Dij be the shortest distance from I to j, right? So the distance of the shortest path from I to j is represented by this factor, but then with just some other extra thing here. What I want is I don't want the shortest path from I to j over all these vertices. Now I want to find out the shortest path between I to j in such a way that the vertices which are included are 1 to k. So I write like this. So what does this representation mean is, I want to find out among all the paths what is the shortest path from I to j, which will include only the vertices 1 to k, which means I am supposed to use only the vertices 1, 2, 3, so on k. Even though I have vertices till n, I am going to use it only till k, right? Now let us say I got the shortest path, and let me call it shortest path is some p. This is the shortest path from Dij, which contains only maximum of in between I and j only k vertices, 1 2 3 4 so on, k vertices are present, right? Now P could be divided into two cases. First thing is, the path P might contain this vertex k, or the path P might not contain the vertex k. In case among all the shortest paths using all these vertices, if the shortest path does not contain k at all, then it is nothing but we are better off without using the this one. So without using the vertex k. So in case if our vertex does not contain k, then definitely it is I could represent like this. Then the distance of the shortest path from I to j is nothing but distance of the shortest path from I to j without k, because even if you give it k, it is not using it. Therefore the distance of the shortest path from I to k is nothing but the distance of the shortest path from I to j without without using k. Maximum is k minus 1. Or the other way is, now this path, if this path is containing the vertex k, then what I would like to do is, I'll take the path P and now I divide into two paths, P1 and P2, in such a way that P1 is a path from I to k, because you know that k is already present in the path P, therefore I am dividing it into two parts exactly at the node k. Then this entire path is divided as I to k plus k to j, right? And since we have removed k, definitely I to k will not contain k again. Why? If I to j path is containing all the vertices till k, and now if you remove k from the path, which means let us say the path is like this, I 1 2 3 so on k, and again some j, some l, m, and so on, there is j. Now I am dividing it like this. I am taking the path from I to k and then I am taking the path from k to j. Then this path will definitely not contain k in the middle, right? Why? If it already contains k in the middle, it cannot be the shortest path from, see, if somewhere here if k has arisen, then this entire path cannot be the shortest path from I to k. Why? There is a path from I to k here itself, right? Therefore I am splitting the path into two paths in such a way that first path will not contain k, as well as the second part will not contain k. So first path will start from I and end at k, second path will start at k and end at j, right? Now look at this. So this path is broken like this, and since it does not use k, I can write like this, k minus 1 and k minus 1. So this is the total length of the path. So what does it mean? If you are having I to j is the distance between I and j, which are including in the path at most k vertices, then the kth vertex may be present or it might not be present, right? So if it is not present, then definitely the distance between I to j using k minus 1 vertices, that is the minimum, right? In case if it is present, then I am breaking it into two parts. Then what do I get? D I to j using k minus 1 vertices plus d j to k using k minus 1 vertices, right? So if I use k in my path, this is the distance I get, and if I don't use k, this is the distance I get, right? Therefore I am able to divide a big problem into smaller problems. What is the big problem? In till k. What is the smaller problem? K minus 1. Now you should know where to stop it, right? So that is why we need the base condition. So what is the base condition for this one is, what is the distance from I to j if I don't include any vertex? If I don't include any vertex in the middle, it is nothing but the path containing single edge, right? So in case, this is the case when k is greater than 0. In case if k equal to 0, which means I don't want to go through any vertices on the way, I just want to directly go from I to j in single edge. Then what is the distance? Then the distance is nothing but weight of ij, right? So I don't know whether you understood this concept or not. What I'll do is, I'll take an example and then we shall solve the example completely without the equations, and again I'll revisit the equations and then we shall see how to apply the dynamic programming. Okay, I'll take an example.